your calculator and you get 0.53, which as far as I know is always bigger than a half. So this proves the birthday paradox, and you notice it was crucial to assume that the samples are independent of one another. We only proved it for the uniform distribution, but as I said, it's actually fairly easy to argue now that any distribution that's away from the uniform distribution will satisfy this with even a lower bound. So if you have 1.2 square root of b, the theorem will certainly hold for non-uniform distributions. The reason it's called a paradox is because it's very paradoxical that the square root function grows very slowly. In particular, if you try to apply this to birth dates, so let's assume that we have a number of people in a room, and let's assume that their birth dates are independent of one another and are uniform in the interval 1 to 365, then what the birthday paradox says is that we need roughly 1.2 times square root of 365, which I believe is something like 23, which says we need roughly 23 people in a room, and then with probability 1/2, 2 of them will actually have the same birthday. The reason it's called a paradox is because the number 23 seems really small to people, and yet by this theorem that we just proved, with probability 1/2, there will be 2 people with the same birthday. By the way, the intuition for why this fact is true is because really what the collision is counting is it's looking at all possible pairs of people, and if you have a square root of b people, then there are square root of b squared pairs, roughly, which is roughly b pairs total, and so it's very likely that each pair collides with probability 1/b, and if you have b pairs, it's likely that one of the pairs will collide. So hopefully this gives you intuition for where the square root comes from. It's basically from the fact that if you have n people in a room, there are n squared possible pairs. I should say, by the way, that even though the birthday paradox is often applied to birth dates are actually not uniform at all. If you actually look at the birth dates of people, you see that there's a very clear bias towards being born in September, and for some bizarre reason there's also a bias towards being born on a Tuesday. And so when we apply the birthday paradox to birthdays, in fact the actual bound is going to be smaller than 1 minus 2 square root of b, because we said that for non-uniform distributions you need even fewer samples before you get a collision. So let me show you a graph of the birthday paradox. It's quite interesting how it behaves. So here I set b to be 1,000,000. In other words, we're picking random uniform samples in the range 1 to 1,000,000. And the x-axis here is the number of samples that we're picking, and the y-axis is the probability that we get a collision among those n samples. So we see that the probability of 1/2 happens around 1.2 square root of b, roughly 1200, 1.2 square root of b. And you see that if we look at exactly square root of b, the probability for a collision is around 0.4 or 0.41. And you notice the probability goes up to 1 extremely fast. For example, already at roughly 2 square root of b, the probability of a collision is already 90%. Similarly, when we go below square root of b, the probability of a collision very, very quickly drops to 0. Okay, so there's kind of a threshold phenomena around square root of b, where the probability for a collision goes to 1 very quickly above square root of b, and drops to 0 very quickly below square root of b. So now we can analyze our attack algorithm. So let me remind you, here we chose 2 to the n over 2 random elements in the message space. We hashed them. And so we started off with a random distribution in the message space. After we hashed them, we end up with some distribution. This distribution over tags might not be uniform, but we don't care. The point is that all these tags, t1 to t2 to the n over 2, are independent of one another. And as a result, if we choose 2 to the n over 2 or 1.2 to the n over 2 tags, the probability that a collision will exist is roughly 1/2. So let me ask you then, in that case, how many times do we have to iterate this algorithm before we actually find a collision? Well, so since each iteration is going to find a collision with probability 1/2, we have to iterate about 2 times in expectation. And as a result, the running time of this algorithm is basically 2 to the n over 2 evaluations of the hash functions. Okay, so notice also this algorithm takes a lot of space, but we're going to ignore the space issue, and we're just going to focus on the running time. Okay, so this is kind of cool. This says that if your hash function outputs n-bit outputs, there will always be an attack algorithm that runs in time 2 to the n over 2. So for example, if we output 128-bit outputs, then a collision could be found in time 2 to the 64, which is not considered sufficiently secure. Okay, so this is why collision-resistant hash functions generally are not going to output 128 bits. So let me show you some examples. The first 3 are actually federal standards, SHA-1, SHA-256, and SHA-512. And the fourth one is an example from the designers of AES called Whirlpool. And so you can see SHA-1 outputs 160 bits, and as a result there's a generic attack on it that runs in time 2 to the 80. SHA-256 outputs 256 bits, so the generic attack will run in time 2 to the 128, and so on and so forth. I also listed the speeds of these algorithms, and you notice that the bigger the block size, actually the slower the algorithm is, and so there's a performance penalty, but nevertheless there's quite a bit of benefit in terms of security. Now you notice the SHA function is actually grayed out. The SHA function, although nobody has found collisions for SHA-1 yet, it's still recommended that in new projects and hopefully in programming projects in this class, you don't use SHA-1, instead use SHA-256. And in particular, there is actually a theoretical collision finder on SHA-1 that works in time 2 to the 51. So it's probably just a matter of time until finally someone finds a collision for SHA-1 and just kills altogether. But the current advice is SHA-1 is still a collision-resistant hash function because nobody has found collisions for it, but it's probably just a matter of time, just a few months or a few years until a collision is found. And as a result, in new products and new projects, SHA-1 should not be used and only use SHA-256, or if you want to be even more cautious, then use SHA-512. So this is the end of this segment, and now we're going to turn to building collision-resistant hash functions. So now we're going to look at a very general paradigm called the Merkle-Damgard Paradigm that's used for constructing collision-resistant hash functions. Before we do that, let me just remind you what our goals are. So as usual, we say that H is a hash function that maps some large message space into a small tag space. And we say that a collision for the hash function is basically a pair of distinct messages that happen to map to the same value under this hash function. And our goal is to build collision-resistant hash functions, namely functions where it's hard to find even a single collision. Even though we know many collisions exist, no efficient algorithm can even output a single collision. So we're going to construct these hash functions, these collision-resistant hash functions, in two steps. The first step, which we're going to do in this segment, is to show that if you give me a collision-resistant hash function for short messages, we can extend it and build a collision-resistant hash function for much longer messages. In the next segment, we'll actually build collision-resistant hash functions for short messages. Okay, so let's look at the construction. The construction is actually very general, and in fact, all collision-resistant hash functions follow this paradigm. It's actually a very elegant paradigm, and let me show you how it works. So here we have our function h, which we're going to assume is a collision-resistant hash function for small size inputs. So the way we're going to use this little function h, this h is sometimes called a compression function, is we're going to take a big message m and break this message into blocks, and then we use a fixed value called the IV. Here in this case the IV is fixed forever, and it's basically embedded in the code and in the standards. It's just a fixed IV that's part of the definition of the function. And then what we do is we apply the small compression function h to the first message block along with this IV. What comes out of that is what's called a chaining variable that's going to be fed into the next compression function, which compresses the next block along with the previous chaining variable, and out comes the next chaining variable, and the next message block is compressed, and so on and so forth, until we reach the final message block. And in the final message block, the one special thing that we do is we must append this padding block, this PB, which stands for padding block, and I'll explain what the padding block is in just a second. But after we append the padding block, we again compress the last chaining variable with the last message block, and the output of that is the actual output of the hash function. So just to summarize, in symbols, we have this compression function that maps elements in T. This is the output of the hash function, plus message blocks. This X corresponds to message blocks, and outputs the next chaining variable. So as I said, this is what the compression functions do. And then from this compression function, we're able to build a hash function for large inputs, namely inputs in the space X to some power of L, namely up to L blocks of X. And of course, these are variable length, so we can have different length messages that are being given as input to this function H. And what comes out of it is basically a tag in the tag space. So the only thing that's left to define is the padding block. And so the padding block actually is very important, as we're going to see in just a minute. What it is basically, well, it's a sequence of 1, 0, 0, 0, just to denote the end of the actual message block. And then the most important part of the padding block is that we encode the message length in this padding block. And the message length field is basically fixed to be 64 bits. So in all the SHA hash functions, the maximum message length is 2 to the 64 minus 1. So in fact, the message length fits into a 64-bit block. and an upper bound of 2 to the 64 minus 1 bits on the message length is actually sufficiently long to handle all the messages we're going to throw at it. Okay, so that's the padding block, and of course the question is, what do we do if the last block really is a multiple of the compression function block length? Where are we going to fit the padding block? And the answer, as usual, is basically if there's no space for the padding block in the last block of the message, then we're going to have to add another dummy block and stick the padding block in there, and of course put the 1000 in the right place. Okay, so the point is it's very, very important that the padding block contains the message length, as we'll see in just a minute. So this is the Merkle-Damgard construction. The last piece of terminology I'll say is that we have these chaining variables. So H0 is the initial value, H1, H2, H3, up to H4, which is the actual final output of this hash function. So as I said, all standard hash functions follow this paradigm for constructing a collision-resistant hash function from a compression function. The reason this paradigm is so popular is because of the following theorem, which says basically that if the little compression function is collision resistant, then the big Merkle-Damgard hash function is also collision resistant. So in other words, if we're going to build collision resistant functions for large inputs, all we have to do is just build compression functions that are collision resistant. So let's prove this theorem. It's an elegant proof and it's not too difficult. So the way we're going to prove it is using the contrapositive. That is, if you can find me a collision on the big hash function, then we're going to deduce a collision on the little compression function. Therefore, if little h is collision resistant, so will be the big H. So suppose you give me a collision on the big compression function, namely two distinct messages m and m prime that happen to hash to the same output, we're going to use m and m prime to build a collision on the little compression function. So the first thing is we have to remember how the Merkle-Damgard construction works, and in particular, let's assign names to the chaining variables when we hash m versus when we hash m prime. So here are the chaining variables that come up when we hash the message capital M. So H0 is the fixed IV that starts the whole process. H1 would be the result of hashing the first message block with the IV, and so on and so forth, until H sub t plus 1 is the final chaining variable, which is the final output of the Merkle-Damgard chain. And then similarly for m prime, let's define H0 prime to be the first chaining variable, H1 prime to be the result after compressing the first message block of m prime, and so on and so forth, up until we get to h prime of r plus 1, which is the final hash of the message m prime. Now you notice the length of the messages m and m prime don't have to be the same. In particular, m has length t, whereas m prime has length r. Now because the collision occurred, we know that these two values here are the same. H of m is equal to h of m prime. In other words, the last chaining variables are actually equal to one another. So now let's look carefully how ht plus 1 and h prime r plus 1 were calculated. Well, ht plus 1 is calculated as the compression function applied to the previous chaining variable along with the last message block of m, including the padding block. You notice here I'm assuming that the padding block fits with the last message block of m. Even if the last padding block is in its own block, it's not going to make any difference. So for simplicity, let's assume that the padding block fits with the last message block of capital M. So by hashing the last message block with the padding block and the last chaining variable, we obtain ht plus 1. And similarly, the same thing happens with m prime. By hashing the last message block, the last chaining variable, we obtain h prime r plus 1. And we know that since these two values are equal, all of a sudden we have a candidate collision for the compression function. Here, let me circle the candidate collision. This is one part of it, and this is the other part of it. Okay, so we have an equality between two arguments given to the compression function that happen to produce the same value. The only way we would not get a collision is if the arguments happen to be the same. In other words, what we're saying here is if the arguments to the compression function are distinct, then we get a collision for little h. So let's write it out more precisely. So if ht is not equal to h prime r, or mt is not equal to m prime r, or the padding blocks are distinct, then we have a collision for the compression function h, and we're done. We're done and we can stop. So the only way we need to continue is if this three-way disjunction doesn't hold. So what does it mean that this junction doesn't hold? Well, so the only reason we need to continue is if the second to last chaining variables are equal, the last blocks of the messages are equal, and the two padding blocks are equal. So what does it mean that the two padding blocks are equal? Remember that the message lengths were encoded in the padding block. So in particular, this means that the length of m and the length of m prime is the same, namely that t is equal to r. So from now on, I can assume t is equal to r. Whenever I wrote r, I'm just going to write t. But now we can apply exactly the same argument to the second to last chaining variables. In other words, how was ht computed? Well, ht is computed by hashing the previous chaining variable, namely ht minus 1, with the second to last message block. And similarly, ht prime was computed, you notice I replaced r by t, so ht prime was computed by hashing the previous chaining variable along with the second to last message block of m prime. And because these two are equal, now we get another candidate collision for the compression function. In other words, if ht minus 1 is not equal to ht minus 1 prime, or mt minus 1 is not equal to m prime t minus 1, then basically we have a collision for h, and we can stop. We're done. So now the only case when we need to continue is if this condition over here doesn't hold, namely, so let's suppose that ht minus 1 is equal to h prime t minus 1, and we already know that, let's see, so mt is equal to mt prime, and mt minus 1 is equal to mt minus 1 prime. Suppose it so happens that these two condition holds. Well, you can see that now we can continue to iterate. In other words, we can now apply exactly the same argument to ht minus 1 and ht minus 1 prime. And so iterating this again and again, we can iterate all the way to the beginning of the message, iterate to the beginning of the message, and one of two things must hold. Either we find a collision for the compression function, or it so happens that all the message blocks of m and m prime are the same. In other words, for all I, mi is equal to mi prime. But this means, because the messages, we already proved the messages are the same length, this means that m is actually equal to m prime. But then this contradicts the fact that you gave me a collision to begin with. So in other words, this condition over here can't actually happen because it contradicts the fact that m and m prime are actually a collision for the big Merkle-Damgard function, capital H. And as a result, this means that we have to find a collision for the compression function, so that as we work our way from the end of the message all the way to the beginning, at some point we must find the collision for little h. Okay, so this basically completes the proof of the theorem, so I can put a little QED block here. So basically what this proves is that if the little compression function h is collision resistant, then the big Merkle-Damgard function, capital H, must also be collision resistant. So again, the reason why people like this construction is it shows that to construct big hash functions, it suffices to construct just compression functions for small inputs. And we're going to do that in the next segment. So our goal for this segment is to build secure compression functions. So compression functions that are collision resistant. So just to remind you where we are, we looked at this Merkle-Damgard construction, which takes a little compression function and builds from it a hash function for much, much larger inputs. And we proved this Q theorem that says that, in fact, if the little compression function h is collision resistant, then plugging it into the Merkle-Damgard construction gives us a collision resistant hash function for larger inputs. So now in this segment, our goal is basically to build a compression function that is collision resistant. So we're going to see a couple of constructions. And so the first question that comes to mind is, well, can we build compression functions from primitives that we already have? In particular, we spent a lot of work to build block ciphers. And the question is, can we build compression functions from block ciphers? And the answer is yes. And let me show you how to do it. So assume we have a certain block cipher. Here it operates on n-bit blocks. So the input is in n bits, output is n bits. And then there's this classic construction called the Davies-Mayer construction, which I wrote down in symbols here. Basically says that what you would do is, given the message block and the chaining variable, all we do is we encrypt the chaining variable using the message block as a key, and then we kind of do one more XOR on the output. So this might seem a little bizarre, because remember, the message block is something that's completely under the control of the adversary. He's trying to find a collision, so he can choose the message blocks however he wants. And yet we're using this message block as a key into a block cipher. But nevertheless, we can argue that this construction, at least when E is what's called an ideal cipher, we can argue that this construction, in fact, is as collision resistant as possible. So let me state the theorem. The theorem states that, as I said, if E is an ideal block cipher, meaning that it's a random collection of k random permutations from 0, 1 to the n to 0, 1 to the n, then under that assumption that E is an ideal block cipher, in fact, finding a collision for this compression function h takes time 2 to the n over 2. In particular, we can show that anyone who's finding collisions has to evaluate the encryption and decryption functions at least 2 to the n over 2 times. And if you think about what that means, since the output of this compression function is only n bits long, we know that there's always a generic birthday attack that finds collisions in time 2 to the n over 2. So basically, this theorem says that this collision-resistant function is as collision-resistant as possible. We can find the collision in time 2 to the n over 2 using the birthday attack, but there is no algorithm that will do better than 2 to the n over 2. So Davies-Meyer is actually a very common compression function used in collision-resistant hashing. In fact, the SHA functions all use Davies-Meyer. It turns out there's something special about the Davies-Meyer construction that makes it collision-resistant. If you just try to guess a construction, very likely you'll end up with something that's not collision-resistant. And so let me ask you the following puzzle. Suppose we actually define the compression function as follows. Namely, all we do is we encrypt the chaining variable h using the current message block as the key. So the difference is that we dropped this XOR h in Davies-Meyer, we simply ignored it. So it's not there. And the puzzle for you is show me that this compression function then is actually not collision resistant. So let's see. So we're trying to build a collision, namely a distinct pair of hm and h prime m prime that happen to collide under this little function h. And my question to you is, how would you do it? So I'm already going to tell you that you're going to choose h, m, and m prime arbitrarily. The only requirement is that m and m prime are distinct. And then my question is, how would you construct an h prime that would cause a collision to pop out? So the answer is the first choice, and the easy way to see it is if we apply the encryption function using m prime to both sides, then we get that this is basically e of m prime applied to h prime, right? This is what we get by applying encryption using m prime to the left-hand side. And if we apply encryption using m prime to the right-hand side, the decryption operator cancels out, and we simply are left with the encryption of m comma h, which is exactly the collision that we wanted to find. So there, you can see that it's basically by using the decryption function d, it's very easy to build collisions for this compression function. Now I should tell you that in fact, Davies-Meyer is not unique. There are other ways to build collision-resistant compression functions from block ciphers. For example, here's a method called Miyaguchi-Pernille. Miyaguchi-Pernille actually is used in Whirlpool hash function that we saw earlier. Here's another method that happens to result in a collision-resistant compression function. And there are 12 variants like this, playing with XORs and placing the variables in different slots that will actually give a collision-resistant mechanism. But there are also many, many variants of this, like we saw in the previous puzzle, that are not collision-resistant. So here's another example that's not collision-resistant, and I'm going to leave it as a homework problem to figure out a collision for this construction. So now basically we have all the ingredients to describe the SHA-256 hash function. I'll tell you that it's a Merkle-Damgard construction exactly as the one that we saw before. It uses a Davies-Meyer compression function. And so the only question is, what's the underlying block cipher for Davies-Meyer? And that block cipher is called SHA-2, and I'll just tell you its parameters. It uses a 512-bit key, and remember the key is taken from the message block. So this is really what the message block is. And it so happens to be 512 bits, which means that SHA-256 will process its input message 512 bits at a time. And then the block size for this block cipher is 256 bits, and these are the chaining variables. So this would be hi-1, and this would be a successive chaining variable. So now you have a complete understanding of how SHA-256 works, modulo this block cipher SHA-2 that I'm not going to describe here. So as I said, one class of compression functions is built from block ciphers. It turns out there's another class of compression functions that's built using hard problems for number theory, and I want to very briefly show you one example. And we call these compression functions provable because if you can find a collision on this compression function, then you're going to be able to solve a very hard number theoretic problem, which is believed to be intractable, and as a result, if the number theoretic problem is intractable, the resulting compression function is provably collision resistant. So here's how this compression function works. Basically, we're going to choose a large prime p, so this is a gigantic prime, something like 700 digits, 2,000 bits, and then we're going to choose two random values u and v between 1 and p. And now let's define the compression function as follows. It takes two numbers between 0 and p minus 1, and it's going to output one number between 0 and p minus 1. So its compression ratio is 2 to 1. Yeah, it takes two numbers and outputs one number in the range 0 to p minus 1. And it does it basically by computing this double exponentiation. It computes u to the h times v to the n. And the theorem, which right now I'm just going to state as a fact, this fact actually turns out to be fairly straightforward to prove, and we're going to do it later on when we get to the number theoretic part of the course. The fact is that if you can find a collision for this compression function, then you can solve a standard hard problem in number theory called the discrete log problem. Everyone believes discrete log is hard, and as a result, this compression function is provably collision resistant. So you might ask me, why do people not use this compression function in practice? Why would we not use this for SHA-256? And the answer is that this gives very slow performance in comparison to what you get from a block cipher, so this is not really used for any compression functions. However, if for some reason you really only want to, say, MAC or sign just one long message and you have a whole day to do it, then certainly you can use this type of compression function, and even though it's slow, you'll get something that's provably collision resistant. Okay, so that's the end of this segment, and now we're finally ready to talk about HMAC, which we're going to do in the next segments. So now that we understand what collision-resistant hash functions are and we know how to construct them, we're ready to describe a very popular MAC called HMAC. So let me remind you what the Merkle-Damgard construction is. Basically, we have a small compression function h from which we build a large hash function which is collision-resistant, assuming the compression function is collision-resistant. The question we're going to ask this segment is, can we use the large hash function to construct a MAC directly without having to rely on a PRF? So here's the first thing that comes to mind. Suppose I give you a Merkle-Damgard hash function. So you notice it hashes large messages into small digests. And we want to convert that directly into a MAC. So the first thing that comes to mind is, well, why don't we just hash the concatenation of the MAC key along with the message that we're trying to MAC? And it turns out this is completely insecure. And so let me ask you why this is insecure. The answer is the standard extension attack. And if you think back to the Merkle-Damgard construction, you realize that if I tell you the tag for a particular message, in other words, I tell you the value at this point, it's very easy for the attacker to just add another block and then compute one more application of the compression function h, and now they will be able to get the tag for the original message, concatenated the padding block, concatenated their word w that they added themselves, and as a result, this is an existential forgery. Yeah, so basically this is exactly what we get here, where after concatenating the padding block, the attacker can actually concatenate whatever he wants, and he would get the tag on this combined message. So this is totally insecure, and I cannot tell you how many products have actually made this mistake, where they assume that this is a secure MAC. This is completely insecure and should never, ever, ever be used. Instead, there's a standardized method to convert a collision-resistant hash function into a MAC, and that method is called HMAC. So, in particular, we could use the SHA-256 hash function to build this MAC. The output is going to be 256 bits, and in fact, HMAC is believed to be a pseudo-random function. So, in fact, out of SHA-256, we get a pseudo-random function that outputs 256-bit outputs. So let me show you the construction. Here's the construction in symbols, and it works as follows. First, we take our key k, and we concatenate what's called an internal pad to it, an I-pad to it. This makes it into one block of the Merkle-Damgard construction. So for example, this would be 512 bits in the case of SHA-256. We prepend this to the message m, and then we hash. Now this by itself, we just said, is completely insecure. However, what HMAC does in addition, it takes the output, which is 256 bits, it prepends to that the key again, XORed with what's called the outer pad, the O pad. This also becomes 512 bits. It's one block. And then it hashes the combination of these two to finally obtain the resulting tag on the message M. So it's more, rather than looking at this in symbols, it's more instructive to look at HMAC in pictures. And so you can see here are the two keys, K XOR inner pad, which is then fed into the Merkle-Damgard chain. And then the resulting output of this chain is fed into another Merkle-Damgard chain. And finally, the final output is produced. Okay, so this is how HMAC works in pictures. And now I want to argue that we've already seen something very similar to this. In particular, if you can think of the compression function h as a PRF, where the key is the top input, then what we're actually doing here is we're evaluating this PRF H at a fixed IV, and therefore the result here is a random value which we're going to call K1. And then we apply the Merkle-Damgard chain, and we can do the same thing on the outer pad. If you think of little h as a PRF, where the key is the upper input, again we're applying this PRF using a different key to a fixed value IV, and as a result we're going to get another random value K2. So now when we compute HMAC using these keys K1 and K2, this should actually look very familiar. This is basically NMAC. It's identical to NMAC that we discussed in a previous segment. And notice, to argue that this is an NMAC construction, we have to assume that the compression function little h is a PRF where the key is actually the lower input to the function. Now let me say that these pads, the I pad and the O pad, these are fixed constants that are specified in the HMAC standard. So these are literally just 512-bit constants that never change. And so when we go back to look at the complete HMAC construction, you realize that the main difference between this and NMAC is that these keys here, since they're dependent, you notice they're both just the same key XORed with different constants. Essentially, the keys K1 and K2 are also somewhat dependent because they're computed by applying a PRF to the same fixed value, namely IV, but with dependent keys. And so to argue that K1 and K2 are pseudo-random and independent of one another, one has to argue that the compression function not only is a PRF where when the input, the top input, is the key input, but it's also a PRF when dependent keys are used. But under those assumptions, basically the exact same analysis as NMAC would apply to HMAC, and we would get a security argument that HMAC is a secure MAC. And so as I said, HMAC can be proven secure under these PRF assumptions about the compression function H. The security bounds are just as they are for NMAC. In other words, you should not have to change the key as long as the number of messages you're macking is smaller than the size of the output tag to the 1/2. But for HMAC SHA-256, the output space is 2 to the 256. Square root of that would put us at 2 to the 128, which means that basically you can use HMAC SHA-256 for as many outputs as you want, and you'll always maintain security. And as a last point about HMAC, I'll tell you that TLS standard actually requires that one support HMAC SHA-196, which means HMAC built from the SHA-1 function and truncated to 96 bits. SHA-1, remember, outputs 160 bits, and we truncated to the most significant 96 bits. Now you might be wondering, remember we said before that SHA-1 is no longer considered a secure hash function, so how come we're using SHA-1 in HMAC? Well, it turns out it's actually fine because HMAC, the analysis of HMAC, doesn't need SHA-1 to be collision resistant. All it needs is that the compression function of SHA-1 be a PRF when either input is allowed to be the key. And as far as we know, that's still correct for the underlying compression function for SHA-1. Even though it might not be collision resistant, as far as we know, it's still fine to use it inside of HMAC. So this is the end of our discussion of HMAC, and in the next segment we're going to look at timing attacks on HMAC. In the last segment in this module, I want to show you a general attack that affects many implementations of MAC algorithms, and there's a nice lesson to be learned from an attack like this. So let's look at a particular implementation of HMAC verification. This happens to be an implementation from the Keysar library that happens to be written in Python. So here's the code that's used to verify a tag generated by HMAC. This code is actually simplified. I just wanted to kind of simplify it as much as I can to get the point across. So basically what the inputs are, the key, the message, and the tag bytes. The way we verify it is we recompute the HMAC on the message, and then we compare, say, the resulting 16 bytes to the actual given signature bytes. So this looks perfectly fine. In fact, anyone might implement it like this, and in fact, many people have implemented it like this. The problem is that if you look at how the comparison is done, the comparison, as you might expect, is done byte by byte. There's a loop inside of the Python interpreter that loops over all 16 bytes, and it so happens that the first time it finds an inequality, the loop terminates and says the strings are not equal. And the fact that the comparator exits when the first inequality is found introduces a significant timing attack on this library. So let me show you how one might attack it. So imagine you're the attacker and you have a message M for which you want to obtain a valid tag. Now your goal is to attack a server that has an HMAC secret key stored in it. And the server exposes an interface that basically takes message MAC pairs, checks that the MAC is valid. If the MAC is valid, it does something with the message. And if the MAC is not valid, it says reject. Okay, it sends back to the originator the message reject. So now this attacker has an opportunity to basically submit lots of message tag pairs and see if it can deduce the tag for the particular message for which it wants a tag. And here's how we might use the broken implementation from the previous slide to do just that. So what the attacker is going to do is submit many message tag queries where the message is always the same, but with the tag he's going to experiment with lots and lots and lots of different tags. So in the first query, what he's going to do is just submit a random tag along with the target message. And he's going to measure how long the server took to respond. The next query that he's going to submit is he's going to try all possible first bytes for the tag. So let me explain what I mean by that. So the remaining bytes of the tag that he submits are just arbitrary. It doesn't really matter what they are. But for the first byte, what he'll do is he'll submit a tag starting with the byte 0. And then he's going to see whether the server took a little bit longer to verify the tag than before. If the server took exactly the same amount of time to verify the tag as in step 1, then he's going to try again, this time with byte set to 1. If still the server responded very quickly, he's going to try with a byte set to 2. If the server responded quickly, he's going to try with a byte set to 3, and so on, until finally, let's say when the byte is set to 3, the server takes a little bit longer to respond. What that means is actually when it did the comparison between the correct MAC and the MAC submitted by the attacker, the two matched on this byte, and the rejection happened on the second byte. Aha, so now the attacker knows that the first byte of the tag is set to 3, and now he can mount exactly the same attack on the second byte. So here, it's going to submit a tag with the second byte. Here, let me use a different color. So it's going to submit a tag when the second byte is set to 0, and it's going to measure whether this took a little bit longer than in step 2. If not, he's going to change this to be set to 1, and he's going to measure if the server's response time is a little longer than before. Eventually, let's say when he sets this to, I don't know, when the byte is set to 53, say, all of a sudden the server takes a little bit longer to respond, which means that now the comparator matched on the first 2 bytes, and now the attacker learned that the first 2 bytes of the MAC are 3 and 53, and now he can move on and do the exact same thing on the 3rd byte, and then on the 4th byte, and so on and so forth, until finally the server says, yes, I accept, you actually gave me the right MAC, and then it will go ahead and act on this bogus message that the attacker supplied. So this is a beautiful example of how a timing attack can reveal the value of a MAC, the correct value of the MAC, kind of byte by byte, until eventually the attacker obtains all the correct bytes of the tag, and then he's able to fool the server into accepting this message tag pair. The reason I like this example is this is a perfectly reasonable way of implementing a MAC verification routine, and yet if you write it this way, it'll be completely broken. So what do? So let me show you 2 defenses. The first defense, I'll write it again in Python, is as follows. And in fact, the Keysar library exactly implemented this defense. This code is actually taken out of the updated version of the library. The first thing we do is we test if the signature bytes submitted by the attacker are of the correct length. Say for HMAC, this would be, say, 96 bits or 128 bits. And if not, we reject that as an invalid MAC. But now if the signature bytes really do have the correct length, what we do is we implement our own comparator that always takes the same amount of time to compare the 2 strings. So in particular, this uses the zip function in Python, which will essentially, if you are giving it 2 16-byte strings, it will create 16 pairs of bytes. So it will just create a list of 16 elements where each element is a pair of bytes, one taken from the left and one taken from the right. And then you loop through this list of pairs. You compute the XOR of the first pair and you OR that into the result. Then you compute the XOR of the second pair and you OR that into the result. And you notice that if at any point in this loop 2 bytes happen to be not equal, then the XOR will evaluate to something that's non-zero, and therefore when we OR it into the result will also become non-zero, and then we'll return false at the end of the comparison. So the point here is that now the comparator always takes the same amount of time. Even if it finds a difference in byte number 3, it will continue running down both strings until the very end, and only then will it return the result. So now the timing attack supposedly is impossible. However, this can be quite problematic because compilers try to be too helpful here. So an optimizing compiler might look at this code and say, hey, wait a minute, I can actually improve this code by making the for loop end as soon as an incompatible set of bytes is discovered. And so now optimizing compiler could be your kind of Achilles heel when it comes to making programs always take the same amount of time. And so a different defense, which is not as widely implemented, is to try and hide from the adversary what strings are actually being compared. So let me show you what I mean by that. So again, here we have our verification algorithm. So it takes as inputs a key, a message, and a candidate MAC from the adversary. And then the way we do the comparison is we first of all compute the correct MAC on the message. But then instead of directly comparing the MAC and the signature bytes from the adversary, what we're going to do is we're going to hash one more time. So we compute a hash here of the MAC, we compute a hash of the signature bytes. Of course, if these two happen to be the same, then the resulting HMACs will also be the same, so the comparison will actually succeed. But the point is now, if sig bytes happen to equal MAC on the first byte but not on the remaining bytes, then when we do this additional hash layer, it's likely that the two resulting values are completely different, and as a result, the byte-by-byte comparator will just output on the first iteration. The point here is that the adversary doesn't actually know what strings are being compared, and as a result, he can't mount the timing attack that we discussed earlier. Okay, so this is another defense. At least now you're not at the mercy of an optimizing compiler. The main lesson from all of this is that you realize that people who even are experts at implementing crypto libraries get this stuff wrong. And they write code that works perfectly fine, and yet is completely vulnerable to a timing attack that completely undo all security of the system. So the lesson here is, of course, you should not be inventing your own crypto, but you shouldn't even be implementing your own crypto, because most likely it'll be vulnerable to these side channel attacks. Just use the standard libraries like OpenSSL. Keyzar is actually a fine library to use that would reduce the chances that you're vulnerable to these types of attacks. Now that we're done with message integrity, we're going to go back and talk about encryption, and we're going to show how to construct encryption schemes that provide much stronger security guarantees than what we had before. But first, let's do a recap of where we are. So in previous segments, we talked about confidentiality, in particular, how to encrypt messages such that we achieve semantic security against what's called a chosen plaintext attack. Now, I kept mentioning again and again that security against chosen plaintext attacks only provides security against eavesdropping. In other words, this only provides security against adversaries that listen to network traffic, but don't actually change any packets or don't inject their own packets, and so on. In this module, our goal is actually to design encryption schemes that are secure against adversaries that can tamper with traffic by blocking certain packets and injecting other packets and so on. And then we also looked at how to provide message integrity where the message itself is not confidential. We just want to make sure that the message is not modified while it's en route. And so we talked about message authentication codes, MAC algorithms that provide existential unforgeability against a chosen message attack. In other words, even though the attacker is able to obtain the MACs on arbitrary messages of his choice, he can't build MACs for any other messages. And we looked at a number of MAC constructions, in particular a CBC MAC, HMAC, a parallel MAC construction, and a fast MAC construction called a Carter-Wagman MAC. In this module, we're going to show how to combine these confidentiality and integrity mechanisms to obtain encryption schemes that are secure against a much, much stronger adversary, namely an adversary that can tamper with traffic while it's in the network, inject its own packets, block certain packets, and so on. And our goal is basically to ensure that even against such powerful adversaries, we maintain confidentiality. In other words, the adversary can't learn what the plaintext is, and the adversary can't even modify the ciphertext and cause the recipient to think that a different plaintext was actually sent. So before we do that, I want to give you a few examples of adversaries that can tamper with traffic and as a result completely break security of CPA-secure encryption. This will show you that actually without providing integrity, confidentiality can also be destroyed. In other words, the two must go together, integrity and confidentiality, if we're going to achieve security against active adversaries. So let's look at an example from the world of networking. In particular, let's look at TCP/IP. I'm going to use a highly simplified version of TCP/IP just so we can quickly focus on the attack and not get bogged down by the details. So here we have two machines communicating with one another. A user sits at one machine and the other machine is a server. Now the server, of course, has a TCP/IP stack that's receiving packets, and then based on the destination field in those packets, it forwards the packets to the appropriate place. So here we have, for example, two processes listening to these packets, a web server, say, over here, and another user, we'll call him Bob, over here. The web server listens on port 80, and here this user Bob listens on port 25. Now when a packet comes in, the TCP/IP stack looks at the destination port. In this case it would be destination 80, and as a result the stack forwards the packets over to the web server. If the destination port said port 25, the TCP/IP stack would forward the packet over to Bob, who's listening on port 25. Now a fairly well-known security protocol called IPsec encrypts these IP packets between the sender and the recipient. So here the sender and the recipients basically have a shared key. And when the sender sends IP packets, those IP packets are encrypted using the secret key K. Now, when a packet arrives at the destination, namely it arrives at the server, the TCP/IP stack will go ahead and decrypt the packet, and then look at the destination port and send it to the appropriate place, decrypted. You notice the data here is decrypted, so in this case it would send it to the web server because the destination port is port 80. If the destination port happens to be port 25, the TCP/IP stack will decrypt the packet, look at the destination port, and send the data in the clear to the process who's listening on port 25. So now I want to show you that without integrity, in this setup, we can't possibly achieve any form of confidentiality. And let's see why. So imagine the attacker intercepts a certain packet that's intended for the web server. In other words, it's an encrypted packet intended for port 80. Remember that the attacker can actually receive the decryption of any packets that's intended for port 25 because the TCP stack will happily decrypt packets for port 25 and send them over to Bob, who's listening over here. So what Bob is going to do, Bob here is the attacker, what he's going to do is he's going to intercept this packet en route, prevent the packet from reaching the server as is, and instead he's going to modify the packet. So now the destination port is going to read like port 25. This is done on the ciphertext, and we're going to see how to do that in just a minute. When this packet now arrives at the server, the destination port says 25, the server will decrypt the packet, see that the destination is 25, and forward the data over to Bob. So now Bob was, simply by changing the destination port, Bob was able to read data that was not intended for himself, but rather was intended for the web server. So if the data is encrypted using CBC encryption with a random IV, remember this is a CPA-secure scheme. Nevertheless, if that's the case, I'm going to show you that it's trivial for the attacker to change the ciphertext so that now he can obtain new ciphertext where the destination port is 25 instead of 80. The only thing that's going to change is just the IV field. In fact, everything else is going to remain the same. So let's see how to do it. So here, just remind yourself that in fact, what the attacker captured is a CBC encrypted packet where he knows the destination port is port 80, but he doesn't know what the data is. The attacker has no clue what the data is, but he does know this packet is intended for the web server. His goal is to build a new encrypted packet where now the destination port is port 25. So the way he's going to do it, as we said, is just by changing the IV. And let me remind you that the way you decrypt CBC encrypted data is essentially the first plaintext block is simply decryption of the first ciphertext block XORed with IV. And we know that in the original packet, this is going to read dest equals 80, because in the original packet, the destination port is port 80. So now my question to you is, how would the attacker change the IV so now the destination port will read dest equals 25? So it's pretty easy to see that if the attacker simply takes the original IV, XORs it with here, there are a bunch of zeros over here, and a bunch of zeros over here. He XORs it with the zeros, and then 80 XORs with zeros, and then 25 in the appropriate place, namely in the port bytes in the encrypted packet. Then it's easy to see that when this new IV prime is sent along with the original ciphertext, when the attacker decrypts, you can see that the original ciphertext would decrypt to port 80, but now the new IV will cancel out this 80. This 80 here cancels out the 80 that would be obtained in the original plaintext, and then by XORing with 25, essentially the destination now becomes 25. So this is a nice example where, with a simple change to the IV field, the attacker was able to divert the packet so that now after decryption, the packet goes to the attacker instead of the actual web server. And as a result now, the attacker can read the plaintext data that was intended for the server. So this nice example shows that without integrity, it's simply impossible for a CPA-secure encryption to provide confidentiality when the attacker can modify packets en route. CPA-secure encryption only provides confidentiality if the attacker is only eavesdropping on data but can't actually modify ciphertext en route. Whereas you see, if you can modify ciphertext, a simple modification completely reveals the plaintext. I want to show you another tampering attack that only requires network access to traffic. It doesn't actually require the attacker to be present on the decryption machine. So let's look at an example where there's a remote terminal application where every time the user hits a keystroke, basically an encrypted keystroke is sent over to the server, and let's pretend that the encrypted keystroke is encrypted using counter mode. So here you have the TCP/IP packet. D here corresponds to the 1 byte keystroke, and as we said, it's encrypted using counter mode. And as you probably know, every TCP packet actually contains a checksum. This is a 16-bit checksum that's just used to detect transmission errors. So the server, if it receives a packet that has the wrong checksum, it simply drops it on the floor and ignores it. Now the TCP header, including the checksum and the keystroke, all are encrypted using counter mode. Now the attacker wants to learn what the keystroke was, and let me show you what he can do. The attacker is going to intercept this packet, and he's not actually going to modify it. He's going to send it over to the server, but he's going to record the packet. Later on, he's going to modify the packet and send a modified packet over to the server. What he's going to do is he's going to XOR the encrypted checksum field with a value t, and he's going to XOR the encrypted data field with a value s. And he's going to do this for lots and lots of t's and s's. Now remember, a property of counter mode is that if you XOR the ciphertext with t, after decryption, the resulting plaintext is also XORed with t. Similarly, if you XOR the encrypted data with S, after decryption, the resulting decrypted data will also be encrypted with S. Now, the server is going to decrypt this modified packet, and the resulting packet is going to have the checksum XORed with T and the data XORed with S. Now, what happens? If the modified checksum is correct for this modified packet, the server will send an ACK back. If the modified checksum is incorrect for this modified packet, the server will just drop the packet on the floor and do nothing. So the attacker can simply observe, look for an ACK packet or not, and in doing so, he learns whether this particular XOR of T and XOR of S pairs corresponds to a valid checksum or not. Now the attacker is going to do this for lots and lots of T's and S's, and you notice what he learns is if I modify the data by XORing it with this particular value S, that changes the checksum by a particular value T. And he learns this for lots of T and S pairs. So it turns out for certain checksums, by looking at a sequence of equations of this type, you can actually figure out what the value D is. I should point out that for the TCP checksum, this actually might not be true, but certainly there are easy checksums for which this is actually absolutely true. So again, by looking at a lot of equations of this type, the attacker can recover D. And this is a really nice example of what's called a chosen ciphertext attack. The attacker basically submitted ciphertext of his choice that was derived from the ciphertext that he wanted to decrypt. And then by looking at how the server responded, he was able to learn something about the resulting plaintext. And by repeating this for many different values of T and S, he was actually eventually able to recover what the actual full plaintext is. So in this segment, we're going to look at many more examples of attacks of this type. These are called active attacks, where the attacker is actually modifying traffic en route. And I hope that these two simple examples convinces you that all you provide is CPA security, in other words, security against eavesdropping. You can't even guarantee secrecy against an active attacker. Not only does your ciphertext not have integrity, in other words, the recipient might obtain a message different from the one sent by the sender, but you don't even have confidentiality. And I showed you two examples where, without integrity, the attacker can simply decrypt the packet by using the recipient as an oracle for decrypting certain parts of the data. And so the lesson that I'm going to repeat again and again and again throughout this module is that if your message needs integrity but no confidentiality, just use a MAC. But if your message needs integrity and confidentiality, you have to use what's called an authenticated encryption mode, which is precisely the topic of this module. So the next thing we're going to do is define what authenticated encryption means, and we're going to build authenticated encryption systems. But the point I want you to remember is that the CPA security modes we discussed before should never actually be used to encrypt data by themselves. So CBC with a random IV is a building block towards authenticated encryption, but should never be used on its own. Okay, so we're going to define authenticated encryption in the next segment. In the last segment, we saw two active attacks that can completely destroy the security of CPA-secure encryption. In this segment, we're going to define a new concept called authenticated encryption that remains secure in the presence of an active adversary. In later segments, we'll construct encryption schemes that satisfy this new authenticated encryption concept. So what is authenticated encryption? Authenticated encryption is a cipher where, as usual, the encryption algorithm takes a key, a message, and absolutely a nonce, and outputs a ciphertext. The decryption algorithm, as usual, outputs a message. However, here the decryption algorithm is allowed to output a special symbol called bottom. When the decryption algorithm outputs the symbol bottom, basically it says that the ciphertext is invalid and should be ignored. The only requirement is that this bottom is not in the message space, so that in fact it is a unique symbol that indicates that the ciphertext should be rejected. Now, what does it mean for an authenticated encryption system to be secure? Well, the system has to satisfy two properties. The first property is that it has to be semantically secure under a chosen plaintext attack, just as before. But now there's a second property which says that the system also has to satisfy what's called ciphertext integrity. What that means is that even though the attacker gets to see a number of ciphertexts, it should not be able to produce another ciphertext that decrypts properly. In other words, that decrypts to something other than bottom. More precisely, let's look at the ciphertext integrity game. So here, ED is a cipher with message space M. As usual, the challenger begins by choosing a random key K, and now the adversary can submit messages of his choice and receive the encryptions of those messages. So here, C1 is the encryption of M1, where M1 was chosen by the adversary. And the adversary can do this repeatedly. In other words, he submits M2 and obtains the encryption of M2, and so on and so forth. He submits many more messages up until NQ and obtains the encryptions of all those messages. So here the adversary obtained Q ciphertexts for messages of his choice, and then his goal is to produce some new ciphertext that's valid. So we'll say that the adversary wins the game if basically this new ciphertext that the adversary created decrypts correctly, in other words, decrypts to something other than bottom, and it's a new ciphertext. In other words, it's not one of the ciphertexts that was given to the adversary as part of his chosen plaintext attack. And then, as usual, we define the adversary's advantage in the ciphertext integrity game as the probability that the challenger outputs 1 at the end of the game, and we'll say that the cipher has ciphertext integrity if, in fact, for all efficient adversaries, their advantage in winning this game is negligible. So now that we understand what ciphertext integrity is, we can define authenticated encryption, and basically we say that a cipher has authenticated encryption if, as we said, it's semantically secure under a chosen plaintext attack, and it also has ciphertext integrity. So just as a bad example, let me mention that CBC with a random IV does not provide authenticated encryption because it's very easy for the adversary to win the ciphertext integrity game. The adversary simply submits a random ciphertext, and since the decryption algorithm for CBC encryption never outputs bottom, it always outputs some message, the adversary just easily wins the game. Any old random ciphertext will decrypt to something other than bottom, and therefore the adversary directly wins the ciphertext integrity game. So this is just a trivial example of a CPA-secure cipher that does not provide authenticated encryption. So I want to mention two implications of authenticated encryption. The first I'll call authenticity, which means that basically an attacker cannot fool the recipient Bob into thinking that Alice sent a certain message that she didn't actually send. So let's see what I mean by that. Well, here the attacker basically gets to interact with Alice and get her to encrypt arbitrary messages of his choice. So this is a chosen plaintext attack. And then the attacker's goal is to produce some ciphertext that was not actually created by Alice. And because the attacker can't win the ciphertext integrity game, he can't do this. And what this means is, when Bob receives a ciphertext that decrypts correctly under the decryption algorithm, he knows that the message must have come from someone who knows the secret key K. In particular, if Alice is the only one who knows K, then he knows the ciphertext really did come from Alice, and it's not some modification that was sent by the attacker. Now, the only caveat to that is that authenticated encryption doesn't defend against replay attacks. In particular, the attacker could have intercepted some ciphertext from Alice to Bob and could have replayed it, and both ciphertexts would look valid to Bob. So for example, Alice might send a message to Bob saying, transfer $100 to Charlie. Then Charlie could replay that ciphertext, and as a result, Bob would transfer another $100 to Charlie. So in fact, any encryption protocol has to defend against replay attacks, and this is not something that's directly prevented by authenticated encryption. And we'll come back and talk about replay attacks in 2 segments. The second implication of authenticated encryption is that it defends against a very powerful type of adversary, namely an adversary that can mount what's called a chosen ciphertext attack. And we're going to talk about that actually in the next segment. In the last segment, we defined authenticated encryption, but I didn't really show you why authenticated encryption is the right notion of security. In this segment, I want to show you that authenticated encryption, in fact, is a very natural notion of security, and I'll do it by showing you that it defends against a very powerful attack called a chosen ciphertext attack. So in fact, we already saw a number of examples of a chosen ciphertext attack. So imagine the adversary has some ciphertext C that it wants to decrypt. And what it can do is, for example, fool the decryption server into decrypting some ciphertext, but not actually the ciphertext C. So we already saw some examples of that. If you remember in the first segment, we looked at an adversary that can submit arbitrary ciphertext, and if the plaintext happened to start with destination equals 25, then the adversary is actually given the plaintext in the clear. So that's an example of an adversary that can obtain the decryption of certain ciphertexts, but not all ciphertexts. Another example we saw is an adversary that can learn something about the plaintext by submitting ciphertexts to the decryptor. So we had this example where the adversary submits encrypted TCP/IP packets to the decryption server, and if the decryption server sends back an ACK, the adversary learns that the decrypted plaintext had a valid checksum. And otherwise, the decrypted plaintext didn't have a valid checksum. So this is again an example of a chosen ciphertext attack where the attacker submits ciphertext and learns something about the decryption of that ciphertext. So to address this type of threat, we're going to define a very general notion of security called chosen ciphertext security. So here we're going to give the adversary a lot of power. Okay, so he can do both chosen plaintext attack and a chosen ciphertext attack. In other words, he can obtain the encryption of arbitrary messages of his choice, and he can decrypt any ciphertext of his choice other than some challenged ciphertext. And as I showed you before, this is actually a fairly conservative modeling of real life. In real life, often the attacker can fool the decryptor into decrypting certain ciphertext for the attacker, but not all ciphertexts. So the model here is that the attacker has a certain ciphertext that it wants to decrypt. It can interact with the decryptor by issuing these chosen ciphertext queries to the decryptor, namely to decrypt various ciphertext other than the challenged ciphertext. And then the adversary's goal is to break semantic security of the challenged ciphertext. So you notice that we're giving the adversary a lot of power, and all we're asking him to do is break semantic security. So it's going to be fairly difficult to design systems that are secure against such adversaries, and nevertheless we're going to do it. So let's define the chosen ciphertext security model more precisely. So as usual, we have a cipher ED, and we're going to define 2 experiments, experiment 0 and experiment 1. So this should look somewhat familiar by now. The challenger is going to start off by choosing a random key, and now the adversary is going to submit queries to this challenger. Every query can be one of 2 types. It can be a chosen plaintext query, or it can be a chosen ciphertext query. So chosen plaintext queries, we already know, basically the adversary submits 2 messages, M0 and M1. They have to be the same length, and the adversary receives the encryption of either M0 if we're in experiment 0, or M1 if we're in experiment 1. So he receives the encryption of the left or the right, depending on whether we're in experiment 0 or in experiment 1. The second type of query is the more interesting one. This is where the adversary submits an arbitrary ciphertext of his choice, and what he gets back is the decryption of that ciphertext. So you notice the adversary is allowed to decrypt arbitrary ciphertext of his choice. The only restriction is that the ciphertext is not one of the ciphertexts that were obtained as a result of a CPA query. And of course, this wouldn't be fair otherwise, because the attacker can simply take one ciphertext that was obtained from a CPA query. That's going to be either the encryption of M0 or the encryption of M1. If he could submit a CCA query for that particular ciphertext, he will, in response, either obtain M0 or M1, and then he'll know whether he's in experiment 0 or in experiment 1. So this wouldn't be fair, so we say that these CPA ciphertexts that he received are the challenged ciphertexts, and he's allowed to decrypt any ciphertext of his choice other than these challenged ciphertexts. And as usual, his goal is to determine whether he's in experiment 0 or in experiment 1. So I'm going to emphasize again that this is an extremely powerful adversary. one that can decrypt any ciphertext of his choice other than the challenge ciphertext, and still he can't distinguish whether he's in experiment 0 or in experiment 1. So as usual, we say that the cipher is CPA-secure, chosen ciphertext secure, if the adversary behaves the same in experiment 0 as it does in experiment 1, namely cannot distinguish the two experiments. So let's start with a simple example and show that in fact CBC with a random IV is not CPA-secure, is not secure against chosen ciphertext attacks. So let's see why that's the case. So what the adversary is going to start by doing, he's going to simply submit two distinct messages, M0 and M1, and let's just pretend that these messages are one block messages. And what he's going to get back is the CBC encryption of either M0 or M1. You notice the ciphertext only has one block because the plaintext were only one block long. Now what is the attacker going to do? Well, he's going to modify the ciphertext C that he was given into C prime simply by changing the IV. Okay, so he just takes the IV and XORs it with 1. That's it. This gives a new ciphertext, C prime, which is different from C, and as a result, it's perfectly valid for the adversary to submit C prime as a chosen ciphertext query. So he asks the challenger, please decrypt this C prime for me. The challenger, because C prime is not equal to C, must decrypt C prime. And now let's see, what happens when he decrypts C prime? Well, what's the decryption of C prime? Let me ask you. So you probably remember from the first segment that if we XOR the IV by 1, that simply XORs the plaintext by 1. So now the adversary received M0 XOR 1 or M1 XOR 1, and now he can perfectly tell whether he's in experiment 0 or in experiment 1. So the advantage of this adversary is basically 1, because he can very easily tell which experiment he's in, and as a result he can win the chosen ciphertext security game. So if you think about it for a second, you'll see that this attack game exactly captured the first active attack that we saw, where the adversary slightly changed the ciphertext that he was given, and then he got the decryptor to decrypt it for him, and therefore he was able to eavesdrop on messages that were not intended for the adversary. So I want to emphasize again that this chosen ciphertext game really does come up in real life, where the adversary can submit ciphertext to the decryptor, and the decryptor can reveal information about the plaintext, or can give the plaintext outright to the adversary for certain ciphertext, but not others. So this is a very natural notion of security, and the question is, how do we design crypto systems that are CCA secure? So I claim that this authenticated encryption notion that we defined before actually implies chosen ciphertext security, and this is why authenticated encryption is such a natural concept. Okay, so the theorem basically says, well, if you give me a cipher that provides authenticated encryption, the cipher can withstand chosen ciphertext attacks. And more precisely, the theorem says the following: if we have an adversary that issues Q queries, in other words, at most Q CPA queries and Q chosen ciphertext queries, then there are two efficient adversaries, B1 and B2, that satisfy this inequality here. So since the scheme has authenticated encryption, we know that this quantity is negligible because it's CPA secure, and we know that this quantity is negligible because the encryption scheme has ciphertext integrity. And as a result, since both terms are negligible, we know that adversary's advantage in winning the CCA game is also negligible. So let's prove this theorem. It's actually a very simple theorem to prove. And so let's just do it as proof by pictures. Okay, so here we have two copies of the CCA game. So this would be experiment 0, and the bottom one is experiment 1. You can see the adversary is issuing CPA queries, and he's issuing CCA queries, and at the end he outputs, a certain guess B, let's call it B prime, and our goal is to show that this B prime is indistinguishable in both cases. In other words, the probability that B prime is equal to 1 in the top game is the same as the probability that B prime is equal to 1 in the bottom game. Okay, so the way we're going to do it is the following. Well, first of all, we're going to change the challenger a little bit so that instead of actually outputting the decryption of CCA queries, the challenger is just going to always output bottom. So every time the adversary submits a CCA query, the challenger says bottom. And I claim that these two games are in fact indistinguishable. In other words, the adversary can't distinguish these two games for the simple reason that because the scheme has ciphertext integrity, the adversary simply cannot create a ciphertext that's not in C1 to Ci-1 that decrypts to anything other than bottom. That is the definition of ciphertext integrity. And as a result, again, because of ciphertext integrity, it must be the case that every chosen ciphertext query that the adversary issues results in bottom. If the adversary in fact could distinguish between the left game and the right game, that would mean that at some point he issued a query that decrypted to something other than bottom, and that we could use to then break ciphertext integrity of the scheme. And since the scheme has ciphertext integrity, these left and right games are indistinguishable. Okay, so that's kind of a cute argument that shows that it's very easy to respond to chosen ciphertext queries when you have ciphertext integrity. And the same thing exactly applies on the bottom, where we can simply replace the chosen ciphertext responses by just always saying bottom. Okay, very good. But now, since the chosen ciphertext queries always respond in the same way, they're not giving the adversary any information. The adversary always knows that we're always going to just respond with bottom. So we might as well just remove these queries, because they don't contribute any information to the adversary. But now, once we remove these queries, the resulting game should look fairly familiar. The top right game and the top bottom game are basically the two games that come up in the definition of CPA security. And as a result, because the scheme is CPA secure, we know that the adversary can't distinguish the top from the bottom. And so now, by this chain of reasoning, we've proven that all these games are equivalent, and in particular, the original two games that we started with are also equivalent, and therefore, the adversary can't distinguish the top left from the bottom left, and therefore, the scheme is CCA secure. So this gives you the intuition as to why authenticated encryption is such a cool concept, because primarily it implies security against chosen ciphertext attacks. Okay, so as we said, authenticated encryption ensures confidentiality, even if the adversary can decrypt a subset of the ciphertext, and more generally, even if he can mount a general chosen ciphertext attack, he still is not going to be able to break semantic security of the system. However, it is important to remember the two limitations. First of all, it does not prevent replay attacks on its own. We're going to have to do something in addition to defend against replay attacks. We're going to see several examples where if the decryption engine reveals more information about why a ciphertext is rejected, it doesn't just output bottom, but it actually outputs more information, say by timing attacks, and that explains why the ciphertext is rejected, then in fact that can completely destroy security of the authenticated encryption system. So we'll see some cute attacks like this in a later segment. Okay, so in the next segment we're going to turn to constructing authenticated encryption systems. In this segment, we're going to construct authenticated encryption systems. Since we already have CPA-secure encryption and we have secure MACs, the natural question is whether we can combine the two somehow in order to get authenticated encryption. And that's exactly what we're going to do in this segment. Authenticated encryption was introduced in the year 2000 in two independent papers that I point to at the end of this module. But before then, many crypto libraries provided an API that separately supported CPA-secure encryption and MACing. So there was one function for implementing CPA-secure encryption, for example, CBC with a random IV, and another function for implementing a MAC. And then every developer that wanted to implement encryption had to himself call separately the CPA-secure encryption scheme and the MAC scheme. In particular, every developer had to invent his own way of combining encryption and MACing to provide some sort of authenticated encryption. But since the goals of combining encryption and MACing wasn't well understood, since authenticated encryption hasn't yet been defined, it wasn't really clear which combinations of encryption and MACing are correct and which aren't. And so every project, as I said, had to invent its own combination, and in fact not all combinations were correct. And I can tell you that the most common mistake in software projects were basically incorrectly combining the encryption and integrity mechanisms. So hopefully by the end of this module, you will know how to combine them correctly and you won't be making these mistakes yourself. So let's look at some combinations of CPA-secure encryption and MAC that were introduced by different projects. So here are three examples. So first of all, in all three examples, there's a separate key for encryption and a separate key for MACing. These two keys are independent of one another and both are generated at session setup time. And we're going to see how to generate these two keys later on in the course. So the first example is the SSL protocol. So the way SSL combines encryption and MAC in the hope of achieving authenticated encryption is the following. Basically, you take the plaintext M, and then you compute a MAC on the plaintext M. So you use your MAC key, KI, to compute tag for this message M. And then you concatenate the tag to the message, and then you encrypt the concatenation of the message and the tag. And what comes out is the actual final ciphertext. So that's option number one. The second option is what IPsec does. So here you take the message. The first thing you do is you encrypt the message, and then you compute a tag on the resulting ciphertext. So you notice the tag itself is computed on the resulting ciphertext. The third option is what the SSH protocol does. So here the SSH takes the message and encrypts it using a CPA-secure encryption scheme. And then to it, it concatenates a tag of the message. The difference between IPsec and SSH is that in IPsec, the tag is computed over the ciphertext, whereas in SSH, the tag is computed over the message. And so these are three completely different ways of combining encryption and MAC. And the question is, which one of these is secure? So I will let you think about this for a second, and then when we continue, we'll do the analysis together. Okay, so let's start with the SSH method. So in the SSH method, you notice that the tag is computed on the message and then concatenated in the clear to the ciphertext. Now, this is actually quite a problem because MACs themselves are not designed to provide confidentiality. MACs are only designed for integrity. And in fact, there's nothing wrong with a MAC that as part of the tag outputs a few bits of the plaintext, outputs a few bits of the message M. That would be a perfectly fine tag. And yet, if we did that, that would completely break CPA security here because some bits of the message are leaked in the ciphertext. And so the SSH approach, even though the specifics of SSH are fine and the protocol itself is not compromised by the specific combination, generally it's advisable not to use this approach simply because the output of the MAC signing algorithm might leak bits of the message. So now let's look at SSL and IPsec. As it turns out, the recommended method actually is the IPsec method because it turns out no matter what CPA secure system and MAC key you use, the combination is always going to provide authenticated encryption. Now let me very briefly explain why. Basically what happens is once we encrypt the message, well, the message contents now is hidden inside the ciphertext. And now when we compute a tag of the ciphertext, basically we're locking, this tag locks the ciphertext and makes sure no one can produce a different ciphertext that would look valid. And as a result, this approach ensures that any modifications to the ciphertext will be detected by the decryptor simply because the MAC isn't going to verify. As it turns out, for the SSL approach, there actually are kind of pathological examples where you combine a CPA-secure encryption system with a secure MAC, and the result is vulnerable to a chosen ciphertext attack, so that it does not actually provide authenticated encryption. And basically the reason that could happen is that there's some sort of bad interaction between the encryption scheme and the MAC algorithm, such that, in fact, there will be a chosen ciphertext attack. So if you're designing a new project, the recommendation now is to always use encrypt then MAC, because that is secure no matter which CPA secure encryption and secure MAC algorithm you're combining. Now, just to set the terminology, the SSL method is sometimes called MAC then encrypt, and the IPsec method is called encrypt then MAC. The SSH method, even though you're not supposed to use it, is called encrypt and MAC. Okay, so I'll often refer to encrypt then MAC and MAC then encrypt to differentiate SSL and IPsec. Okay, so just to repeat what I've just said, the IPsec method, encrypt then MAC, always provides authenticated encryption. If you start from a CPA secure cipher and a secure MAC, you will always get authenticated encryption. As I said, MAC then encrypt, in fact, there are pathological cases where the result is vulnerable to CCA attacks and therefore does not provide authenticated encryption. However, the story is a little bit more interesting than that, in that it turns out if you're actually using randomized counter mode or randomized CBC, then it turns out for those particular CPA secure encryption schemes, MAC then encrypt actually does provide authenticated encryption and therefore it is secure. In fact, there's even a more interesting twist here in that if you're using randomized counter mode, then it's enough that your MAC algorithm just be one time secure. It doesn't have to be a fully secure MAC, it just has to be secure when a key is used to encrypt a single message. Okay, and when we talked about message integrity, we saw that there are actually much faster MACs that are one time secure than MACs that are fully secure. As a result, if you're using randomized counter mode, MAC then encrypt could actually result in a more efficient encryption mechanism. However, I'm going to repeat this again. The recommendation is to use encrypt then MAC, and we're going to see a number of attacks on systems that didn't use encrypt then MAC. And so just to make sure things are secure without you having to think too hard about this, again, I'm going to recommend that you always use encrypt then MAC. Now, once the concept of authenticated encryption became more popular, a number of standardized approaches for combining encryption and MAC turned up, and those were even standardized by the National Institute of Standards. So I'm just going to mention 3 of these standards. 2 of these were standardized by NIST, and these are called Galois counter mode and CBC counter mode. And so let me explain what they do. Galois counter mode basically uses counter mode encryption, so randomized counter mode, with a Carter-Wagman MAC, so a very fast Carter-Wagman MAC. The way the Carter-Wagman MAC works in GCM is it's basically a hash function of the message that's being MAC'd, and then the result is encrypted using a PRF. Now, this hash function in GCM is already quite fast, to the point where the bulk of the running time of GCM is dominated by the counter mode encryption. And it's even made more so in that Intel introduced a special instruction, PCLM-UL-QDQ, specifically designed for the purpose of making the hash function in GCM run as fast as possible. Now, CCM counter mode is another NIST standard. It uses a CBC MAC and then counter mode encryption. So this mechanism, you notice, uses MAC then encrypt like SSL does. So this is actually not the recommended way of doing things, but because counter mode encryption is used, this is actually a perfectly fine encryption mechanism. One thing that I'd like to point out about CCM is that everything is based on AES. You notice it's using AES for the CBC MAC, and it's using AES for the counter mode encryption. And as a result, CCM can be implemented with relatively little code, because all you need is an AES engine and nothing else. And because of this, CCM actually was adopted by the Wi-Fi Alliance, and in fact, you're probably using CCM on a daily basis. If you're using encrypted Wi-Fi 802.11i, then you're basically using CCM to encrypt traffic between your laptop and the access point. There's another mode called EAX that uses counter mode encryption and then CMAC. So again, you notice encrypt then MAC, and that's another fine mode to use. We'll do a comparison of all these modes in just a minute. Now, I wanted to mention that first of all these modes are nonce-based. In other words, they don't use any randomness, but they do take as input a nonce, and the nonce has to be unique per key. In other words, as you remember, the pair key comma nonce should never ever ever repeat, but the nonce itself need not be random, so it's perfectly fine to use a counter, for example, as a nonce. And the other important point is that in fact all these modes are what's called authenticated encryption with associated data. This is an extension of authenticated encryption that comes up very often in networking protocols. So the idea behind AEAD is that in fact the message that's provided to the encryption mode is not intended to be fully encrypted. Only part of the message is intended to be encrypted, but all of the message is intended to be authenticated. A good example of this is a network packet. Think of like an IP packet, where there's a header, and then there's a payload. And typically the header is not going to be encrypted. For example, the header might contain the destination of the packet, but then the header had better not be encrypted, otherwise routers along the way wouldn't know where to route the packet. And so typically the header is sent in the clear. The payload, of course, is always encrypted. But what you'd like to do is have the header be authenticated, not encrypted, but authenticated. So this is exactly what these AEAD modes do. They would authenticate the header and then encrypt the payload, but the header and the payload are bound together in the authentication, so they can't actually be separated. So this is not difficult to do. What happens is in these 3 modes, GCM, CCM, and EAX, basically the MAC is applied to the entire data, but the encryption is only applied to the part of the data that needs to be encrypted. So I wanted to show you what an API to these authenticated encryption with associated data encryption schemes look like. So here's what it looks like in OpenSSL. For example, just as an API for GCM. So what you do is you call the init function to initialize the encryption mode, and you notice you give it a key and the nonce. The nonce, again, doesn't have to be random, but it has to be unique. And after initialization, you would call this encrypt function, where you see that you give it the associated data that's going to be authenticated but not encrypted. You give it a data that's going to be both authenticated and encrypted, and it gives you back the full ciphertext, which is an encryption of the data, but of course does not include the AAD, because the AAD is going to be sent in the clear. So now that we understand this mode of encrypt then MAC, we can go back to the definition of MAC security, and I can explain to you something that might have been a little obscure when we looked at that definition. So if you remember, one of the requirements that followed from our definition of secure MACs meant that given a message MAC pair on a message M, the attacker cannot produce another tag on the same message M. In other words, even though the attacker already has a tag for the message M, he shouldn't be able to produce a new tag for the same message M. And it's really not clear, why does that matter? Who cares if the adversary already has a tag on the message M? Who cares if he can produce another tag? Well, it turns out if the MAC didn't have this property, in other words, given a message MAC pair, you can produce another MAC on the same message, then that MAC would result in an insecure encrypt then MAC mode. And so if we want our encrypt then MAC to have ciphertext integrity, it's crucial that our MAC security would imply this strong notion of security, which of course it does because we defined it correctly. So let's see what would go wrong if in fact it was easy to produce this type of forgery. So what I'll do is I'll show you a chosen ciphertext attack on the resulting encrypt then MAC system. And since the system has a chosen ciphertext attack on it, it necessarily means that it doesn't provide authenticated encryption. So let's see. So the adversary is going to start by sending two messages, M0 and M1. And he's going to receive, as usual, the encryption of one of them, either the encryption of M0 or the encryption of M1. And since we're using encrypt then MAC, the adversary receives a ciphertext, we'll call it C0, and a MAC on the ciphertext C0. Well, now we said that given the MAC on a message, the adversary can produce another MAC on the same message. So what he's going to do is he's going to produce another MAC on the message C0. Now he has a new ciphertext, C0, comma T prime, which is a perfectly valid ciphertext. T prime is a valid MAC of C0. Therefore, the adversary now can submit a chosen ciphertext query on C prime, and this is a valid chosen ciphertext query because it's different from C. It's a new ciphertext. The poor challenger now is forced to decrypt this ciphertext C prime, so he's going to send back the decryption of C prime. It's a valid ciphertext, therefore the decryption of C prime is the message MB, but now the attacker just learned the value of B because he can test whether MB is equal to M0 or MB is equal to M1. As a result, he can just output B and he gets advantage 1 in defeating the scheme. And so again, if our MAC security did not imply this property here, then there would be a chosen ciphertext attack on encrypt and MAC, and therefore it would not be secure. So the fact that we defined MAC security correctly means that encrypt and MAC really does provide authenticated encryption. And throughout all the MACs that we discussed actually do satisfy this strong notion of unforgeability. So interestingly, this is not the end of the story. So as we said before the concept of authenticated encryption was introduced, everyone was just combining MACs and encryption in various ways in the hope of achieving some authenticated encryption. After the notion of authenticated encryption became formalized and rigorous, people kind of started scratching their heads and said, hey, wait a minute, maybe we can achieve authenticated encryption more efficiently than by combining a MAC and an encryption scheme. In fact, if you think about how this combination of MAC and encryption works, let's say we combine counter mode with CMAC, then for every block of plaintext, you first of all have to use your block cipher for counter mode, and then you have to use your block cipher again for the CBCMAC. This means that if you're combining CPA-secure encryption with a MAC, for every block of plaintext, you have to evaluate your block cipher twice, once for the MAC and once for the encryption scheme. So the natural question was, can we construct an authenticated encryption scheme directly from a PRP such that we would have to only evaluate the PRP once per block? And it turns out the answer is yes, and there's this beautiful construction called OCB that pretty much does everything you want and is much faster than constructions that are separately built from an encryption and a MAC. So I wrote down kind of a schematic of OCB. I don't want to explain it in detail. I'll just kind of explain it at a high level. So here we have our input plaintext here at the top. And you notice that first of all, OCB is parallelizable, completely parallelizable. So every block can be encrypted separately of every other block. The other thing to notice is that, as I promised, you only evaluate your block cipher once per plaintext block. And then you evaluate it one more time at the end to build your authentication tag. And then the overhead of OCB beyond just a block cipher is minimal. All you have to do is evaluate a certain very simple function P. The nonce goes into this P, you notice. The key goes into this P. And then there's a block counter that goes into this P. So you just evaluate this function P twice for every block, and you XOR the result before and after encryption using the block cipher. And that's it. That's all you have to do. And then you get a very fast and efficient authenticated encryption scheme built from a block cipher. So OCB actually has a nice security theorem associated with it, and I'm going to point to a paper on OCB when we get to the end of this module where I list some further reading papers that you can take a look at. So you might be wondering, if OCB is so much better than everything we've seen so far, all these three standards, CCM, GCM, and EAX, why isn't OCB being used, or why isn't OCB the standard? And the answer is a little sad. The primary answer that OCB is not being used is actually because of various patents. And I'll just leave it at that. So to conclude this section, I wanted to show you some performance numbers. So here on the right, I listed performance numbers for modes that you shouldn't be using. So this is for randomized counter modes, and this is for randomized CBC. And you can see also the performance of CBC-MAC is basically the same as the performance of CBC encryption. Okay, now here are the authenticated encryption modes. So these are the ones that you're supposed to be using. These you're not supposed to be using on their own, right? These two, you should never ever use these two because they only provide CPA security. They don't actually provide security against active attacks. You're only supposed to use authenticated encryption for encryption. And so I listed performance numbers for the three standards. Let me remind you that GCM basically uses a very fast hash, and then it uses counter mode for actual encryption, and you can see that the overhead of GCM over counter mode is relatively small. CCM and EAX both use a block cipher based encryption and block cipher based MAC, and as a result they're about twice as slow as counter mode. And you see that OCB is actually the fastest of these, primarily because it only uses the block cipher once per message block. So based on these performance numbers, you would think that GCM is exactly the right mode to always use. But it turns out if you're on the space-constrained hardware, GCM is not ideal, primarily because its implementation requires larger code than the other two modes. However, as I said, Intel specifically added instructions to speed up GCM mode, and as a result, implementing GCM on an Intel architecture takes very little code. But on other hardware platforms, say in smart cards or other constrained environments, the code size for implementing GCM would be considerably larger than for the other two modes. But if code size is not a constraint, then GCM is the right mode to use. So to summarize this segment, I want to say it one more time, that when you want to encrypt messages, you have to use an authenticated encryption mode. And the recommended way to do it is to use one of the standards, namely one of these three modes for providing authenticated encryption. Don't implement the encryption scheme yourself. In other words, don't implement encrypt and MAC yourself. Just use one of these three standards. Many crypto libraries now provide standard APIs for these three modes, and these are the ones you should be using and nothing else. In the next segment, we're going to see what else can go wrong when you try to implement authenticated encryption by yourself. So I want to show you how authenticated encryption is used in the real world. So let's use TLS as an example and see how TLS works. So data encryption in TLS is done using a protocol called the TLS record protocol. In this protocol, every TLS record starts with a header. We'll see the structure of the header in just a minute, followed by encrypted data that is sent from one side to the other. In TLS, it so happens that the records are at most 16 kilobytes, and if more data than 16 kilobytes needs to be sent, then basically the record is fragmented into multiple records. Now, TLS uses what's called unidirectional keys, meaning that there's one key from browser to server, and there's a separate key from server to browser. So one key is used for sending messages from a browser to the server, and the other key is used from sending messages from the server to the browser. And of course, both sides, both the server and the browser, know both of these keys. And just to be clear, I'll say the browser will use this key to send data to the server, and will use this key to read data from the server. And the server basically does exactly the same thing, just with the opposite keys. Now these keys, both of these keys, are actually generated by the TLS key exchange protocol, which we're going to talk about in the second part of the course. Right now, I'm going to assume that these keys have already been established. They're known to both the server and the browser, and now the browser and server want to exchange information using those keys. So the TLS record protocol uses what's called stateful encryption, which means that the encryption of every packet is done using a certain state that's maintained inside of the browser and the server. In particular, the state that's of interest to us are these 64-bit counters. Again, there are two 64-bit counters, one for traffic from browser to server, and one from traffic from the server to the browser. These counters are initialized to 0 when the session is first initialized, and they're incremented every time a record is sent. So every time the browser sends a record to the server will go ahead and increment this counter. When the server receives that record, it'll go ahead and increment the counter on its side. And when the server sends a record to the browser, it'll go ahead and increment the second counter. And again, when the browser receives this record, it'll go ahead and increment its copy of this counter. So the state, these two counters, basically the state exists both on the browser and on the server, and it's updated appropriately as records are sent from one to the other and received by the appropriate side. Now, the purpose of these counters, as we'll see in just a minute, is to prevent replay attacks, so that an attacker can't simply record a record and then replay it at a later time, because by then the counters would have to be incremented. Okay, so let's look at the details of how the record protocol works. In particular, I'll show you kind of the mandatory cipher suite, which is encryption using AES-CBC and MACing using HMAC SHA-1. Okay, so remember, TLS uses MAC then encrypt, where the MAC algorithm is HMAC SHA-1 and the encryption algorithm is AES-128 in CBC mode. Okay, so let's look at how the browser sends data to the server, which, as I said, is done using the browser to server key. Now, the browser to server key itself is made up of a MAC key and an encryption key. Two separate keys that are, again, as I said, negotiated during session setup. And again, I want to be absolutely clear, there is a separate key for browser to server and a separate key from server to browser, so that overall there are 4 keys, 2 MAC keys and 2 encryption keys, each one used in the appropriate direction. Okay, so here I wrote down the diagram of what a TLS packet looks like. It begins with a header that contains the type of the packet, the version number for the protocol, and the length of the packet. Notice the length of the packet is sent in the clear. Now, when encrypting data, a certain record, the encryption procedure works as follows. Of course, it takes key as input, and it takes the current state as input, and then it works as follows. What it would do is, first of all, is it would MAC the following data. Well, here is the actual payload that's MAC'd, but the header is also MAC'd. And in addition, the counter, the current value of the counter is also MAC'd, and of course, it's all the counter is incremented to indicate the fact that one more record has been sent. Now, the interesting thing here is that even though the value of the counter is included in the tag, you notice the value of the counter is actually never sent in the record. And the reason it doesn't need to be sent in the record is that the server on the other side already knows what the value of the counter needs to be. So it doesn't need to be told in the record what the value of the counter is. It implicitly already knows what it is. And when it's going to verify the MAC, it could just use the value that it thinks the counter should be and verify the MAC in that fashion. Okay, so this is kind of an interesting approach where even though the two sides maintain these counters that function as nonces, there's no reason to send the nonces in the record because both sides actually already know what counters to expect in every record that they receive. Okay, so that's the tag. The tag is computed, as we said, over this triple of data. The next thing that happens is that the tag is concatenated to the data. Remember, this is MAC, then encrypt. So here we computed the MAC. Now we're going to encrypt the data along with the tag. So the header, the data, and the tag are padded to the AES block, and I think we already said that this pad, if the pad length is 5, then the pad is done by simply writing the byte 5 times. So if the pad length needs to be 5, the pad would just be 55555. And then we CBC encrypt using the encryption key. We CBC encrypt the data and the tag, and we do that using a fresh random IV, which is later embedded in the ciphertext. And then we prepend the header, the type, the version, and the length, and that gives us the entire TLS record, which is then sent over to the server. So the grayed out fields in this diagram correspond to encrypted data, and the white fields correspond to plaintext data. So you can see that this is TLS's implementation of MAC then encrypt. The only difference from basic MAC then encrypt is the fact that there is a state, namely this counter is being included in the value of the MAC. And again, as I said, that's done to prevent replays. So let's see why that prevents replays. In particular, let's see how the record protocol decrypts an incoming record. So here comes an incoming encrypted record. And again, the server is going to use its own key that it corresponds to data from browser to server and its own browser to server counter. And the first thing it's going to do is it's going to decrypt the record using the encryption key. After encryption, it's going to check the format of the pad. In other words, if the pad length is 5 bytes, it's going to check that it really is 55555. And if it's not, it's going to send a bad record MAC alert message and terminate the connection so that a new session key would have to be negotiated if more records need to be sent. If the pad format is correct, then removing the pad is really easy. All the server does is it looks at the last byte of the pad, say the last byte is equal to 5, and then it removes the last 5 bytes of the record. By doing that, it strips off the pad. The next thing it's going to do is it's going to extract the tag from the record. So this would be the subsequent bytes inside of the record. So this would be the trailing bytes in the record after we remove the pad. And then it's going to verify the tag on the header, the data, and its value of the counter. And if the MAC doesn't verify, again, it's going to send an alert, bad record MAC, and tear down the connection. And if the pad does verify, it's going to remove the tag, remove the header, and the remaining part of the record is the plaintext data that's given to the application. Now you can see that if a record is ever replayed, in other words, if an attacker records a particular record and then replays it to the server at a later time, then by then the value of the counter would have changed, and as a result, the tag on the replayed record would simply not verify because the tag was computed using one value of the counter, but when the replayed record is received at the server, the value of the counter at the server is different from the value that was used to compute the tag, and as a result, the tag would not verify. So these counters are a very elegant and simple way for preventing replays. And the nice thing about this is because both sides know the value of the counter implicitly, there's never a need to send the counter in the record itself. So the counter itself doesn't increase the length of the ciphertext at all. Now, we already mentioned that this particular approach to authenticated encryption, namely MAC then encrypt using CBC encryption, is in fact authenticated encryption. However, it's only authenticated encryption if no other information is leaked during decryption. And we're going to see some cute attacks on TLS if there is information being leaked during decryption. I should say that this bad record MAC alert basically corresponds to the decryption algorithm outputting this reject symbol, the bottom symbol, meaning that the ciphertext is invalid. And as long as there's no way to differentiate between why the ciphertext was rejected, in other words, the decryptor only exposes the fact that a rejection took place, but it doesn't say why the rejection happened, this is in fact an authenticated encryption system. However, if you differentiate and expose why the ciphertext was rejected, whether it was because of a bad pad or because of a bad MAC, then it turns out there's a very cute attack, which we're going to see in the next segment. What I showed you so far is called TLS version 1.1. It turns out that earlier versions of TLS actually had significant mistakes in it, and as a result, the earlier record protocol is vulnerable to a number of attacks. The first mistake is that the IV used in CBC encryption is predictable. And we said earlier that in CBC, if the IV is predictable, then the resulting CBC encryption is not CPA-secure. Well, in this older version of TLS, TLS 1.0 and earlier, the IV for the next record is simply the last ciphertext block of the current record. And as a result, if the adversary can observe the current record, he knows the IV for the next record, and that will allow him to break semantic security of the next record. So the resulting scheme is not CPA secure, but not only is it not CPA secure, in fact there's a very cute attack called the Beast attack that's able to decrypt the initial part of a TLS record simply based on the fact that this scheme is not semantically secure. So I should say that this method of choosing the IV to be the last block of the previous record is called chained IVs, and you should remember that this actually should not be used in practice because it always leads to an attack. Because of this, TLS 1.1 moved to what's called explicit IVs, where every TLS record has its own random, unpredictable IV. And that's fixed the problem. As soon as browsers and servers move to TLS 1.1, this will no longer be an issue. Now, another mistake that was done in TLS 1.0 and earlier enabled what's called a padding oracle, which is something that we're going to talk about in the next segment, where what happened was that if the ciphertext was rejected due to an invalid pad, the server would send back an alert message saying decryption failed. Whereas if the ciphertext was rejected due to a bad MAC, the server would send back a bad record MAC alert. As a result, an adversary who observes the alert sent back from the server can tell whether the pad in the ciphertext was valid or invalid, and this introduces a very significant attack called a padding attack, which we're going to talk about in the next segment. The solution to this in TLS 1.1 was basically to say that instead of reporting decryption failed here, we're going to report a bad record MAC even if the pad is incorrect. and as a result, simply looking at which alert is sent back from the server, an attacker can't tell if the ciphertext is rejected because of a bad pad or a bad MAC. So this tries to mask this information. Now the lesson from this is that when decryption fails, you should never ever explain why. I guess this is something that comes out of networking protocols, where if there's a failure, you want to tell the peer why the failure occurred. Well, in cryptography, if you explain why the failure occurred, that very often leads to an attack. In other words, when decryption fails, just output reject, and don't explain why the reject actually happens, just reject the ciphertext. Okay, so now that we've seen TLS 1.1, let's see a broken protocol. So of course I always like to pick on 802.11b WEP, which pretty much got everything wrong. So let's see how not to provide authenticated encryption. So let me remind you how 802.11b WEP works. Basically there's a message that the laptop wants to send to the access point. The first thing that happens is that the laptop computes a cyclic redundancy checksum on the message and concatenates the CRC checksum to the message. Then the result is encrypted using a stream cipher, in particular RC4. If you recall, the key that's used is the concatenation of an initial value IV that changes per packet and the long-term key K, and then the IV along with the ciphertext are transmitted to the other side. Now we already saw two problems with this approach. One was if the IV is ever repeated, and in fact it is going to be repeated, then you get a two-time pad attack. And the other problem is that WEP uses very closely related keys. In other words, the key is simply IV concatenated K, and the only thing that changes is the IV. So the key is always fixed, which means that these PRG keys are very closely related to one another. And as we said, the PRG that's used here, RC4, is not designed for this type of use, and it completely breaks if you use it with related keys, and as a result, WEP has no security at all. What I want to show you is that even the CRC mechanism that's used here in an attempt to provide integrity and prevent an adversary from tampering with the ciphertext, even that mechanism is completely broken, and it's actually very easy to tamper with ciphertexts en route. So let's see how that's done. The attack uses a particular property of the CRC checksum, namely that CRC is linear. What that means is if I give you CRC of M, and I ask you to compute CRC of M XOR P, then it's very easy to do. Basically, you just compute some well-known and public function of Fp, you XOR these two together, and that in fact will give you CRC of M XOR P. So in some sense, the XOR just comes out of the parentheses, and that basically means that CRC is linear. Now here's how the attack works. Suppose the adversary intercepts a particular packet that's destined to the access point. Now the packet says it's destined for destination port 80, and the attacker knows that it's intended for destination port 80, and what he wants to do is modify the ciphertext such that now the destination port will say 25 instead of 80. And maybe the attacker can read messages for port 25, and that's how he actually obtains the actual data in the packet. So recall that the CRC checksum is there to make sure that exactly the attacker cannot change data inside of the ciphertext. But I want to show you that in fact it's really easy to modify data in the ciphertext, and the CRC basically provides no security against tampering at all. So let's see how to do it. Well, what the attacker would do is he would basically XOR a certain value XX into the bytes that represent the 80 in the ciphertext. Now what he'll XOR in will basically be the string 25 XOR 80. And you remember that if I XOR a certain string XX into the ciphertext that was created using a stream cipher, when that ciphertext is decrypted, the plaintext at this position will also be XORed by XX. And as a result, after decryption, the plaintext at this position basically will be the original 80 XOR 25 XOR 80, which gives us 25. Okay, so after decryption, the plaintext at this position will now be 25. The problem is that if that's all we did, then this attack would fail because the CRC checksum would not validate. The CRC checksum was built with 80 as a plaintext, but 25 is a different plaintext and needs a different CRC. But it's not a problem because what we can do is we can easily correct the checksum, the CRC checksum, even though the CRC checksum is encrypted. What we do is we XOR f of XX into the ciphertext at the place where the CRC is supposed to be. And as a result, when the ciphertext is decrypted, what will happen is we'll get the correct CRC checksum after decryption. So the interesting thing that happened here is even though the attacker doesn't know what the CRC value is, he's able to correct it using this linearity property, such that when the ciphertext is decrypted, the correct CRC value appears in the plaintext. Okay, so the linearity property of CRC plays a critical role in making this attack works. The end conclusion here is basically that a CRC checksum provides absolutely no integrity at all against active attacks, and it should never ever be used as an integrity mechanism, and instead, if you want to provide integrity, you're supposed to use a cryptographic MAC, not an ad hoc mechanism like CRC. Okay, so now we've seen how authenticated encryption is implemented in a real-world protocol like TLS. In the next segment, we're going to look at real-world attacks on authenticated encryption implementations that happen to implement authenticated encryption incorrectly. In this segment and the next, I want to show you two very cute attacks on deployed authenticated encryption systems. But first, let's do a quick recap. So recall that authenticated encryption means that the system provides CPA security plus ciphertext integrity. And authenticated encryption means that we can preserve confidentiality in the presence of an active adversary, and moreover, the adversary can't modify the ciphertext in any way without being detected. We also showed that authenticated encryption prevents these very powerful chosen ciphertext attacks. Unfortunately, authenticated encryption has a pretty significant limitation in that it simply can't help a bad implementation. If you implement authenticated encryption incorrectly, then your implementation will be vulnerable to active attacks. And then we looked at standards constructions. I mentioned these three standards that provide authenticated encryption. And I want to point out, when you need to use authenticated encryption in practice, you should just be using one of these three standards. You shouldn't try to implement authenticated encryption by yourself. And I hope that the attack that I show you in this segment convinces you that this is not something you should do yourself. Just use one of GCM, CCM, or AEX. However, it's good for you to know that in general, when you want to provide authenticated encryption, the correct way to do things is encrypt then MAC, because then no matter which encryption and MAC algorithms you combine, the result will be authenticated encryption, again, assuming the encryption and MAC algorithm are implemented correctly. Okay, so let's look at a very cute attack on the TLS record protocol, in particular when CBC encryption is used. Let me just briefly remind you that the way TLS decryption works is, first of all, an incoming ciphertext is CBC decrypted. Then the next thing that happens is the implementation will check that the pad has the correct format. For example, if the pad is of length 5, the format should be 55555. And if it's not of the correct format, then the ciphertext is rejected. So this basically checks that the ending of the decrypted record contains the correct pad. And then if the pad has the correct format, then the next thing that happens is that the MAC is checked, the tag is checked, and if the tag turns out to be incorrect, again, the record is rejected. If the tag is valid, then the remaining data is considered to be authentic and is given to the application. So what I wanted to point out is there are two types of errors in TLS decryption. One is a padding error and one is a MAC error. And it turns out it's very important that the adversary not be told which of these errors occurred. And let me briefly explain why. So suppose an attacker can actually differentiate the two types of errors. In other words, he can tell if a pad error occurred or a MAC error occurred. The result is what we call a padding oracle. Because now imagine the adversary has a certain ciphertext that it intercepted, and it wants to try and decrypt that ciphertext. What it could do is it could take that ciphertext as is and submit it to the server. The server is going to decrypt the ciphertext and then look to see if the pad has the correct format. If the pad doesn't have the correct format, we'll get one type of error. If the pad has the correct format, it's very likely, since this is just some random ciphertext that the adversary concocted himself, it's very likely the MAC will be incorrect, and then the adversary will observe a MAC error. So if the pad is invalid, we'll see a pad error, whereas the pad is valid, we'll see a MAC error. As a result, the adversary, after submitting the ciphertext to the server, the adversary can tell whether the last bytes in the decrypted ciphertext have a valid pad or not. In other words, whether the last bytes in the decrypted ciphertext end with 1 or 22 or 333 or 4444 and so on. So the adversary learns something about the decrypted ciphertext just by submitting the ciphertext to the server. So this is a beautiful example of what's called a chosen ciphertext attack, where again the adversary submits a ciphertext and then he gets to learn something about the resulting plaintext. And now the question is whether he can use that information to completely decrypt a given ciphertext. And I want to show you that a padding oracle can actually be used to completely decrypt a given ciphertext. But before I say that, I want to remind you that older versions of TLS actually leaked the type of error simply in the alert message that was sent back to the peer. Different types of alerts were sent depending on which type of error occurred. As soon as this attack came out, SSL implementations simply always reported the same type of error, so just looking at the alert type wouldn't tell the adversary which error occurred. Nevertheless, there was still a padding oracle. So let me explain why. So this was observed by Canville et al. Canville et al. Realized that the way TLS decryption is implemented is, first of all, the record is decrypted, then the pad is checked, and if the pad is invalid, decryption is aborted and an error is generated. If the pad is valid, then the MAC is checked, and then if the MAC is invalid, decryption is aborted and an error is generated. As a result, this causes a timing attack. You realize that if pad is invalid, then the alert message is sent very quickly. And you notice here that in fact you see that within 21 milliseconds the ciphertext is rejected. However, if the pad is valid, then now the MAC needs to be checked, and when it's discovered to be invalid, the alert is only generated at that point. In other words, then in that case, it takes a little bit longer until the alert is generated, and you see that on average this takes about 23 milliseconds. So even though the same alert is sent back to the peer, the adversary can simply observe the time until the alert message is generated. If the time is short, it knows the pad was invalid. If the time is long, it knows the pad was valid, but the MAC was invalid. And as a result, the adversary still has a padding oracle that can tell it whether the pad was valid or invalid. So now let's see how to use a padding oracle. So I claim that if the attacker has a certain ciphertext C, he can completely decrypt that ciphertext just using the padding oracle. So let's see how to do it. And just as an example, suppose he wants to obtain M1. In other words, a decryption of the second block of the ciphertext. So let's see what he would do. So here we have the ciphertext that the attacker intercepted. And this just happens to be the decryption of that ciphertext. And the reason I wrote this down is I wanted you to remember how CBC decryption works. So you should keep in mind that one ciphertext block is directly XORed into the decryption of the next ciphertext block. Okay, so the adversary here wants to basically learn just this part of the plaintext setting. So here's what he's going to do. So first of all, he's going to throw away C2 so that the last block really is just C1, which is the one that he's interested in decrypting. Now let's suppose that he has a certain guess G for the last byte of M1. In other words, he just has a guess for this very, very, very last byte. G is a value between 0 and 255. What the attacker will do is the following. He will XOR the value G XOR 01 into the last byte of the block C0, the previous block. Yes, so all he did is he took the last byte of the previous block and XORed that with his guess XOR 01. Now let's think for just a second and see what happens when this two-block ciphertext is decrypted. Well, C0 is going to get decrypted to whatever it's decrypted to. That's just going to be some garbage that we don't care about. But now when C1 is decrypted, the last byte is going to be XORed with this modified C0, and the result, the last byte of the plaintext is going to be also XORed with this extra value that we stuck into C0. So what goes in here is the actual original last byte in the plaintext M1, but now it gets XORed with G XOR 0x01. So now you see where I'm going with this. If the guess G for the last byte of M1 is correct, then these two guys will cancel one another. Last byte XOR G is just 0. And what we'll get as the last byte of the plaintext is just 0x01. I should mention, by the way, 0x01 just means hex notation for 01. So literally, this is just a 1-byte representation of the number 1. Good. So again, what this means is if our guess for the last byte of M1 is correct, then we get a pad that's well-formed. It's just the number 1. The number 1 is a well-formed pad, and therefore the pad is valid, and the padding oracle will say the pad is valid. If the guess is incorrect, then we'll get a value here that's not equal to 1, and then it's very likely that we have an invalid pad. And as a result, the padding oracle will say the pad is invalid. So again, you see that if our guess for the last byte of M1 is correct, we learn that G was in fact a correct guess, whereas if our guess is incorrect, then we learn that G is an incorrect guess. So what the attacker is going to do is he's going to create his modified ciphertext. You notice he only modifies the second block of the ciphertext. We're going to send this to the padding oracle, and then based on the result of the padding oracle, we learn whether the last byte is equal to G or not. Well, now we can simply repeat this again and again for G from 0 to 255. This basically requires 256 chosen ciphertext queries. Actually, I guess on average we'll only have to do 128 chosen ciphertext queries until we find the right G. And then we learn the last byte of M1. Well, so now we know the last byte of M1. I claim that we can now use the exact same process to learn the second to last byte of M1. Let me ask you, what pad are we going to use to learn the second to last byte of M1? Well, it shouldn't be surprising that instead of just using the pad containing the byte 1, we're going to use a 2-byte pad containing the bytes 22. That's a well-formed pad. And now we can always make sure, because we know the last byte of M1, when we do our XORing trick, we can always make sure that the last byte of the plaintext is in fact 02. And now we can guess the second to last byte of M2 by simply trying lots of values in G until we find one that makes the pad in fact be 0202. And by issuing 256 additional queries to the padding oracle, we will get to learn the second to last byte of M1. And now we can iterate this again and again, and basically since the length of the block is 16 bytes, after 16 times 256 queries, we get to learn all of M1. So this is a pretty significant attack that is able to decrypt blocks of the TLS record. So those of you who know the inner workings of TLS should complain that this attack isn't going to work. The problem is that when TLS receives a record with a bad pad or a bad MAC, it shuts down the connection and renegotiates a new key. As a result, the attacker is now stuck with a ciphertext encrypted using an old key, and that key is no longer used anywhere, so it cannot submit any more queries. So with TLS, basically, it can only submit one query, and that's it. Even a single query still leaks information about the plaintext to the attacker, but it doesn't expose the entire plaintext block M1. However, this attack is so cute that whenever there's a mistake like this in a protocol, there will be some settings in which it comes up. And in this case, the setting is in the case of an IMAP server. So IMAP is a popular protocol for reading email from an IMAP email server. And it's very common to protect the IMAP protocol by running it on top of the TLS protocol. Now, it turns out in IMAP, every 5 minutes, the IMAP client will connect to the IMAP server and check whether there's new email. And the way it does it is by first logging in to the IMAP server by sending this login username password message, and then it goes ahead and checks if there's new email available. Well, what this means is that every 5 minutes the attacker gets an encryption of exactly the same message. In particular, it gets an encryption of the password. And so every 5 minutes it can mount one guess on the block that contains the password. And so if your password is 8 characters long, the attacker simply needs to recover those 8 characters, and he's going to recover them 1 byte at a time by doing one guess per 5 minutes. And so Canville et al. Showed that within a few hours you can basically recover the user's password just by mounting one guess every 5 minutes. So this is a pretty significant attack against an implementation of TLS, and the defense against this was to always check the MAC whether the pad is valid or invalid, and as a result it takes the same amount of time to respond whether the pad is valid or invalid. So this removes the timing attack and makes this attack much harder to mount. So there are 2 lessons here. First of all, you notice that if TLS had used encrypt then MAC rather than MAC then encrypt, then this whole issue would be completely moot, because in encrypt and MAC, the MAC is checked first, and only then does decryption and pad checking take place. In encrypt and MAC, the ciphertext is discarded because the MAC is invalid, and we never even get to a pad check. As a result, any tampering or games with a ciphertext will be discarded immediately because the MAC is simply going to fail. The second lesson to remember is that, remember I told you that MAC then CBC actually does provide authenticated encryption, but only if you don't reveal why decryption failed. In this case, the padding oracle completely destroyed the authenticated encryption property, and basically I showed you an attack that shows that now this mode does not provide authenticated encryption. So let me ask you the following question. Suppose in TLS, instead of using MAC then CBC, TLS did MAC then counter mode encryption. Would the padding oracle attack still be possible or not? The answer is it wouldn't be possible, simply because counter mode doesn't use any padding at all. So this padding oracle attack only affects CBC encryption modes in TLS. TLS also supports counter mode encryption, and counter mode encryption modes are simply not affected by these padding attacks. So that's the end of this segment. In the next segment, I want to show you another very, very clever attack on authenticated encryption systems. In the last segment, we looked at a padding oracle attack that completely breaks an authenticated encryption system. I hope this attack convinces you that you shouldn't implement authenticated encryption on your own, because you might end up exposing yourself to a padding oracle attack or a timing attack or any other such attack. Instead, you should be using standards like GCM or any other of the standardized authenticated encryption modes as implemented in many crypto libraries. In this segment, I'm going to show you another very clever attack on an authenticated encryption system, and I hope after you see this attack, you'll be completely convinced not to invent and implement your own authenticated encryption systems, but instead always use one of the standard schemes like GCM or others. So this particular attack that I want to show you is an attack on the SSH binary packet protocol. So SSH is a standard secure remote shell application that uses a protocol between a client and the server. It has a key exchange mechanism, and once two sides exchange keys, SSH uses what's called the binary packet protocol to send messages back and forth between the client and the server. Now here's how SSH works. So recall that SSH uses what we called encrypt and MAC. Okay, so technically what happens is every SSH packet begins with a sequence number, and then the packet contains the packet length, the length of the CBC pad, the actual payload follows, then the CBC pad follows. Now this whole red block here is CBC encrypted, also with a chained IV, so this is also vulnerable to the CPA attack that we discussed before. But nevertheless, this whole red packet is encrypted using CBC encryption, and then the entire clear text packet is MAC'd, and the MAC is sent in the clear along with the packet. So I want you to remember that the MAC is computed over plain text packet, and then the MAC is sent in the clear. This is what we call encrypt and MAC. And we said that this is not a good way to do things because MACs have no confidentiality requirements, and by sending the MAC of the clear text in the clear, you might be exposing information about the clear text. But this is not the mistake that I want to show you here. I want to show you a much more clever attack. So first, let's look at how decryption works in SSH. So what happens is, first of all, the server decrypts the encrypted packet length field only. So it only decrypts these particular first few bytes. Then it will go ahead and read from the network as many bytes as specified in the packet length field. It's going to decrypt the remaining ciphertext blocks using CBC decryption. Then once it's recovered the entire SSH packet, it will go ahead and check the MAC of the plaintext and report an error if the MAC happens to be invalid. Now the problem here is that the packet length field is decrypted and then used directly to determine the length of the packet before any authentication has taken place. In fact, it's not possible to verify the MAC of the packet length field because we haven't recovered the entire packet yet, and as a result we cannot check the MAC. But nevertheless, the protocol uses the packet length before verifying that the MAC is valid. So it turns out this introduces a very, very cute attack, and I'm only going to describe a very simplified version of this attack just to get the idea across. So here's the idea. Suppose the attacker intercepted a particular ciphertext block, namely the direct AES encryption of the message block M, and now he wants to recover this M. And I emphasize that this intercepted ciphertext is only one block length. It's one AES block. So here's what the attacker is going to do. Well, he's going to send a packet to the server that starts off as normal. It basically starts off with a sequence number, and then he's going to inject his capture ciphertext as the first ciphertext block that's sent to the server. Now what is the server going to do? The server is going to decrypt the first few bytes of this first AES block, and he's going to interpret the first few bytes as the length field of the packet. The next thing that's going to happen is the server is going to expect this many bytes before it checks that the MAC is valid. And so what the attacker is going to do is he's going to feed the server one byte at a time. So the server will read one byte and then another byte and then another byte. Eventually the server will read as many bytes as the length field specifies, at which point it will check that the MAC is valid. And of course the attacker was just feeding the server junk bytes, and as a result the MAC is not going to verify and the server will send a MAC error. But you realize that what happened here, the attacker was counting how many bytes it sent to the server, and so it knows exactly how many bytes were sent at the time that it receives the MAC error from the server. So that tells it that the decryption of the first 32 bits of its ciphertext C are exactly equal to the number of bytes that were sent before it saw MAC error. So this is a very clever attack. So let me say it one more time to make sure this is clear. So again, the attacker has a one-block ciphertext C that it wants to decrypt. And let's pretend that when C is decrypted, the 32 most significant bits of the plaintext happen to be the number 5. In this case, what the attacker will see is the following behavior. The server is going to decrypt the challenge block C, and he's going to obtain the number 5 as the length field. So now the attacker is going to feed the server 1 byte at a time, and after the attacker feeds the server 5 bytes, the server says, hey, I've just recovered the entire packet, let me check the MAC. The MAC is likely to be false, and then it will send bad MAC error. So after 5 bytes are read off the network, the attacker is going to see a bad MAC error, and then the attacker learns that the most significant 32 bits of the decrypted block is equal to the number 5. So there. So he just learned the 32 most significant bits of C. So this is a very significant attack because the attacker just learned 32 bits of the decrypted ciphertext block, and since he can apply this attack to any ciphertext block he wants, he can basically learn the first 32 bits of every ciphertext block in a very long message. So what just happened here? Well, there are actually two things that were wrong in this design. The first one is the decryption operation is non-atomic. In other words, the decryption algorithm doesn't take a whole packet as input and respond with a whole plaintext as output or with the word reject. Instead, the decryption algorithm partially decrypts the ciphertext, namely to obtain the length field, and then it waits to recover as many bytes as needed, and then it completes the decryption process. So these non-atomic decryption operations are fairly dangerous, and generally they should be avoided. In this example, this non-atomic decryption happens to break authenticated encryption. The other problem that happened is that the length field was used before it was properly authenticated, and this is another issue that should never be done. So a decryption field should never be used before the field is actually authenticated. So let me ask you, if you had the option of redesigning SSH, what is the minimum change you would do to make SSH resist this attack? And let me tell you that multiple answers might be correct. One option is to send the length field in the clear, just as in the case of TLS. In this case, there's no opportunity for an attacker to submit chosen ciphertext attack because, well, the length field is never decrypted, and so there's no decryption taking place that the attacker can abuse. Replacing encrypt and MAC by encrypt then MAC doesn't have any impact because this attack would apply either way. The problem is that the length field is used before it's authenticated, and that would have to happen either way. So a better mode of encryption doesn't actually help. Another option is to MAC the length field separately so that now the server can read the length field, check that the MAC for just the length field is valid, and then it would know how many subsequent bytes to read before checking the MAC field on the entire packet. The last option is actually one that works but is terribly inefficient. It would expose the server to a denial of service attack, so I'm not going to mark it as a valid answer. So the main lesson to remember is don't implement or design your own authenticated encryption system. Just use the standards like GCM. But if for some reason you can't use the standards and you have to implement your own authenticated encryption system, then use encrypt then MAC, and make sure not to repeat the mistakes of the last two segments, namely don't use a length field before the length field is authenticated, and more generally don't use any decrypted field before that field is authenticated. Okay, so this is the end of our discussion of authenticated encryption. I wanted to point out a couple of papers on authenticated encryption that you could use as further reading. The first one is a very cute one on the order of encryption and authentication that talks about whether one should do encrypt then MAC or MAC then encrypt, and it shows that one is correct and one is incorrect. It's a good read and there's a lot of information in that paper. The second paper discusses OCB mode, which is a very efficient way of building authenticated encryption. In particular, it looks at a variant of OCB with associated data, as we discussed when we described OCB. The last three papers are attack papers. The first one describes the padding oracle attack that we discussed in the last segment. This one here describes the length attack that we just described in this segment. And the last one describes a number of attacks on encryptions that just use CPA-security without adding integrity. So this last paper actually provides a number of good examples for why CPA-security by itself should never ever be used for encryption. Remember, the only thing you're allowed to use is authenticated encryption for confidentiality, or if all you need is integrity with no confidentiality, then you just use a MAC. Well, we're almost done with our discussion of symmetric encryption. There are just a couple of odds and ends that I'd like to discuss before we move on to the next topic. So the first thing I'd like to mention is how we derive many keys from one key. And actually this comes up all the time in practice. So I'd like to make sure you know how to do this correctly. So what's the settings that we're looking at? Well, imagine we have a certain source key that's generated by one of a number of methods. Imagine the source key is generated by a hardware random number generator, or perhaps is generated by a key exchange protocol, which we're going to discuss later. But anyhow, there are a number of ways in which a source key might be generated between Alice and Bob, such that the attacker doesn't know what this source key is. But now, as we said, in many cases, we actually need many keys to secure a session, not just one single source key. For example, if you remember in TLS, there were unidirectional keys. We needed keys in each direction. And in fact, in each direction, we needed multiple keys. We needed a MAC key, we needed an encryption key, we needed an IV, and so on. Similarly, in non-spaced encryption, you remember there were multiple keys that were being used, and so on. And so the question is, how do we use the one source key that we just derived, either from a hardware process or by key exchange, and generate a bunch of keys from it that we can then use to secure our session? The way that's done is using a mechanism called a key derivation function, KDF, and I want to talk a little bit about how KDFs are constructed. So first of all, suppose we have a secure PRF that happens to have key space K. And now, suppose that it so happens that our source key SK is uniform in the key K. In this case, the source key is in fact a uniform random key for the secure PRF F, and we can use it directly to generate keys, all the keys that we need to secure the session. So in this case, the KDF is really simple. The key derivation function would just work as follows. It would take as input the source key. It would take an input, a parameter context, which I'm going to describe in just a minute, and then it's going to take a length input as well. And then what it will do is it will basically evaluate the PRF on 0. Then it will evaluate the PRF on 1. Then it will evaluate the PRF on 2 up until L. And we'll talk about what this context is in just a second. And then basically you would use as many bits of the output as you would need to generate all the keys for the session. So if you need unidirectional keys, you would generate one key in each direction, where each key might include an encryption key and a MAC key. And so you would basically generate as many bits as you need, and then finally cut off the output at the time when you've generated enough keys to secure your session. Okay, so this is a fairly straightforward mechanism. It's basically using the secure PRF as a pseudo-random generator. And the only question is, what is this context string? Well, I'll tell you that the context string is basically a unique string that identifies the application. So in fact, you might have multiple applications on the same system that's trying to establish multiple secure keys. Maybe you have SSH running as one process, you have a web server running as another process, IPsec as a third process, and all three need to have secret keys generated. And this context variable basically tries to separate the three of them. So let me ask you more precisely, what do you think the purpose of this context variable is? So I guess I've given it away, and this context variable is supposed to basically separate applications so that even if, for example, the three services that we just talked about, SSH, web server, and IPsec, if they all happen to obtain the same source key from the hardware random number generator, then the context, since it's different for the three apps, will make sure that they still get three independent strings that they can then use to secure the sessions. I just want you to remember that even though this is actually fairly straightforward, and we discussed this before, the context string is actually important, and it does need to be specific to the application so that each application gets its own session keys, even if multiple applications happen to sample the same SK. The next question is, what do we do if the source key actually isn't uniform? Well, now we got a problem. If the source key is not a uniform key for the pseudo-random function, then we can no longer assume that the output of the pseudo-random function is indistinguishable from random. In fact, if we just use the KDF that we just described, then the output might not look random to the adversary, and then he might be able to anticipate some of the session keys that we'll be using and thereby break the session. So then we have a problem. Now, why would this source key not be uniform? Well, there are many reasons why this happens. For example, if you use a key exchange protocol, it so happens typically that key exchange protocols will generate a high entropy key, but the high entropy key is going to be distributed in some subspace of the key space. So it's not going to be a uniform string, it'll be uniform in some subset of a larger set. And we'll see examples of that as soon as we talk about key exchange protocols. And so KDFs have to kind of accommodate for the fact that key exchange protocols actually don't generate uniform bit strings. The other problem is that, in fact, the hardware random number generator you're using might actually produce biased outputs. We don't want to rely on the non-bias of the hardware random number generator, and so all we want to assume is that it generates a high entropy string, but one that might be biased, in which case we have to somehow clean this bias. And so this introduces this paradigm for building KDFs. This is called the extract then expand paradigm, where the first step of the KDF is to extract a pseudo-random key from the actual source key. So in a picture, you can think about it like this. In some sense, these are the different possible values of the source key. This is the horizontal line. And the vertical axis is basically the probability of each one of these values. And you can see that this is kind of a bumpy function, which would say that the source key is not uniformly distributed in the key space. What we do in this case is we use what's called an extractor. So an extractor is something that takes a bumpy distribution and makes it into a uniform distribution over the key space. In our case, we're actually just going to be using what are called computational extractors, namely extractors that don't necessarily produce uniform distribution at the end, but they generate a distribution that's indistinguishable from uniform. Now, extractors typically take as input something called a salt. And a salt, just like in a salad, it kind of adds flavor to things. What it does is basically kind of jumbles things around so that no matter what the input distribution is, the output distribution is still going to be indistinguishable from random. So a salt, basically, what is it? It's a non-secret string, so it's publicly known. It doesn't matter if the adversary knows what the salt is, and it's fixed forever. The only point is that when you chose it, you chose one at random. And then the hope is that the funny distribution that you're trying to extract from kind of doesn't inherently depend on the salt that you chose, and as a result, using your salt, you will actually get a distribution that looks indistinguishable from random. So essentially, the salt, you can just bang on the keyboard a couple of times when you generate it, but it just needs to be something that's random initially, but then it's fixed forever, and it's fine if the adversary knows what it is. And nevertheless, the extractor is able to extract the entropy and output a uniformly random string K. In some sense, the salt is only there to defend against adversarially bad distributions that might mess up our extractor. Okay, so now that we have extracted a pseudo-random key, now we might as well just use it in a KDF that we just saw using a secure pseudo-random function to expand the key into as many bits as we need to actually secure the session. Okay, so there are these two steps. The first one is we extract a pseudo-random key, and then once we have a pseudo-random key, we already know how to extend it into as many keys as we need using a pseudo-random function. So the standardized way of doing this is called HKDF. This is a KDF, a key derivation function that's built from HMAC. And here HMAC is used both as the PRF for expanding and an extractor for extracting the initial pseudo-random key. So let me explain how this works. So in the extract step, we're going to use our salt, which you remember is a public value, just happened to be generated at random at the beginning of time, and we use this salt as the HMAC key. And then the source key we're going to use as the HMAC data. So we're kind of using a public value as a key, and nevertheless, one can argue that HMAC has extraction properties such that when we apply HMAC, the resulting key is going to look indistinguishable from random, assuming that the source key actually has enough entropy to it. And now that we have the pseudo-random key, we're simply going to use HMAC as a PRF to generate a session key, as many bits as we need for the session keys. Okay, so that basically concludes our discussion of HKDF, and I just want you to remember that once you obtain a source key either from hardware or from a key exchange protocol, the way you convert it into session keys is not by using that sample directly. You would never use the source key directly as a session key in a protocol. What you would do is you would run the source key through a KDF, and the KDF would give you all the keys and output that you need for the randomness, for the random keys to be used in your protocol. And a typical KDF to use is HKDF, which is actually getting quite a bit of traction out there. Okay, the last topic I want to talk about in this segment is how do you extract keys from passwords. So these are called password-based KDFs, or PB-KDFs. The problem here is that passwords have relatively low entropy. In fact, we're going to talk about passwords later on in the course when we talk about user authentication. And so I'm not going to say too much here. I'll just say passwords generally have very little entropy. Estimate is something on the order of 20 bits of entropy, say. And as a result, there's simply not enough entropy to generate session keys out of a password. And yet, we still need to do it very frequently. We still need to derive encryption keys and MACs and so on out of passwords. So the question is how to do it. The first thing is, for this kind of purpose, don't use HKDF. That's not what it's designed for. What will happen is that the derived keys will actually be vulnerable to something called a dictionary attack, which we're going to talk about much later in the course when we talk about user authentication. So the way PBKDFs defend against this low entropy problem that results in a dictionary attack is by two means. First of all, as before, they use a salt, a public random value that's fixed forever. But in addition, they also use what's called a slow hash function. And let me describe kind of the standard approach to deriving keys from passwords. This is called PKCS5, and in particular, the version I'll describe is what's called PBKDF1. And I should say that this mechanism is implemented in most crypto libraries, so you shouldn't have to implement this yourself. All you would do, you would call a function, derive key from password. You would give the password in as input, and you would get a key as output. But you should be aware, of course, that this key is not going to have high entropy, so in fact, it will be guessable. What these PBKDFs try to do is make the guessing problem as hard as possible. Okay, so the way they work, first of all, is, as we said, they basically hash the concatenation of the password and the salt, and then the hash itself is designed to be a very slow hash function, and the way we build a slow hash function is by taking one particular hash function, say SHA-256, and we iterate it many, many times, C times. So you can imagine 1,000 times, perhaps even 1,000,000 times. And what do I mean by iterating it? So, well, we take the password and the salt, and we put them inside of one input to the hash function, and then we apply the hash function. Oops, let me write it like this. And then we apply the hash function and we get an output. And then we apply the hash function again and we get another output. And we do this again and again and again, maybe 1,000 times or 1,000,000 times, depending on how fast your processors are. And then finally we get the final output that we actually output as the key output of this key derivation function. Now, what is the point here? Iterating a function 10,000 times or even 1,000,000 times is going to take very little time on a modern CPU, and as a result, it doesn't really affect the user's experience. The user types in his password, it gets hashed 1,000,000 times, and then it gets output. And maybe that could even take a tenth of a second, and the user wouldn't even notice it. However, the attacker, all he can do is he can try all the passwords in a dictionary, because we know people tend to pick passwords in dictionaries. And so he could just try them one by one. You remember, the salt is public, so he knows what the salt is. And so he can just try this hash one by one. However, because the hash function is slow, each attempt is going to take him a tenth of a second. So if he needs to run through a dictionary, with 200 billion passwords in it, because the hash function is slow, this is going to take quite a while. And by doing that, we slow down the dictionary attack, and we make it harder for the attacker to get our session keys. Not impossible, just harder. That's all this is trying to do. Okay, so this is basically what I wanted to say about password-based KDFs. As I said, this is not something you would build yourself. All crypto libraries have an implementation of a PKCS5 mechanism, and you would just call the appropriate function to convert a password into key and then use the resulting key. Okay, in the next segment, we're going to see how to use symmetric encryption in a way that allows us to search on the ciphertexts. In this segment, we're going to look at the concept of deterministic encryption that often comes up in practice. When I say deterministic encryption system, I mean an encryption system that will always map given message to exactly the same ciphertext. So if we encrypt the same message 3 times, every time we'll get exactly the same ciphertext. So there are no nonsense involved here. Literally, this is just a consistent encryption scheme that will always output the same ciphertext given a particular message. So let's see where this comes up in practice, and in particular, I want to show you the case of lookups into an encrypted database. So the settings are, imagine we have a server here that is going to store information inside of an encrypted database. So what it'll store is records, and every record has an index and some data that's stored inside of the record. Now, the first thing the server is going to do is he's going to encrypt this record. So here the record became encrypted, and you notice that the index became encrypted with K1, and the data is encrypted with K2. And then the encrypted record is sent over to the database. And the same thing happens to many records, so that the database overall holds many, many encrypted records, where again you can imagine that the index is encrypted using the key K1, and then the data in the records is encrypted using the key K2. Now, if encryption is deterministic, the nice thing about that is that at a later time, when the server wants to retrieve a record from the database, all he needs to do is send to the database an encryption of the index that the server is interested in. So here it would send an encryption of the index Alice. That again becomes encrypted, and the resulting ciphertext is identical to the ciphertext that was generated when the record was first written to the database. And the database can then, find a record that has this encrypted index in it, and then send the result back to the server. The nice thing about this is that now the database is completely in the dark as to what data is stored in the database, and it doesn't even know what records are being retrieved by the server, since all it sees are basically requests for encrypted indices. And so this deterministic encryption mechanism lets us do a quick lookup in the database given an encrypted index, and we're guaranteed that because of the deterministic encryption property, that the index is going to become encrypted in exactly the same way as it was when the record was created. And so this should be disturbing to many of you, because we previously said that deterministic encryption simply cannot be chosen plaintext secure. The problem is that an attacker can look at different ciphertexts, and if he sees the same ciphertext twice, he knows that the underlying encrypted messages must also be the same. So in other words, by looking at ciphertext, he can learn something about the corresponding plaintext, because every time he sees the same ciphertext twice, he knows that the underlying messages are equal. In practice, this leads to significant attacks, and particularly when the message space is small. For example, if we're transmitting single bytes across the network, such as keystrokes that are being transmitted one keystroke at a time, then in fact an attacker can simply build a dictionary of all possible ciphertexts. If it's only single bytes, then there will only be 256 possible ciphertexts. And then simply by learning what the decryptions of those ciphertexts are, he can actually figure out all future ciphertexts simply by looking them up in this dictionary. And so there are many cases where the message space is small, where this deterministic encryption simply is insecure. Now concretely, in the case of an encrypted database, what the attacker would see is if there are two records that happen to have the same ciphertext in the index position, then now he knows that those two records correspond to the same index. So again, even though he doesn't know what the index is, he learned something about the corresponding plaintexts. I wanted to briefly remind you that formally we say that deterministic encryption cannot be CPA-secure by describing an adversary that wins the CPA game, the chosen plaintext attack game. And let me quickly remind you how that works. The game starts by the adversary sending two messages, M0 and M0. And remember that in this game, the adversary is always going to be given the encryption of the left message or the encryption of the right message. In this case, since he used the same message in both cases, both on the left and on the right, he's simply going to get the encryption of the message M0. In the next step, he's going to send the messages M0, M1, and now he's either going to get the encryption of M0 or the encryption of M1, and his goal is to tell which one he got. But because the encryption is deterministic, this is very easy for him to do. All he has to do is just test whether C is equal to C0. And if C is equal to C0, then he knows that he got the encryption of M0. If C is not equal to C0, he knows that he got the encryption of M1. So he can output 0 if C is equal to C0 and output 1 if C is not equal to C0. And his advantage in this particular game would be 1. So it would be as high an advantage as possible, which means that the attacker completely defeats chosen plaintext security. Okay, so this is just a formal way of saying that the attacker basically learns more information about the plaintext than he should. So the question is, what do we do? And it turns out the solution is basically to restrict the type of messages that can be encrypted under a single key. And so the idea is to say that suppose the encryptor never, ever, ever encrypts the same message under a single key. In other words, the message key pair is always different and never repeats. So that for every single encryption, either the message changes or the key changes, or both change. But it can't be that we encrypt the same message twice under the same key. So why would this ever happen? Well, it turns out there are very natural cases where this happens. For example, if the messages happen to be random, say the encryptor is encrypting keys, and those keys, say are 128-bit keys, so they'll never actually, with very high probability, they'll never repeat. In this case, when we're encrypting keys, in fact, it's very likely that all the messages that are encrypted under one master key are always distinct, because, again, these keys are very unlikely to ever repeat. The other reason why messages would never repeat is simply because of some structure in the message space. For example, if all we're encrypting are unique user IDs, so imagine in the database example, the index corresponds to a unique user ID, And if there's exactly one record in the database for each user, that says that every encrypted record basically contains an encrypted index where the index is distinct for all records in the database. Okay, so these are two reasons why messages might never repeat, and this is a fairly reasonable thing that actually does happen quite often in practice. So now if the messages never repeat, now maybe we can actually define security and actually give constructions that satisfy our definitions. So this motivates the concept of deterministic chosen plaintext attacks, and let me explain what they mean. So as usual, we have a cipher defined as an encryption and a decryption algorithm. So we have a key space, a message space, and a ciphertext space. And we're going to define security just as normal using two experiments, experiment 0 and experiment 1. And the game actually looks very similar. It's almost an identical game to the standard chosen plaintext attack game, where basically the attacker issues queries. So you can see these queries consist of pairs of messages, M0 and M1. As usual, they have to be the same length. And for each query, the attacker either gets the encryption of M0 or the encryption of M1. And the attacker can do this again and again. He can do this Q times. And at the end of the game, he's supposed to say whether he got the encryptions of the left messages or the encryptions of the right messages. So this is the standard chosen plaintext attack game, but now there's one extra caveat, which is to say that if the bit is equal to 0, if b is equal to 0, in other words, the attacker always sees the encryption of the left messages, then it so happens that the left messages must all be distinct. In other words, he will never get to see the encryption of the same message twice, because these left messages are always distinct. So if the bit b is equal to 0, again, he'll never see the same message encrypted under the same key, because again these 0 messages, M10 to MQ0, are all distinct. Similarly, we require that all the 1 messages are also distinct, and so that again if bit b happens to be equal to 1, the attacker will never see 2 messages encrypted under the same key. Okay, so this requirement that all these messages are distinct, and similarly all these Q messages are distinct, basically captures this use case that the encryptor will never encrypt the same message multiple times using one particular key. And as a result, the attacker simply can't ask for the encryption of the same message multiple times using the same key. Now I should point out, if you go back to the original attack here, so here we go back to our CPA attack on deterministic encryption, you notice that here, in fact, this is not a deterministic CPA game, because here the attacker did ask for the same message M0 to be encrypted twice. So in fact, this attack would be an illegal attack under the deterministic CPA game. And by ruling out this attack, we actually make it plausible that we might be able to give constructions that are deterministic CPA secure. And so as usual, we say if the adversary cannot distinguish experiment 0 when he's given the encryption of the left messages from experiment 1 when he's given the encryption of the right messages, then the scheme is semantically secure under a deterministic CPA attack. Okay, so as usual, we ask for what's the probability that the adversary outputs 1 in experiment 0, what's the probability that he outputs 1 in experiment 1, and if these probabilities are close, then his advantage in attacking the scheme is negligible, and if that's true for all efficient adversaries, then we say that the scheme is semantically secure under a deterministic CPA attack. So the first thing I want to do is show you the cipher block chaining with a fixed IV, in fact, is not deterministic CPA secure. And this is a common mistake that's used in practice. There are many products that should be using a cipher that's deterministic CPA secure, but instead they just use CBC with a fixed IV and assume that that's a secure mechanism. And in fact, it's not, and I want to show you why. So suppose we have a PRP that happens to operate on n-bit blocks, and we're going to use this PRP in CBC mode. So, if there are 5 blocks in the message, then this PRPE will be called 5 times to encrypt each one of those blocks. Okay, so here's how the attack's going to work. Well, the first thing the adversary is going to do is he's going to ask for the encryption of the message 0n, 1n. In other words, the first block is all zeros and the second block is all ones. So the left message is equal to the right message here, which means that he just wants the encryption of this 0 and 1 to the n message. So let's see what the ciphertext looks like. Well, for completeness, I'm going to write the IV, the fixed IV, as the first element in the ciphertext. And if you think about how CBC works, the second element in the ciphertext is going to be basically the encryption of the IV XOR the first block of the message. Well, in our case, the first block of the message is all zeros, so really all we're encrypting is just a fixed IV. So the second block of the ciphertext is simply going to be the encryption of this fixed IV. So next what the adversary is going to do is now he's going to output two messages that are a single block. So the first message is going to be, the message on the left is going to be the all zeros block, and the message on the right is going to be all ones block. So observe that this is a valid query because messages on the left are all distinct, and the messages on the right are also all distinct. So these are all valid deterministic CPA queries. Now what does the attacker get in response? Well, what he'll get in response is the following. If he gets the encryption of the message on the left, then, well, what's the encryption of the one block message 0 to the n? It's simply the encryption of the fixed IV, just as we saw before. However, if he's getting the encryption of the message on the right, well, that's going to be the encryption of 1 XOR the fixed IV. That's just the definition of CBC encryption. And now you can see basically how the attack is going to proceed. You notice if, here, I'll use a different color here. You notice if these two blocks happen to be the same, then we know that he received the encryption of the message on the left. In other words, b is equal to 0. If they're not the same, then he knows that b is equal to 1. Okay, so he's going to output 0 if, c of 1, which is this block, is equal to c1 of 1, which is this block, and he's going to output 1 otherwise. So this basically shows that CBC with a fixed IV is completely insecure. Basically, the first block can be very easily attacked, and in fact, if the messages are short, you can again build dictionaries and completely break systems that kind of use CBC with a fixed IV, hoping that it's going to be deterministic CPA secure. So don't do that. We're actually going to see secure deterministic CPA constructions in the next segment. So I'll say it one more time. If you need to encrypt a database index in a consistent manner, don't use CBC with a fixed IV to do it. Use the schemes that I'm going to show you in the next segment. And so let me ask you the same question about counter mode with a fixed IV. Is this going to be a deterministic CPA secure system or not? And here I'm reminding you what counter mode with a fixed IV is. Basically, we concatenate the fixed IV plus 1, fixed IV plus L. We encrypt all these counters. We concatenate the results. We encrypt the message to get the ciphertext. So do you think this is going to be deterministic CPA secure? So I hope everybody said no, because basically this is a one-time pad encryption, and if we use this one-time pad to encrypt distinct messages, basically we'll be getting a two-time pad. And to see it more precisely, here I wrote down the deterministic CPA game. So you notice what the attacker would do is he would start off by asking for the encryption of the message M. So he would get here the message M XOR the encryption of the fixed IV. And then he's going to ask for some two distinct messages, M0 and M1, that's different from M. So M, M0, and M1 all three are distinct messages. And then what he'll get is the encryption of MB, and now he can simply mount a standard kind of two-time pad attack. And if this equality here, if C XOR C prime is equal to M XOR M0, he knows that C prime is the encryption of M0. And otherwise, he knows that it's the encryption of M1. So again, he will completely win this game with advantage, as usual, with advantage equals to 1. Okay, so again, deterministic CPA with a fixed IV is also completely insecure as a deterministic CPA cipher. So don't use any of those schemes. Instead, let's use the schemes that I'm going to describe in the next segment. Now that we understand what is deterministic encryption, let's see some constructions that provide security against deterministic chosen plaintext attacks. So first, let me remind you that deterministic encryption is needed, for example, when encrypting a database index, and later we want to look up records using the encrypted index. Because the encryption is deterministic, we're guaranteed that when we do the lookup, the encrypted index is going to be identical to the encrypted index that was sent to the database when the record was written to the database. And so this deterministic encryption allows us a very simple and fast way to do lookups based on encrypted indices. The problem was that we said deterministic encryption can't possibly be secure against a general chosen plaintext attack, because if the attacker sees two ciphertexts that are equal, it learns that the underlying encrypted messages are the same. So then we defined this concept of deterministic chosen plaintext security, which means that we have security as long as the encryptor never encrypts the same message more than once using a given key. In particular, this key comma message pair is only used once. For every encryption, either the key changes or the message changes. And then, as I said, formally we define this CPA, deterministic CPA security game, and our goal in this segment is to actually give constructions that are deterministic CPA secure. So the first construction we're going to look at is what's called SIV, synthetic IVs. And the way this construction works is as follows. Imagine we have a general CPA-secure encryption system. So here is the key and here is the message, and I'm going to denote by R the randomness that's used by the encryption algorithm. Remember that a CPA-secure system that doesn't use nonces has to be randomized, and so we're explicitly going to write down this variable R to denote the random string that's used by the encryption algorithm as it's doing the encryption. For example, if we're using randomized counter mode, R would be the random IV that's used by randomized counter mode. And of course, C is the resulting ciphertext. Now, in addition, we're also going to need a pseudo-random function f that what it does is it takes arbitrary messages in the message space and outputs strings R that can be used as randomness for the CPA-secure encryption scheme. So the little r over here is actually a member of the big R set. Okay, and we're going to assume this is f is a pseudo-random function that maps messages to random string. Now the way SIV works is as follows. It's going to use two keys K1 and K2 to encrypt the message M. And what it does is the first thing is going to apply the pseudo-random function f to the message M to derive randomness for the CPA-secure encryption scheme E. And then it's going to encrypt the message M using the randomness that it just derived. And this is going to give us a ciphertext C, and then it's going to output this ciphertext C. Okay, so that's how this SIV mode works. Basically, it first derives the randomness from the message being encrypted, and then it uses this derived randomness to actually encrypt the message to obtain the ciphertext. Now, I'd like to point out, for example, if the encryption scheme E happened to be randomized counter mode, then the randomness R would just be the random IV, which would actually be output along with the ciphertext. So this means that the ciphertext is a little bit longer than the plain text. But the point here isn't to generate a short ciphertext. Rather, the point here is to make sure that the encryption scheme is deterministic. So if we encrypt the same message multiple times, every time we should obtain the same ciphertext. And indeed, every time we'll obtain the same randomness R. And as a result, every time we'll obtain the same ciphertext C. So it's fairly easy to show that this encryption scheme really is semantically secure under a deterministic chosen plaintext attack. The reason that's so is because we apply the pseudo-random function f to distinct messages. Well, if we apply f to distinct messages, then the random string that f generates is going to look like just truly random strings, a different random string for every message. And as a result, the CPA-secure encryption scheme E is always applied using truly random strings. And that's exactly the situation where it is CPA-secure. So because these R's are just random indistinguishable from random strings, the resulting system is in fact going to be CPA-secure. So this is just the intuition for why this works, and it's actually fairly straightforward to actually formalize this into a complete proof. Now, I should emphasize that this is actually well suited for messages that are more than one AES block. In fact, for short messages, we're going to see a slightly different encryption scheme that's actually better suited for these short messages. Okay, now the really cool thing about SIV is that actually we get ciphertext integrity for free. In fact, we don't have to use a special MAC if we want to add integrity. In a sense, SIV already has a built-in integrity mechanism. And let me explain what I mean by that. First of all, our goal is to build what's called Deterministic Authenticated Encryption, DAE, Deterministic Authenticated Encryption, which basically means deterministic CPA security and ciphertext integrity. Remember, ciphertext integrity means that the attacker gets to ask for the encryption of messages of his choice, and then he shouldn't be able to produce another ciphertext that decrypts to a valid message. Okay, so I want to claim that in fact SIV automatically gives a ciphertext integrity without the need for an embedded MAC or anything else. So let's see why. In particular, let's look at a special case of SIV when the underlying encryption scheme is randomized counter mode. Okay, so we'll call this SIV-CTR, again to denote SIV, where we're using randomized counter mode. Alright, so let me remind you again how SIV works in this case. Well, so we take our message, here we take our message, and then we apply a PRF to it, and that derives an IV, and then that IV is going to be used to encrypt the message using randomized counter mode. Okay, so in particular we're going to use this PRF FCTR for F counter for randomized counter mode, and essentially we evaluate this FCTR at IV plus 1, up to IV plus L, and then we XOR that with the message, and that gives us the final ciphertext. Okay, so this is SIV with randomized counter mode. Now let's see how decryption is going to work, and during decryption we're going to add one more check, and that's going to provide ciphertext integrity. So let's see how decryption is going to work. So here we have our input ciphertext, so it contains the IV and the ciphertext. Well, the first thing we're going to do is we're going to decrypt the ciphertext using the given IV, and that will give us candidate plaintext. Now we're going to reapply the PRF-F from the definition of SIV to this message. Now if the message is valid, we should be getting the same IV that the adversary supplied as part of the ciphertext. If we get a different IV, then we know that this message is not a valid message and we simply reject the ciphertext. So this is really cute. It's a very simple kind of built-in check to make sure that the ciphertext is valid, right? We simply check that after decryption, if we rederive the IV, we would actually get the correct IV. And if not, we reject the message. And I claim that this simple check during decryption is enough to actually provide ciphertext integrity and therefore deterministic authenticated encryption. So I'll state this in a simple theorem, basically to say that if F is a secure PRF and encounter mode that's derived from FCTR is CPA-secure, then the result, in fact, is a deterministic authenticated encryption system. Now, the proof for this is not too difficult. In 2 sentences, let me just show you the rough intuition for why this is true. So all we have to argue is just ciphertext integrity. So we already argued before that the system has deterministic CPA security. All we have to argue is just ciphertext integrity. So to argue that the system has ciphertext integrity, let's think again how the ciphertext integrity game works. Adversary asks for the encryption of a bunch of messages of his choice, and he gets the resulting ciphertexts, and then his goal is to produce a new valid ciphertext. Well, if that valid ciphertext, upon decryption, decrypts to some completely new message, then when we plug this new message into the PRF-F, we're just going to get some random IV, and it's very unlikely to hit the IV that the adversary supplied in the ciphertext that he output. So therefore, that says that when the adversary outputs his forged ciphertext, the message in that forged ciphertext basically should be equal to one of the messages in his chosen message queries. Otherwise, again, the IV that you get is simply not going to be equal to the IV in the forged ciphertext with very high probability. But if the message is equal to one of the messages that the adversary queried us on, well, then the ciphertext that we're going to get is also going to be equal to one of the ciphertexts that we supply to the adversary. But then his forgery is simply one of the ciphertexts that we gave to him, and therefore this is not a valid forgery. He has to give us a new ciphertext to win the ciphertext integrity game. But he gave us one of our old ciphertexts. So this is the rough intuition. I hope I kind of went through it quickly. I hope it kind of makes sense. If it doesn't, it's not the end of the world. I'm going to reference the paper that describes the SIV at the end of the module, and if you want to see this in more detail, you can read and take a look inside of that paper. But regardless, this is a very cute idea that I wanted to show you, where kind of the fact that we derive the randomness for deterministic counter mode using a PRF also gives us an integrity check when we actually do the decryption. Okay, so this SIV is a good mode for doing deterministic encryption when you need to, particularly if the messages are long. If the messages are very short, say they're less than 16 bytes, in fact there's a better way to do it, and that's the method that I want to show you now. So the second construction is actually trivial. All we're going to do is we're going to use a PRP directly. So here's what we do. So suppose ED is a secure PRP, so E will encrypt and D will decrypt. And I claim that if we use E directly, that already gives us deterministic CPA security. So let me show you very quickly why. So suppose F is a truly random invertible function from X to X. Okay, so remember a PRP is indistinguishable from a truly random invertible function, so let's pretend that we actually do have a truly random invertible function. Now in experiment 0, what the attacker is going to see, well, he submits a bunch of messages, you know, the messages on the left, and what he's going to see is basically the evaluation of F on the messages on the left that he supplied. Well, in the deterministic CPA game, all these messages are distinct, and so all he's going to get back are just Q distinct random values in X. That's all he sees. Yes, just Q distinct random values in X. Now let's think about experiment 1. In experiment 1, he gets to see the encryptions of messages on the right. Okay, the M11 to MQ1. Well, again, all these messages are all distinct, so all he gets to see are just Q random distinct values in X. Well, these two distributions in experiment 0 and experiment 1, therefore, are identical. Basically, in both cases, what he gets to see are just Q distinct random values in X. And as a result, he can't distinguish experiment 0 from experiment 1. And since he can't do this for a truly random function, he also can't do this for the PRP. Okay, so that explains why directly encrypting with a PRP already gives us a CPA-secure system, very, very, very simple to use. That says that if all we want to do is encrypt short messages, say less than 16 bytes, then all we need to do is just directly encrypt them using AES, and the result will in fact be deterministic CPA-secure. So if your indices are less than 16 bytes, directly using AES is a fine thing to do. Notice, however, that's not going to provide any integrity, and we're going to see how to add integrity in just a minute. But the question for you is, what do we do if we have longer than 16-byte messages? Well, one option is to use SIV, but what if we wanted to actually use this construction too? It's actually an interesting question. Can we construct PRPs that have message spaces that are bigger than just 16 bytes? If you remember, in the past, we constructed PRFs that had large message spaces from PRFs that had small message spaces. Here we're going to construct PRPs with large message spaces from PRPs with small message spaces. So let's see how to do it. So suppose EED is a secure PRP that operates on n-bit blocks. There's a standard mode called EME that actually will construct a PRP that operates on capital N-bit blocks, where capital N is much, much bigger than little n. So this would then allow us to do deterministic encryption on much larger messages than just 16 bytes. In fact, it could be as long as we want. So let's see how EME works. It's a bit daunting at first, but it's not a difficult construction. So let's see how it works. So EME uses two keys, K and L. And in fact, in the real EME, L is derived from K. But for our purposes, let's just pretend that K and L are two distinct keys. The first thing we do is we take our message X and we break it up into blocks. And then we XOR each block with a certain padding function. Okay, so we use the secret key L to derive a pad using this, function P that I'm not going to explain here. We derive a different pad for each one of the blocks, and we XOR that pad into the block. The next thing we do is we apply the PRP E using the key K to each one of these blocks, and we're going to call these outputs PPP0, PPP1, and PPP2. The next thing we do is we XOR all these PPPs together, and we call the result MP. Actually, this XOR doesn't need to be there. And we call the result of this XOR MP. The next thing we do is we XOR all these PPPs together, and we call the result MP. We encrypt this MP using E and the key K, and we call the output of this encryption MC. Okay, so then we XOR MP and MC, and this gives us another key M, which we use to derive one more pad, and then we XOR this output of this pad with all the PPPs to get these CCCs. Now we XOR all these CCCs together. That gives us a value CCC0, which we then encrypt one more time with all these E's. We do one more padding with all these P's, and that actually finally gives us the output of EME. Okay, so like I said, this may look a little daunting, but in fact there's a theorem that shows that if the underlying block cipher E is a secure PRP, then in fact this construction EME is a secure PRP on this larger block, 0, 1 to the capital N. The nice thing about this construction is you notice that it's very parallel, and actually that's why it's a little complicated. Kind of every block gets encrypted in parallel, so if you have a multi-core processor, you can use all your cores to encrypt all the blocks at the same time. And then there would be one kind of sequential step to compute this checksum on all the outputs, and then one more parallel round to encrypt one more time, and then finally you get the outputs. These function P's, by the way, that generate the pads are very, very simple functions. They take constant time, so we're just going to ignore them in terms of performance. So the bottom line is performance here, you notice, requires 2 applications of E per input block. And it turns out this can actually be slower than SIV. If SIV is implemented properly with a very fast PRF to derive the randomness, then in fact SIV can be twice as fast as this particular mode of operation. For this reason, I say that the PRP construction is very good for short messages, whereas SIV is good if you want to encrypt longer messages in a deterministic fashion. But now what if we wanted to add integrity to this PRP-based mechanism? So can we achieve deterministic authenticated encryption using the PRP mechanism, where we directly encrypt the message using a PRP? And it turns out the answer is yes, and it's actually, again, a very simple encryption scheme that you should know about. Basically what we're going to do is we're going to take our message and we're going to append a bunch of zeros to this message, and then we're going to apply the PRP, and that's it. And that's going to give us the ciphertext. Now, very, very simple. Just append zeros and encrypt using a PRP. When we decrypt, we're going to look at these least significant bits of the resulting plaintext, and if they're not equal to 0, we're just going to reject the ciphertext. And if they are equal to 0, we're going to output the message as valid. Okay, so that's it. That's the whole system. Very, very simple. Simply append zeros during decryption, and then check that the zeros are there when you decrypt. And I claim that this very simple mechanism actually provides deterministic authenticated encryption, assuming, of course, that you've appended enough zeros. In particular, if you append n zeros, we need 1/2 to the n to be negligible. And if so, then in fact, this direct PRP-based encryption, in fact, provides deterministic authenticated encryption. So let me see why. Well, we already argued that the system is CPA-secure, so all we have to argue is that it provides ciphertext integrity. And again, that's easy to see. Let's look at the ciphertext integrity game. So the adversary is going to choose, let's say, a truly random permutation, so a truly random invertible function on the input space. In this case, the input space is the message space and the n0 bits. And now what does the adversary get to do? Well, he gets to submit Q messages, and then he receives the encryption of those Q messages. Namely, he receives the PRP at his chosen points concatenated with n zeros. Okay, that's what it means to query the CPA challenger. So in case of a random permutation, he simply gets to see the value of this permutation at Q points of his choice, but only concatenated with n zeros. And now what's his goal in the ciphertext integrity game? Well, his goal is to produce some new ciphertext that's different from the ciphertext that he was given, that's going to decrypt properly. Well, what does it mean that it decrypts properly? It means that if when we apply pi inverse to the ciphertext C, it had better be the case that the n least significant bits of C are all zeros. And the question is, how likely is that to happen? Well, so let's think about this. Basically, we have a truly random permutation, and the adversary got to see the value of this permutation at Q points. How likely is he to produce a new point that, when inverted, happens to have n zeros as the least significant bits? What we're doing here is basically we're evaluating the permutation pi inverse at the point C. And since pi inverse is a random permutation, how likely is it to have its n least significant bits be equal to 0? So it isn't hard to see that the answer is, as at most, the probability is in most 1/2 to the n, because again, basically the permutation is going to output a random element inside of x times 0, 1 to the n, and that element is going to end with n zeros, but basically with a probability 1/2 to the n. And as a result, the adversary wins the game with negligible probability because this value is negligible. So that's the end of this segment. I wanted you to see these two very cute deterministic authenticated encryption schemes. The first one we called SIV, where say you would use randomized counter mode and you just derive the randomness for randomized counter mode from a PRF applied to the message. And the very cute idea here is that during decryption, you can simply recompute the IV from the decrypted message and verify that that IV is what's given to you in the ciphertext. And that simple check is actually enough to guarantee authenticated encryption, or rather deterministic authenticated encryption. So this mode is the way you would encrypt an index in a database if the index was large. If the index happens to be short, maybe say it's 8 bytes, if it's an 8-byte user ID, then you can directly use a PRP, and the way you would do it is you would append zeros to those 8 bytes, and then those zeros would then be used as an integrity check when you decrypt. And again, if you are able to append enough zeros, then in fact this also provides deterministic authenticated encryption. As an aside, I showed you that there's a way to build a wide block PRP from a narrow PRP, and that particular mode of operation is called EME. So we're going to refer to EME actually in the next segment. In this segment, we're going to look at another form of encryption called Tweakable encryption. I'm going to motivate Tweakable encryption using disk encryption as an application, and we'll see disk encryption as yet another application for deterministic encryption. So the disk encryption problem is that we want to encrypt sectors on disks. Say each sector is 4 kilobytes long. And the problem is that there's no space to expand. In other words, if the sector size is 4 kilobytes, the ciphertext size also has to be exactly 4 kilobytes because there's nowhere to write the extra bits if the ciphertext was bigger than the plaintext. And so our goal is basically to build non-expanding encryption where the ciphertext size is identical, exactly equal to the plaintext size. So what does it mean that encryption can't expand? Well, technically we're saying basically the message space is equal to the ciphertext space. So the message space would be 4 kilobyte messages, and the ciphertext space would be also 4 kilobyte messages. In this case, clearly we have to use deterministic encryption because if encryption was randomized, there would be no place to store the randomness. And similarly, we have no room for integrity because we can't expand the ciphertext and add any integrity bits. So the most we can achieve is deterministic CPA security. And that's going to be our goal. Now, it turns out there's a really simple lemma to prove that basically says that if you give me a deterministically CPA secure cipher where the message space is equal to the ciphertext space, so no expansion, then in fact the cipher is a PRP. So really all we're saying here is if we want no expansion at all, our only option for encrypting is what we called construction number 2 in the previous segment. Namely, we have to encrypt using a PRP. So let's look at how we might encrypt using a PRP. Well, we take our disk and we break it into sectors. And now if we encrypted every sector using a PRP under the same key, we kind of run into our standard problem with deterministic encryption. Namely, if sector 1 and sector 3 happen to have the same plaintext, then the encrypted sector 1 would be equal to the encrypted sector 3, and the attacker would learn that the corresponding plaintexts are the same. Now, this actually is a real problem. For example, if some of your sectors are empty, they're all set to 0, then in fact the encrypted sectors would be identical, and as a result the attacker would know exactly which sectors on your disk are empty and which sectors are not. So this is actually quite problematic, and the question is, can we do any better? And so the answer is yes, and the first idea that comes to mind is, well, why don't we use a different key for every sector? So you can see sector number 1 gets encrypted with K1, sector number 2 gets encrypted with K2, and so on and so forth. So now even if the content of sector number 1 is equal to sector number 3, the ciphertext of sector 1 and sector 3 will be different because they're encrypted under different keys. So this actually avoids the leakage that we talked about before, although I do want to point out that there's still a little bit of leakage with this mode. For example, if the user happened to change 1 bit in sector 1, and then that sector gets encrypted into a different ciphertext, so this will be garbled all completely because this is a pseudo-random permutation, the sector will be, even if 1 bit of the plaintext changes, the sector will be just mapped to a completely new random output. However, if the user then undoes the change and reverts back to the original sector, then the encrypted sector will revert back to its original state, and the attacker can tell that a change was made and then reverted. So there's still a little bit of information leakage, but that type of information leakage, there's really nothing we can do without really sacrificing performance. So we're just going to ignore that and deem that acceptable. So the next question is, now you realize our disks are actually getting pretty big and there are lots of sectors, so this would mean that we're generating lots and lots of keys here. But of course, we don't have to store all these keys. We can simply generate these keys using a pseudo-random function. So the way this would work is we would have a master key, which we would call K, and then the sector number, which I'm going to denote by T, is going to be encrypted using the master key, and the result of that encryption would be the particular sector key, which I'll denote by K sub T. Now the reason this is secure is again because the PRF is indistinguishable from a random function, which means that basically if we apply a random function to these sector numbers 1, 2, 3, 4 up to L, they basically get mapped to completely random elements in the key space, and as a result we're encrypting every sector using a new random independent key. So this is a fine construction. However, again, for every sector we would have to apply this PRF. And so the natural question is, can we do even better? And it turns out we can, and this introduces this concept of a tweakable block cipher, where really what we want is basically to have one master key, and we want this one master key to derive many PRPs. So we said one way to do that is simply encrypt the key K using the PRP number. But as we'll see, there's a more efficient way to do that. Now this PRP number is actually what's called a tweak, and that introduces this concept of a tweakable block cipher. So in a tweakable block cipher, the encryption and decryption algorithm basically, as usual, take a key as input. They take a tweak as input. This capital T is what's called the tweak space. And of course, they take the data as input and they output data in the set X. The property is that for every tweak in the tweak space and a random key, basically if we fix the key in the tweak, then we end up with an invertible function, a one-to-one function on the set X. And because the key is random, with the function is in fact indistinguishable from random. In other words, for every setting of the tweak, we basically get a PRP, an independent PRP from x to x. And as I said, the application for this is now we're going to use the sector number as the tweak, and as a result, every sector is going to get its own independent PRP. So let me very, very quickly just define more precisely what is a secure tweakable block cipher. So as we said, there's a tweak space, there's a key, a tweak space, and an input space x, and as usual, we define our two experiments. Here in experiment 1, what's going to happen is we're going to choose a truly random set of permutations. So not just one permutation, we're going to choose as many permutations as there are tweaks. So you notice this is why we raise this to the size of the tweak space. If the size of the tweak space is 5, this says that we're choosing 5 random permutations on the set X. And in the other case, basically, we're just going to choose a random key, and we're going to define our set of permutations as the ones defined by the tweaks in the tweak space. And now the adversary basically gets to submit a tweak and an x, and he gets to see the value of the permutation defined by the tweak T1 evaluated at the point x1. And he gets to see this again and again. Again, he gets to see the value of the permutation defined by the tweak T2 evaluated at the point x2. And so on and so forth. And then his goal is to say whether he interacted with truly random permutations or pseudo-random permutations. And if he can't do it, we say that this tweakable block cipher is secure. So the difference from a regular block cipher is in a regular block cipher, you only get to interact with one permutation, and then your goal is to tell whether you're interacting with a pseudo-random permutation or a truly random permutation. Here you get to interact with t-random permutations, and again your goal is to tell whether the t-random permutations are truly random or pseudo-random. So as usual, if you can't distinguish if the adversary behaves the same in both experiments, we say that this PRP is a secure tweakable PRP. Okay, very good. So let's look at some examples. So we already looked at the trivial example. In the trivial example, what we do, we're going to assume that the key space is equal to the input space. So this PRP really acts on x times x to x. So think of AES, for example, where the key space is 128 bits, the data space is 128 bits, and of course the output is 128 bits. And then the way that we define the tweakable block cipher, again, there's a key, a tweak, and data as input, is basically we encrypt the tweak using our master key, and then we encrypt the data using the resulting random key. Now you realize that if we wanted to encrypt n blocks with this tweakable block cipher, this would require 2 n evaluations of the block cipher. N evaluations to encrypt the given tweaks, and then n more evaluations to encrypt the actual given data. So I want to show you a nice example that shows that we can actually do better. This is called the XTS construction. It's actually originally based on a mode called XEX due to Faragaway. And it works as follows. So suppose you give me a regular block cipher that operates on n-bit blocks. So not a tweakable block cipher, just a regular block cipher. We're going to define a tweakable block cipher. So again, this tweakable block cipher is going to take 2 keys as input. The tweak space, for convenience, which you're going to see in just a minute, we're going to assume this tweak space is made up of 2 values, t and I. T is going to be some tweak value, which we'll see in a minute, and I is going to be some index. And then x is going to be an n-bit string, which we're going to apply the tweakable block cipher to. So the way XTS works is as follows. The first thing we're going to do is we're going to encrypt the left half of the tweak, namely t, using the key k2, and we're going to call the result n. So now what we're going to do is we're going to XOR the message m with some padding function applied to this value n that we just derived at the index I. And this padding function is extremely fast. We can pretty much ignore it in the running time. The next thing we do is we're going to encrypt using the key k2. And then we're going to XOR again using the same pad. So we're going to XOR again using the pad of n applied to I. And the result is going to be the ciphertext, which we'll denote by C. Okay, so again, as I said, the function p is some very, very simple function. It's just some multiplication in a finite field, which I'm not going to explain here. Very, very fast. So the running time is really dominated by the running time of the block cipher E. And that's it. That's XTS. And the nice thing about this construction is now if we wanted to encrypt n plus 1 blocks, all we do is we compute the value n once, and then for the indices 1, 2, 3, 4, basically we just need to evaluate the PRPE once per block. So we would need to encrypt n blocks using the tweaks t, 1, t, 2, t, 3, t, 4, and so on. We would just need n plus 1 evaluations of the block cipher E. So it's twice as fast as the trivial construction. So I want you to stare for just a minute at this XTS construction. So my question to you is it really necessary to encrypt the tweak before using it? That is the following construction a secure tweakable PRP? So you can see in this construction the tweak is used directly as input to the padding function for the XOR, and my question to you is if we did that, would that be a secure tweakable PRP? Now let me remind you again that this is the key, this is the tweak, and this is the data. I hope everybody said that this is the correct answer. Basically, if we set the data to be pt, 1, then when we XOR it with the corresponding tweak, which is also pt, 1, we're going to get here 0. And so what's going to get encrypted is actually 0. So whatever that comes out to be, let's say that's some value C0. And then the actual output is going to be C0 XOR PT1. Now when we do the same thing with PT2, we're going to get C0 XOR PT2. And when we XOR these two things together, we just get PT1 XOR PT2. So the fact that this is true means that an attacker can simply query the challenger at this tweak and this data, this tweak and that data, and then just compute the XOR of the two responses and compare to the XOR of the appropriate padding values. And if the equality holds, we're interacting with a pseudo-random function. Otherwise, we're interacting with a truly random function. So this would allow the attacker to defeat this construction with advantage 1. So just to summarize, the way XTS is used for disk encryption, what we do is we look at sector number T and we break it into blocks, 16-byte blocks, and then block number 1 gets encrypted with a tweak T1. Block number 2 gets encrypted with a tweak T2, and so on and so forth. And so every block gets its own PRP, and the whole sector as a result is encrypted using a collection of PRPs. Now you notice this is a block level PRP, it's not a sector level PRP. So in fact, it's not true that each sector gets encrypted with its own PRP, it's just each block gets encrypted with its own PRP. The distinction between a sector and a block is somewhat artificial, and this XTS mode actually provides deterministic CPA encryption at the block level, at the 16-byte level. That's the goal. And this mode actually is fairly popular in disk encryption products. I just wrote a couple of examples here that actually support XTS. So I wanted you to know that this, in fact, is how disk encryption is commonly done in practice. So to summarize, tweakable encryption is a useful concept to know when you need many independent PRPs, all derived from a single key. One important thing to remember is, in fact, the trivial construction is not the most efficient. There are constructions like XTS are actually more efficient, where you can kind of reuse encryptions from one tweak to get many encryptions for many different tweaks. And so those are the better ways to use them. Both the trivial construction and the XTS construction are what are called narrow block constructions. Namely, they provide a tweakable block ciphers for a 16-byte block. But as we said, we looked at the EME construction in the last segment, which provided a PRP for much larger blocks. And in fact, EME is a tweakable mode of operation. So if you need PRPs for larger blocks or tweakable PRPs for larger blocks, then you would just use EME. But you notice there in EME, you had to apply the block cipher twice per input block. And as a result, it's twice as slow as XTS and is not very often used. So that's what I wanted to say about tweakable encryption. And in the next segment, we'll talk about format preserving encryption. In this segment, I want to tell you about another form of encryption called format preserving encryption. This is again something that comes up in practice quite often, especially when it comes to encrypting credit card numbers. And so let's see how it works. Remember that a typical credit card number is 16 digits broken into 4 blocks of 4 digits each. You've probably heard before that the first 6 digits are what's called the BIN number, which represent the issuer ID. For example, all credit cards issued by Visa always start with the digit 4. All credit cards issued by MasterCard start with digits 51 to 55, and so on and so forth. The next 9 digits are actually the account number that is specific to the particular customer, and the last digit is a checksum that's computed from the previous 15 digits. So there are about 20,000 BIN numbers, and so if you do the calculation, it turns out there are about 2 to the 42 possible credit card numbers, which corresponds to about 42 bits of information that you need to encode if you want to represent a credit card number compactly. Now the problem is this. Suppose we wanted to encrypt credit card numbers so that when the user swipes the credit card number at the point of sale terminal, namely at the the merchant's cash register, the cash register, this is called a point of sale terminal, goes ahead and encrypts the credit card number using a key K, and it's encrypted all the way until it goes to the acquiring bank, or maybe even beyond that, maybe even all the way when it goes to Visa. Now the problem is that these credit card numbers actually pass through many processing points. All of them expect to get something that looks like a credit card number as a result. So if we simply wanted to encrypt something at the endpoint, at one endpoint, and decrypt it at the other endpoint, it's actually not that easy, because if all we did was encrypt it using AES, even if we just use deterministic AES, the output of the encrypted credit card number would be a 128-bit block, 16 bytes, that would need to be sent from one system to the next until it reaches its destination. But each one of these processors then would have to be changed, because they're all expecting to get credit card numbers. And so the question is, can we encrypt at the cash register such that the resulting encryption itself looks like a credit card number, and as a result none of these intermediate systems would have to be changed? Only the endpoints would have to be changed. In doing so, we would actually obtain end-to-end encryption without actually having to change a lot of software along the way. So the question then is, again, can we have this mechanism called format-preserving encryption, where encrypting a credit card itself produces something that looks like a credit card? So that's our goal. The encrypted credit card number should look like a regular valid credit card number. So this is the goal of format-preserving encryption. More abstractly, what it is we're trying to do is basically build a pseudo-random permutation on the set 0 to s-1 for any given s. So for the set of credit card numbers, s would be roughly 2 to the 42. In fact, it's going to be not exactly 2 to the 42. It's going to be some funny numbers that's around 2 to the 42. And our goal is to build a PRP that acts exactly on the interval 0 to s-1. And what we're given as input is some PRF, say something like AES, that acts on much larger blocks, say acts on 16-byte blocks. So we're trying to, in some sense, shrink the domain of the PRF to make it fit the data that we're given. And the question is basically how to do that. Well, once we had such a construction, we can easily use it to encrypt credit card numbers. What we would do is we would take a given credit card number, we would encode it such that now it's represented as a number between 0 and the total number of credit card numbers. Then we would apply our PRP so that we would encrypt this credit card number, using construction number 2 from the deterministic encryption segment. And then we would map the final number back to look like a regular valid credit card number, and then send this along the way. Since this is again non-expanding encryption, the best we can do, as we said before, is to encrypt using a PRP, except again the technical challenge is we need a PRP that acts on this particular funny looking set from 0 to s-1 for this pre-specified value of s. So my goal is to show you how to construct this, and once we see how to do it, you will also know how to encrypt credit card numbers so that the resulting ciphertext is itself a credit card number. So the construction works in 2 steps. The first thing we do is we shrink our PRF from the set 0,1 to the n, say 0,1 to the 128 in the case of AES, to 0,1 to the t, where t is the closest power of 2 to the value s. So say s is some crazy number around 2 to the 41, t would basically be then 42, because that's the closest power of 2 that's just above the value of s. So the construction is basically going to use the Luby-Rokov construction. What we need is a PRF f prime that acts on blocks of size 2 over 2. So imagine, for example, in the credit card case, t would be 42, because 2 to the 42 we said is the closest power of 2 that's bigger than s. S is the total number of credit cards. Then we would need a PRF now that acts on 21-bit inputs. So one way to do that is simply take the AES block cipher, treat it as a PRF on 128-bit inputs, and then simply truncate the output to the least significant 21 bits. Okay, so we would, given a 21-bit value, we would append zeros to it so that we get 128 bits as a result. We would apply AES to that, and then we would truncate back to 21 bits. Now, I should tell you that that's actually a simple way to do it, but it's actually not the best way to do it. There are actually better ways to truncate a PRF on n bits to a PRF on 2 over 2 bits. But for the purposes of this segment, the truncation method I just said is good enough. So let's just use that particular method. Okay, so now we've converted our AES block cipher into a PRF on 2/2 bits, say on 21 bits, but what we really want is a PRP, and so what we'll do is we'll plug our new PRF F prime directly into the Luby-Rokov construction. If you remember, this is basically a Feistel construction. We saw this when we talked about DES. It's a Luby-Rokov used 3 rounds, and we know that this converts a secure PRF into a secure PRP on twice the block size. In other words, we started from a secure PRF on 21 bits, and that will give us, and Luby-Rokov will give us a secure PRF on 42 bits, which is what we wanted. Now, I should tell you that the error parameters in the Luby-Rokov construction are not as good as they could be, and in fact, a better thing to do is to use 7 rounds of Feistel. So in other words, we'll do this 7 times. Every time we'll use a different key. So you notice here we're only using 3 keys. We should be doing this 7 times using 7 different keys. And then there's a nice result due to Pataran that shows that the 7-round construction basically has as good an error terms as possible. So the error terms in the security theorem will basically be 2 to the t. Okay, so now we have a pseudo-random permutation that operates on close power of 2 to the value of s. But that's not good enough. We actually want to get a pseudo-random permutation on the set 0 to s-1. So step 2 will take us down from 0, 1 to the t to the actual set 0 to the s-1 that we're interested in. And this construction is, again, really, really cute, so let me show you how it works. So again, we're given this PRP that operates on a power of 2, and we want to go down to a PRP that operates on something slightly smaller. Okay, so here's how the construction works. Basically, we're given input x in the set 0 to s-1 that we want, and what we're going to do is we're going to iterate the following procedure again and again. So first of all, we map x into this temporary variable y, and now we're just going to encrypt the input x and put the result into y. If y is inside of our target set, we stop and we output y. If not, we iterate this again, and again and again and again and again until finally y falls into our target set, and then we output that value. So in a picture, let me explain how this works. So we start from a point in our target set, and now we apply the function e, and we might be mapped into this point outside our target set. So we're not going to stop. So now we apply the function e again, and we might be mapped into this point, and now we apply the function e again, and now all of a sudden we mapped into this point, and then we stop. And that's our output. Okay, so that's how we map points from 0 to s-1 to other points in 0 to s-1. It should be pretty clear that this is invertible. To invert, all I'll do is I'll just decrypt and walk kind of in the opposite direction. So I'll decrypt, and then decrypt, and then decrypt, until finally I fall into the set 0 to s-1, and that gives me the inverse of the point that I wanted to. So this is in fact a PRP. The question is whether it's a secure PRP, and we'll see that in just a minute. But before that, let me ask you, how many iterations do you expect that we're going to need? And I want to remind you again, before I ask you that question, that in fact s is less than 2 to the t, but is more than 2 to the t minus 1. So in particular, s is greater than 2 to the t over 2. And my question to you now is, how many iterations are we going to need on average until this process converges? So the answer is we're going to need 2 iterations, so really just a small constant number of iterations, and so this will give us a very, very efficient mechanism that will move us down from 0, 1 to the t to 0 to the s-1. So now when we talk about security, it turns out this step here is tight. In other words, there is really no additional security cost to going down from 2 to the t to 0 to s-1. And the reason that's true, it's actually, again, a very cute theorem to prove, but I won't do it here, or maybe I'll leave it as an exercise for you guys to argue, which says that if you give me any 2 sets y and x where y is contained inside of x, then applying the transformation that we just saw to a random permutation from x to x actually gives a random permutation from y to y. So this means that if we started with a truly random permutation on x, you'll end up with a truly random permutation on y, and since the permutation we're starting with is indistinguishable from random on x, we'll end up with a permutation that's indistinguishable from random on y. Okay, so this is a very tight construction, and as I said, the first step actually is basically the analysis is the same as the Luby-Rokov analysis. In fact, it's better to use, as I said, the Pataran analysis using 7 rounds, and so actually here there's a bit of cost in security. But overall, we get a construction that is secure PRP for actually Not such good security parameters, but nevertheless this is a good secure PRP that we can construct that actually will operate on the range 0 to s-1, and this in turn will allow us to encrypt credit card numbers such that the ciphertext looks like a credit card number. And again, I want to emphasize is there's no integrity here. The best we can achieve here is just deterministic CPA security, no ciphertext integrity, and no randomness at all. Okay, so this concludes this module, and as usual I want to point to a few reading materials that you can take a look at if you're interested in learning more about anything that we discussed in this module. So first of all, the HKDF construction that we talked about for key derivation is described in a paper from 2010 by Hugo Kravchuk. Deterministic encryption, the SIV mode that we described, is discussed in this paper over here. The EME mode that we described that allows us to build a wide block pseudo-random permutation is described in this paper here by Halevi and Ragaway. Tweakable block ciphers that actually led to the XDS mode of operation that's used for disk encryption is described in this paper here. And finally, format preserving encryption is described in this last paper that I point to over here. Okay, so this concludes this module, and in the next module we're going to start looking at how to do key exchange. Now that we know how two users can protect data using a shared secret key, the next question is how did these two users generate a shared secret key to begin with? This question will take us into the world of public key cryptography. In this module we will look at a few toy key exchange protocols as a way to introduce the main ideas of public key cryptography. We're going to come back and talk about key exchange and design secure key exchange protocols after we build a few more public key tools. So imagine for a second that there are n users in the world, and the question is how do these users manage these secret keys that they're going to use to communicate with one another? So for example, let's assume n equals 4 and there are 4 users in the world. One option is that basically every pair of users will share a shared secret key. So for example, U1 and U3 will share a shared secret key. I'll call it K13. U1 and U2 will share a shared secret key. We'll call it K12, and so on and so forth. K24, K34, and so on and so forth. K14, and finally K23. The problem with this approach is that now there are many shared keys that users have to manage, and in particular every user has to store in the order of n keys if he's going to talk to n other parties in this world. So the question is, can we do any better than storing n keys per user? And the answer is yes, and one way to do that is what's called an online trusted third party. I'll use TTP to denote a trusted third party. So the way we're going to use a trusted third party is every user will now share a single key with this trusted third party. So user 1 will share a secret key, user 2 will share a secret key, and here are our friends Alice and Bob. Let's call their secret keys K sub A and K sub B. Okay, so now the nice thing about this design is that now every user only has to remember one secret key. The question is now, what happens when Alice wants to talk to Bob? Somehow the two of them have to engage in a certain protocol such that at the end of this protocol they will have a shared secret key, KAB, that the attacker wouldn't be able to know. And so the question is, how do Alice and Bob generate this shared secret key, KAB? So let's look at an example toy protocol for doing that. So here we have our friends Alice and Bob. As usual, Bob has his key KB, which is shared with a trusted third party. Alice here has her secret key KA, which is also shared with a trusted third party. So here the trusted third party has both KA and KB. And the question is, how do they generate a shared key that they both agree on, but the attacker would have no idea what this shared key is? So here we're only going to look at a toy protocol. In particular, this protocol is only going to be secure against eavesdropping. It's not going to be secure against more tampering or active attacks. As I said, we're going to come back and design secure key exchange protocols later on in the course. But for now, just to introduce this idea of key exchange, let's look at the simplest mechanism that's only secure against eavesdropping. So in other words, adversary that listens to the conversation won't know what the shared key KAB is going to be. And so the protocol works as follows. Alice is going to start by sending a message to the trusted third party saying, hey, I want a secret key that's going to be shared with Bob. What the trusted third party will do is it will actually go ahead and choose a random secret key, KAB. So the trusted third party is the one who's going to generate their shared secret key. And what it will do with this key is the following. It's going to send one message back to Alice, but this message consists of two parts. The first part of the message is an encryption using Alice's secret key, using the key KA of the message. This key is supposed to be used between parties Alice and Bob, and she includes the secret key KAB inside of this message. Okay, so just to be clear, what's happening here is that the message that gets encrypted is the key KAB, plus the fact that this key is supposed to be a shared key between Alice and Bob. Okay, and this whole message is encrypted using Alice's secret key. The other part of the message that the TTP sends to Alice is what's called a ticket. And this ticket is basically a message that's encrypted for Bob. So in other words, the ticket is going to be an encryption under the key KB of, again, the fact that this key is supposed to be used between Alice and Bob, and she concatenates to that the secret key KAB. Okay, so again, the message that's encrypted inside of the ticket is the fact that this key is to be used by Alice and Bob, and the secret key KAB is included in the ticket as well. Okay, so these two messages, here let me circle them, these two messages are sent from the trusted third party to Alice. Now I should mention that the encryption system E that's actually being used here is a CPA-secure cipher, and we'll see why that's needed in just a minute. So this is the end of the conversation between Alice and this trusted third party. Basically, as we said, at the end of this conversation, Alice receives one message that's encrypted for her, and another message called a ticket that's encrypted for Bob. Now, at a later time, when Alice wants to communicate securely with Bob, what she will do is, of course, she will decrypt her part of the message. In other words, she will decrypt the ciphertext that was encrypted using the key KA, and now she has the key KAB. And then to Bob, she's going to send over this ticket. Bob is going to receive the ticket, and he's going to use his own secret key KB to decrypt, and then he himself will also recover the secret key KAB. So now they have this shared secret key, KAB, that they can use to communicate securely with one another. And the first question to ask is, why is this protocol secure, even if we only consider eavesdropping adversaries? So let's think about that for a minute. So at the moment, all we care about is just security against an eavesdropper. So let's think, what does an eavesdropper see in this protocol? Well, basically, he sees these two ciphertexts, right? He sees the ciphertext that's encrypted for Alice, and then he sees the ticket that's encrypted for Bob. And in fact, he might see many instances of these messages. In particular, if Alice and Bob continuously exchange keys in this way, he's going to see many messages of this type. And our goal is to say that he has no information about the exchange key KAB. So this follows directly from the CPA security of the cipher ED, because the eavesdropper can't really distinguish between encryptions of the secret key KAB from encryption of just random junk. That's the definition of CPA security. And as a result, he can't distinguish the key KAB from, random junk, which means that he learns nothing about KAB. This is kind of a very high-level argument for why this is eavesdropping security, but it's enough for our purposes here. So the bottom line is that in this protocol, the eavesdropper would actually have no information about what KAB is, and therefore it's okay to use KAB as a secret key to exchange messages between Alice and Bob. Now let's think about the TTP for a minute. So first of all, you notice that the TTP is needed for every single key exchange. Basically, Alice and Bob simply cannot do key exchange unless the TTP is online and available to help them do that. And the other property of this protocol is that, in fact, the TTP knows all the session keys. So if somehow the TTP is corrupt, or maybe it's broken into, then an attacker can very easily steal all the secret keys that have been exchanged between every user of this system. This is why this TTP is called a trusted third party, because essentially it knows all the session keys that have been generated in the system. Nevertheless, the beauty of this mechanism is that it only uses symmetric key cryptography, nothing beyond what we've already seen, and as a result, it's very fast and efficient. The only issue is that you have to use this online trusted party, and it's not immediately clear if, for example, we wanted to use this in the World Wide Web, who would function as this online trusted third party. However, in a corporate settings, this might actually make sense. If you have a single company with a single point of trust, it might make sense to actually designate a machine as a trusted third party. And in fact, a mechanism like this, not quite as the way I described it, but a mechanism like this is the basis of the Kerberos system. So this is our first example of a key exchange protocols that allow Alice and Bob to set up shared keys. However, I really want to point out that this is just a toy protocol, very, very simple, and is only secure against eavesdropping attack. It's actually completely insecure against an active attacker. And here's a very simple example of how an active attacker might destroy this protocol. And so let's just look at replay attacks. So here imagine the attacker records the conversation between Alice and some online merchant. what's called a merchant Bob. So for example, imagine Alice orders a book from the merchant Bob, and the transaction completes, and Bob accepts payment for this book and actually sends Alice a copy of this book. What an attacker can do now, he can completely record the conversation and simply replay the conversation to merchant Bob at a later time. Bob will think that Alice just reordered another copy of the book, and he'll charge her again for it and send her this copy again. So essentially, by replaying a conversation, you can cause quite a bit of harm to Alice, and as a result, this is a simple example of why this protocol is completely insecure against active attacks and should never be used in the real world. As I said, we're going to come back in a few weeks and talk about secure versions of this protocol, and you'll see how to make this work in the real world. Nevertheless, you see that this very simple protocol already raises a very interesting question. And the question is, can we basically design key exchange protocols, whether they're secure against eavesdropping or secure against active attackers? The question is, can we design key exchange protocols that are secure but work without an online trusted third party? So we don't want to rely on any online trusted party that's necessary to complete the key exchange protocol. And so the amazing answer is that, in fact, this is possible. We can do key exchange without a trusted third party, and this is, in fact, the starting point of public key cryptography. So I'm going to show you 3 ideas for making this happen, and we're going to talk about them in much more detail in the coming modules. So the first idea is actually due to Ralph Merkle back in 1974. This was when he was just an undergraduate student, and already he came up with this really nice idea for key exchange without an online trusted third party. So that's one example that we're going to look at. Another example is due to Diffie-Hellman back in 1976. They both actually working here at Stanford University came up with this idea that launched the world of modern key cryptography. And the third idea is due to Ravesh, Shamir, and Adelman working at MIT, and we're going to look in detail exactly how each of these ideas work. But I do want to mention that the work on public key management hasn't stopped in the late 70s. In fact, there have been many ideas over the years, and here I'll just mention 2 from the last decade. One is called identity-based encryption, which is another way for managing public keys, and another is called functional encryption, which is a way of giving secret keys that only partially decrypt a given ciphertext. And so we're going to talk about the core of public key crypto in this and the next week, and we'll talk about these more advanced ideas later on in the course. In this segment, we're going to look at our first key exchange protocol without a trusted third party. So the settings are, we have our friends Alice and Bob as usual, and these friends have never met before, but somehow they want to generate a shared key. So what they're going to do is they're going to send messages to one another back and forth, and this time there's no trusted third party that they can communicate with. And at the end of this protocol, somehow they should have a shared key that they both know. So there's a secret key K that they both know. But an eavesdropper who listens in on this traffic has absolutely no idea what this secret key K is. Now, for now, we're just going to worry about attackers that only eavesdrop on the conversation. In other words, we don't allow any tampering with traffic. All we allow is just eavesdropping. And yet the eavesdropper should have no idea what the secret key K is. And so we're going to look at a number of key exchange protocols in these settings, namely when the attacker is only eavesdropping on the conversation but cannot change traffic. And we're going to see 3 protocols that achieve this goal. And the first question, though, for this segment is, can this be done only using symmetric crypto? So can this only be done using block ciphers or hash functions or any of the tools that we've seen in the last 4 weeks? And so very surprisingly, the answer is yes. In fact, we can do key exchange just using block ciphers or hash functions without a trusted third party, but unfortunately the resulting protocols are very inefficient and are actually never used in practice. Nevertheless, these are very simple protocols, and so I want to show you how they work, and then we'll move on to the more efficient protocols that we'll discuss this week and the next. So the simple protocol I want to show you is what's called a Merkle Puzzles protocol. This protocol was invented by Ralph Merkle back in 1974 when he was just an undergraduate. Interestingly, he invented this protocol as part of a seminar that he took, but apparently the professor didn't quite understand the significance of the contribution, and as a result, Ralph Merkle actually graduated and then moved to Stanford, where he became Marty Hellman's student, and they've done a lot of good things in public key cryptography since then. So let me show you how Merkle puzzles work. The main tool for this protocol is what's called a puzzle, and let me explain what I mean by a puzzle. Well, a puzzle is a problem that's difficult to solve, but can be solved with some effort. In other words, if you really put your mind to it, you can solve it. And so let me give you an example. So suppose we have a symmetric cipher that uses keys that are 128 bits long. So just think of AES, for example. And suppose what I do is I choose an AES key such that the first 96 bits are all 0, and only the remaining 32 bits are non-zero and just chosen at random. Okay, so only 32 bits of this 128-bit key are random, the rest are all 0. And now what I do is I encrypt a fixed plaintext, for example, simply the plaintext message, using this 128-bit key that happens to be mostly 0. The result is what I would call a puzzle, and the reason I call it a puzzle is because it's actually not that hard to find the secret key P simply by trying all 2 to the 32 possibilities. Remember, these are the first 96 bits are all 0, so there are really only 2 to the 32 possible keys to try. And for each key, we'll try to decrypt this puzzle and see if we get the plaintext message, and if so, we know that we've recovered the right solution P. So within 2 to the 32 work, we can actually solve this puzzle, namely we can find P just given puzzle P. So the way this is going to work is as follows. Alice is going to start by generating a large number of puzzles. In particular, she's going to generate 2 to the 32 different puzzles. Now, each of these puzzles, the way she generates it is as follows. What she'll do is she'll choose a 32-bit random puzzle PI. Okay, she does this for I equals 1 to 2 to the 32. And then she's going to choose 2 more values, xi and ki, that happen to be 128 bits each. Now, what she'll do is she'll use the puzzle PI as an AES secret key. Okay, so she'll create a 128-bit key where 96 of the bits are set to 0, and only the 32 least significant bits happen to be random. Okay, so this is a key that only has 32 bits of entropy, if you like, and there are only 2 to the 32 such keys. Now, the plaintext that she'll encrypt using this key is this message that I wrote over here. Basically, it starts off with the word puzzle. That puzzle is identified by the identifier xi, which happens to be 128 bits, and to that we concatenate the value ki, which also happens to be 128 bits. Okay, so she does this for all 2 to the 32 puzzles, and as a result, she gets 2 to the 32 different puzzles. She then goes ahead and sends these 2 to the 32 puzzles to Bob. Now, what does Bob do? Well, Bob receives this flood of 2 to the 32 different puzzles. He's just going to choose one of them. He doesn't even have to remember any of them. He just randomly lets most of them go by, and he happens to choose one of them. Let's say he chose puzzle number J. Then he spends time 2 to the 32 and solves this puzzle. Well, what does it mean to solve this puzzle? He's going to try all possible values of PI. He's going to decrypt the puzzle that he chose, and he's going to check whether the first part of the plaintext starts with the word puzzle. And if it does, he knows that he's correctly solved that puzzle, and then he basically obtains the data embedded in the puzzle, namely xj and kj. Okay, so remember, xj is this value that identifies the puzzle, and kj is going to be a secret that they use. So now he solved the puzzle. He knows that he solved the puzzle correctly, and he obtained this xj and kj. What he'll do is he'll send xj back to Alice, just the value xj. Kj he keeps for himself and keeps it a secret. And then Alice is simply going to look up in her database of puzzles, she's going to look up puzzle number xj, and then she knows that Bob chose the key kj, and now they have this shared key. So kj is going to be the shared key that they use to communicate securely with one another. So in a diagram, the way this protocol works is as follows. Alice starts off by sending 2 to the 32 puzzles to Bob, so we can generalize this. Let's say that she sends n puzzles to Bob, and let's say that each puzzle takes work proportional to n to solve. Bob solves one of these puzzles, and then he sends back xj to Alice. Okay, so far each one of them spent work n, and then Alice basically looks up puzzle xj and recovers the key that corresponds to this puzzle, and as a result, both of them now have a shared key that they can use to communicate with one another. Okay, so let's look at the work that they did. So what the work that Alice did is she had to prepare n puzzles. Well, preparing a puzzle takes constant time. She had to prepare n puzzles, so her work is roughly order n. Bob chose one puzzle and solved it, so his work is also proportional to order n, so linear in n. So now let's see what the eavesdropper has to do. Well, the poor eavesdropper sees these n puzzles go by, and then he sees this xj come back, and he doesn't really know which puzzle Bob actually solved. All he sees is this random value inside of the puzzle. And so to break this protocol, the eavesdropper would actually have to solve all puzzles until he finds the right puzzle that has the value xj in it, and then he will recover kj. So my question to you is, what is the attacker's work? How much work did the eavesdropper have to spend to break this protocol? So the answer is, of course, order n squared, quadratic time in n. He had to solve n puzzles. Each puzzle takes time n to solve, and as a result, he had to spend time order n squared. In our example, we said that there were 2 to the 32 puzzles, and each one took 2 to the 32 time to solve. So overall, the attacker's work is roughly 2 to the 64 steps. So you can see the problem with this protocol. First of all, the participants, Alice and Bob, had to do quite a bit of work themselves. If you think about it, Alice basically had to send 2 to the 32 puzzles to Bob. That's many, many gigabytes that she had to send to Bob, like 16 or 32 gigabytes, depending on how big each puzzle is. Bob had to spend time 2 to the 32 to solve one of these puzzles, so that would take a few seconds too. But then all the security they got is that the attacker can break this protocol in time 2 to the 64. So 2 to the 64 is still not considered particularly secure. As a result, the attacker really, if he really wanted to break this protocol, he could. So to make this secure, the participants would have to increase the parameter n, and they would have to send, say, 2 to the 64 puzzles to one another, and then spend time 2 to the 64 to solve each puzzle, and then the attacker's work would be 2 to the 128, which is considered secure. But having the participants spend time 2 to the 64 to set up a secure session is a little bit too much to ask each of these participants. So this is why this protocol is not particularly used in practice. But nevertheless, there's a really nice idea here in that the participants had to spend linear time where the attacker had to spend quadratic time. So there's a quadratic gap between the amount of work that the participants had to do versus what the attacker had to do to break the protocol. So a natural question is, can we actually do better than a quadratic gap just using symmetric ciphers? In other words, just using tools that we developed in the first 4 weeks of the class. And the answer really is that this is unknown. We don't know whether a quadratic gap is the best that we can do. You might even try to think about this a bit. How would you use AES or SHA-256 to do key exchange that achieves better than a quadratic gap? But I can tell you that we believe that quadratic is the best we can do, and there are even some negative results along those lines. So roughly speaking, there is a result that says that in fact, if we treat the block cipher or the hash function that we use as a black box oracle, in other words, all the participants can do is just query the block cipher or query the hash function at certain points and receive the results. If that's all they're allowed to do, in other words, they're not allowed to actually use the implementation of the cipher or the hash function, then in fact there is a result that says that if the participants only query the block cipher at n points, there will always be an attack that runs in time n squared. So again, this suggests that if all you do is use the block cipher as a black box that you query, then whatever key exchange you come up with, there will always be a quadratic attack on this key exchange. And in fact, at the end of this module, I point to this paper. It's a fairly recent paper from 2009 that shows that quadratic is the best we can do. So if you want to read more about this impossibility result, go ahead and take a look at this paper. It's actually a very readable paper, and you should be able to understand it. And so the question is what to do next. So now we're kind of stuck. We said that with block ciphers, we really can't do better than a quadratic gap. And so what do we do? So this was kind of the starting point of public key cryptography, and the realization is that we need more than just generic block ciphers and generic hash functions. We actually need functions that have very, very special properties. And to build these functions, we actually have to rely on some algebra. So in the next few segments, we're going to look at some algebraic constructions, and then we'll see how to use those for key exchange and for many other things in public key cryptography. In this segment, we're going to look at the Diffie-Hellman Protocol, which is our first practical key exchange mechanism. So let me remind you of the settings. Our friends here, Alice and Bob, have never met, and yet they want to exchange a shared secret key that they can then use to communicate securely with one another. In this segment and the next, we're only going to be looking at eavesdropping security. In other words, we only care about eavesdroppers. The attackers are actually not allowed to tamper with data in the network. They're not allowed to inject packets. They're not allowed to change packets in any way. All they do is they just eavesdrop on the traffic. And at the end of the protocol, the key exchange protocols, our friends Alice and Bob should have a shared secret key, but the attacker, namely the eavesdropper, has no idea what that key is going to be. In the previous segment, we looked at a key exchange mechanism called Merkle Puzzles that's just using block ciphers or hash functions, and I showed you that there the attacker basically has a quadratic gap compared to the participants. In other words, if the participants spend time proportional to n, the attacker can break the protocol in time proportional to n squared. And as a result, that protocol is too insecure to be considered practical. In this segment, we're going to ask whether we can do the same thing, but now we'd like to achieve an exponential gap between the attacker's work and the participant's work. In other words, Alice and Bob might do work proportional to n, but to break the protocol, the attacker is going to have to do work proportional to some exponential in n. So now there's an exponential gap between the participant's work and the attacker's work. So as I said in the previous segment, we can't achieve this exponential gap from block ciphers like AES or SHA-256. We have to use hard problems that have more structure than just those symmetric primitives. And so instead, what we're going to do is use a little bit of algebra. In this segment, I'm going to describe the Diffie-Hellman protocol very concretely and somewhat informally. We're going to come back to Diffie-Hellman next week, and we're going to describe the protocol more abstractly, and we're going to do a much more rigorous security analysis of this protocol. Okay, so how does Diffie-Hellman work? What we're going to do is, first of all, we're going to fix some large prime, which I'm going to call P. Actually, P I'll usually use to denote primes. And you should be thinking of really gigantic primes, like primes that are made up of 600 digits or so. And just for those of you who like to think in binary, a 600-digit prime roughly corresponds to about 2,000 bits. So just writing down the prime takes about 2 kilobits of data. And then we're also going to fix an integer g that happens to live in the range 1 to p. So these values p and g are parameters of the Diffie-Hellman protocol. They're chosen once and they're fixed forever. Now the protocol works as follows. So here are our friends Alice and Bob. So what Alice is going to do is she's going to start off by choosing some random number a in the range 1 to p minus 1. And then she's going to compute the number g to the power of a modulo p. Okay, so she computes this exponentiation and reduces the result modulo the prime p. And we're actually going to see how to compute this efficiently in the next module. So for now, just believe me that this computation can be done efficiently. And let's call capital A the result of this value. So what Alice will do is she'll send capital A over to Bob. Now Bob is going to do the same thing. He's going to choose a random number b in the range 1 to p minus 1. He's going to compute g to the b modulo p. And let's call this number b. And he's going to send this number b over to Alice. So Alice sends a to Bob. Bob sends b to Alice. And now I claim that they can generate a shared secret key. So what's the shared secret key? Well, it's defined as, let's call it KAB. And it's basically defined as the value g to the power of a times b. Now, the amazing observation that Diffie and Hellman had back in 1976 is that, in fact, both parties can compute this value g to the ab. So let's see. So Alice can compute this value because she can take her value b that she received from Bob. She can take this value b and raise it to the power of a. And let's see, what she'll get is g to the b to the power of a. And by the rules of exponentiation, g to the power of b to the power of a is equal to g to the ab. Bob, turns out, can do something similar. So his goal is to compute g to the a to the b, which again is g to the ab. So both Alice and Bob will have computed KAB. And let me ask you, how does Bob actually compute this quantity g to the ab? Well, so all he does is he takes the value a that he received from Alice, and he raises it to his own secret b, and that gives him the shared secret g to the ab. So you can see now that both parties, even though they seemingly computed different values, in fact they both end up with the same value, namely g to the ab modulo p. I should mention, by the way, that Marty Hellman and Whit Diffie came up with this protocol back in 1976. Marty Hellman was a professor here at Stanford, and Whit Diffie was his graduate student. They came up with this protocol, and this protocol really changed the world in that it introduced this new age in cryptography, where now it's not just about designing block ciphers, but it's actually about designing algebraic protocols that have properties like the one we see here. So you notice that what makes this protocol works is basically properties of exponentiation, namely that g to the b to the power of a is the same as g to the a to the power of b. Okay? These are just properties of exponentiations. Now, when I describe a protocol like the one I just showed you, the real question that should be in your mind is not why the protocol works. In other words, it's very easy to verify that, in fact, both Alice and Bob end up with the same secret key. The bigger question is, why is this protocol secure? In other words, why is it that an eavesdropper cannot figure out the same shared key, g to the ab, that both Alice and Bob computed by themselves. So let's analyze this a little bit, and like I said, we're going to do a much more in-depth analysis next week, but let's for now just see intuitively why this protocol is going to be secure. Well, what does the eavesdropper see? Well, he sees the prime and the generator. These are just fixed forever and everybody knows who they are. He also sees the value that Alice sent to Bob, namely this capital A, and he sees the value that Bob sent to Alice, namely this capital B. And the question is, can the eavesdropper compute g to the AB just given these four values? So more generally, what we can do is we can define this Diffie-Hellman function. So we'll say that the Diffie-Hellman function is defined based some value g. And the question is, given g to the A and g to the B, can you compute g to the AB? And what we're asking is, how hard is it to compute this function modulo a very large prime p? Remember, p was something like 600 digits. So the real question we need to answer is, how hard is this Diffie-Hellman function? So let me show you what's known about this. So suppose the prime happens to be n bits long. Okay, so in our case, say n is 2,000 bits. It turns out the best known algorithm for computing the Diffie-Hellman function is actually a more general algorithm that computes the discrete log function, which we're going to talk about next week. But for now, let's just say that this algorithm computes a Diffie-Hellman function. The algorithm is called a general number field sieve. I'm not going to describe how it works, although if you'd want to hear how it works, let me know, and that could be one of the special topics that we cover at the end of the course. But the interesting thing is that its running time is exponential in roughly the cube root of n. In other words, the running time is roughly e to the power of O of cube root of n. So in fact, the exact expression for the running time of this algorithm is much more complicated than this. I'm deliberately simplifying it here just to kind of get the point across. The point that I wanted to emphasize is that in fact, this is not quite an exponential time algorithm. Exponential would be e to the power of n. This is sometimes called a sub-exponential algorithm because the exponent is really just proportional to the cube root of n, as opposed to linear in n. What this says is that even though this problem is quite difficult, it's not really an exponential time problem. The running time in the exponent is going to be just proportional to the cube root of n. So let's look at some examples. Suppose I happen to be looking at a modulus that happens to be about 1,000 bits long. What this algorithm says is that we can solve the Diffie-Hellman problem in time that's approximately e to the cube root of 1024. Now this is not really correct. In fact, there are more constants in the exponents, but again, just to get the point across, we can say that the running time would be roughly e to the cube root of 1024, which is actually very small, roughly e to the 10. So the simple example shows you that if you have a sub-exponential algorithm, you see that even if the problem is quite large, like 1,000 bits, because of the cube root effect, the exponent actually is not that big overall. Now, to be honest, I'm actually lying here. General number field sieve actually has many other constants in the exponents. So in fact, this is not going to be 10 at all. It's going to be actually something like 80 because of various constants in the exponent. But nevertheless, you see that the problem is much harder than, say, 2 to the 1,000. So this is, even though describing the problem takes 1,000 bits, solving it does not take time 2 to the 1,000. So here I wrote down a table that kind of shows you the rough difficulty of breaking the Diffie-Hellman protocol compared to the difficulty of breaking a cipher with an appropriate number of bits. So for example, if your cipher has 80-bit keys, that will be roughly comparable to using a 1,000-bit modulus. In other words, breaking a cipher with 80-bit keys takes time roughly 2 to the 80, which means that breaking the Diffie-Hellman function with a 1,000-bit modulus would take roughly time 2 to the 80. If your cipher uses 128-bit keys like AES, you should be really using a 3,000-bit modulus, even though nobody really does this. In reality, people would use 2,000-bit modulus. And then if your key is very large, like if you're using a 256-bit AES key, then in fact your modulus needs to be very, very large. Again, you can really see the cube root effect here. We double the size of our key, and because of the cube root effect, what that means is we have to increase the size of our modulus by a factor of 2 cubed, namely a factor of 8. Which is where this 15,000 comes from. And again, I should mention that it's not exactly a factor of 8 because of the extra constants in the exponent. So this is a nice table that shows you that if you're going to be using Diffie-Hellman to exchange a session key, and that session key is going to be used for a block cipher with a certain key size, this table shows you what modulus size you need to use so that the security of the key exchange protocol is comparable to the security of the block cipher you're going to be using after. Now, this last row should really be disturbing to you. I should tell you that working with such a large modulus is very problematic. This is actually going to be quite slow. And so the question is whether there's anything better that we can do. And it turns out there is. In fact, the way I described the Diffie-Hellman function is I described it at the way Diffie and Hellman described it back in 1976 using arithmetic modulo primes. The problem with arithmetic modulo primes is that the Diffie-Hellman function is hard to compute, but it's not as hard as you'd like. There's this cube root effect that makes it a little easier than what you'd really like. And so the question is, can we run the Diffie-Hellman protocol in other settings? And it turns out the answer is yes. In fact, we can literally translate the Diffie-Hellman protocol from arithmetic modular primes to a different type of algebraic object. And solving the Diffie-Hellman problem on that other algebraic object is much, much harder. This other algebraic object is what's called an elliptic curve. And as I said, computing the Diffie-Hellman function on these elliptic curves is much harder than computing Diffie-Hellman modulo primes. Because the problem is so much harder, now we can use much smaller objects. In particular, we'd be using primes that are only 160 bits for 80-bit keys, or only 512 bits for 256-bit keys. So because these moduli don't grow as fast on elliptic curves, there's generally a slow transition away from using modular arithmetic to using elliptic curves. I'm not going to describe elliptic curves right now for you, but if this is something you'd like to learn about, I can do that in the very last week of the course when we discuss more advanced topics. But in fact, when we come back to Diffie-Hellman next week, I'm going to describe it more abstractly so that it really doesn't matter which algebraic structure you use, whether you use arithmetic modular primes or whether you use elliptic curves. We can kind of abstract that whole issue away and then use the Diffie-Hellman concept for key exchange and for other things as well. And as I said, again, we'll see that more abstractly next week. So as usual, I want to show that this beautiful protocol that I just showed you, the Diffie-Hellman protocol, is actually completely insecure against an active attack. Namely, is completely insecure against what's called a man-in-the-middle attack. We need to do something more to this protocol to make it secure against man-in-the-middle. And again, we're going to come back to Diffie-Hellman and make it secure against man-in-the-middle next week. Okay, so let's see why the protocol that I just showed you is insecure against active attacks. Well, suppose we have this man in the middle that's trying to eavesdrop on the conversation between Alice and Bob. Well, so the protocol starts with Alice sending G to the A over to Bob. Well, so the man in the middle is going to intercept that, and he's going to take the message that Alice sent, and he's going to replace it with his own message. So let's call this A prime, and let's write that as G to the A prime. Okay, so the man in the middle chooses his own A prime, and what he sends to Bob is actually G to the A prime. Now, poor Bob doesn't know that the man in the middle actually did anything to this traffic. All he sees is he got the value A prime. As far as he knows, that value came from Alice. So what is he going to do in response? Well, he's going to send back his value B, which is G to the B, back to Alice. Well, again, the man in the middle is going to intercept this B. He's going to generate his own B prime, and what he actually sends back to Alice is B prime, which is G to the B prime. Okay, now what happens? Well, Alice is going to compute her part of the secret key, and she's going to get G to the A B prime. Bob is going to compute his part of the secret key, and he's going to get G to the B times A prime. Okay, these, now you notice, these are not the same keys. And the man in the middle, because he knows both A prime and B prime, he can compute both G to the A B prime and G to the B A prime. Yeah, it's not difficult to see. The man in the middle knows both values, and as a result, now he can basically play this man in the middle, and when Alice sends an encrypted message to Bob, the man in the middle can simply decrypt this message because he knows the secret key that Alice encrypted the message with, re-encrypt it using Bob's key, and then send the message on over to Bob. In this way, Alice sent a message to Bob, Bob received that message, he thinks that the message is secure, but in fact that message went through the man in the middle decrypted it, re-encrypted it for Bob, and at the same time he was able to completely read it, modify it if he wants to, and so on. So the protocol becomes completely insecure given a man in the middle. And so as I said, we're going to have to enhance the protocol somehow to defend against man in the middle, but it turns out it's actually not that difficult to enhance and prevent man in the middle attacks. And we're going to come back to that and see that in a week or two. The last thing I want to do is show you an interesting property of the Diffie-Hellman protocol. In fact, I want to show you that this protocol can be viewed as a non-interactive protocol. So what do I mean by that? So imagine we have a whole bunch of users, millions of users. Let's call them Alice, Bob, Charlie, David, and so on and so forth. Each one of them is going to choose a random secret value. And then on their Facebook profiles, they're going to write down their contribution to the Diffie-Hellman Protocol. Okay, so everybody just writes down, G to the A, G to the B, G to the C, and so on. Now, the interesting thing about this is if, say, Alice and Charlie want to set up a shared key, they don't need to communicate at all. Basically, Alice would go and read Charlie's public profile. Charlie would go and read Alice's public profile. And now, boom, they immediately have a secret key. Namely, now Alice knows G to the C and A. Charlie knows G to the A and C. And as a result, both of them can compute G to the AC. So in some sense, once they've posted their contributions to the Diffie-Hellman protocol to their public profiles, they don't need to communicate with each other at all to set up a shared key. They immediately have a shared key, and now they can start communicating securely through Facebook or not with one another. And notice that this is true for any Facebook user. So as soon as I read somebody's public profile, I immediately have a shared key with them without ever communicating with them. This property is sometimes called a non-interactive property of Diffie-Hellman. So now let me show you an open problem. And this is an open problem that's been open for ages and ages and ages. So it'd be really cool if one of you can actually solve it. The question is, can we do this for more than two parties? In other words, say we have 4 parties. All of them post their values to their Facebook profiles. And now we'd like to make it that just by reading Facebook profiles, all of them can set up a shared secret key. In other words, Alice is what she'll do is she'll only read the public profiles of the 3 friends, Bob, Charlie, and David, and already she can compute a shared key with them. And similarly, David is just going to read the public profile of Charlie, Bob, and Alice, and already he has a shared key with all 4 of them. Okay, so the question is whether we can kind of set up non-interactively these shared keys for groups that are larger than just 2 people. So as I said, for n equals 2, this is just a Diffie-Hellman protocol. In other words, if just 2 parties want to set up a shared key without communicating with one another, that's just Diffie-Hellman. It turns out for n equals 3, we also know how to do it. There's a known protocol. It's called a protocol due to Zhu. It already uses very, very fancy mathematics, much more complicated mathematics than what I just showed you. And for n equals 4, 5, or anything above this, above 4, this problem is completely open. Namely, the case where 4 people post something to the public profiles, and then everybody else reads the public profiles, and then they have a joint shared key. This is something we don't know how to do even for 4 people. And this is a problem that's been open for ages and ages. It's kind of a fun problem to think about, and so see if you can solve it. If you will, it's instant fame in the crypto world. Okay, so I'll stop here, and we'll continue with another key exchange mechanism in the next segment. In this module, I want to show you another approach to key exchange based on the concept of public key encryption. So again, just to remind you of the settings, we have our friends Alice and Bob as usual, and their goal is to exchange a secret key K. The eavesdropper gets to see the messages they send to one another, but even though he shouldn't learn anything about the key K that they exchanged. And as usual, in this module, we're only going to be looking at eavesdropping security. That is, we don't allow the attacker to tamper with data or to mount any other form of active attack. So just to remind you, earlier in this module, we saw an inefficient mechanism based on generic block ciphers. In the previous segment, we saw the Diffie-Hellman key exchange mechanism, which has an exponential gap between the work that the participants have to do versus the work that the attacker has to do. And in fact, this Diffie-Hellman protocol is used all over the web very frequently. In this segment, I want to show you a different approach based on public key encryption. So what is public key encryption? So just as in the case of symmetric encryption, there's an encryption algorithm and a decryption algorithm. However, here, the encryption algorithm is given one key, which we're going to call a public key. Let's call this the public key that belongs to Bob. And the decryption algorithm is given a different key. We'll call it a secret key that also belongs to Bob. So these two keys are sometimes called a key pair. One half of the pair is the public key, and the other half of the pair is the secret key. Now, the way you encrypt is as usual. A message would come in. The encryption algorithm would generate a ciphertext that is the encryption of this message using the given public key. And then when the ciphertext is given to the decryption algorithm basically outputs the corresponding message. So as I said, PK is called the public key and SK is called the secret key. So more precisely, what is public key encryption? Well, public key encryption is actually made up of three algorithms, G, E, and D. Algorithm G is what's called a key generation algorithm. When you run algorithm G, it will output two keys, the public key and the secret key. The encryption algorithm, basically given the public key and the message, will output the corresponding ciphertext. And the decryption algorithm, given the secret key and the ciphertext, will output the message, or it will output bottom if an error occurred. And as usual, we have the usual consistency properties that say that for any public key and secret key that could have been output by the key generation algorithm, if we encrypt the message using the public key and then decrypt using the secret key, we should get the original message back. Now, what does it mean for a public key system to be secure? Well, we use the same concept of semantic security that we used before, except the games now are a little bit different. So let me explain how we define semantic security for a public key system. So here, the challenger is going to run the key generation algorithm to generate a public key and a secret key pair, and he's going to give the public key to the adversary. The challenger keeps the secret key to himself. What the adversary will do is he will output two equal length messages, M0 and M1, as before, and then the challenger will give him the encryption of M0 or M1. As usual, we define two experiments, experiment 0 and experiment 1. In experiment 0, the adversary is given the encryption of M0. In experiment 1, the adversary is given the encryption of M1. And then the adversary's goal is to guess which encryption he was given. Was he given the encryption of M0 or was he given the encryption of M1? And we refer to his guess as the output of experiment 0 or experiment 1. One thing I want to emphasize is that in the case of public key encryption, there's no need to give the attacker the ability to mount a chosen plaintext attack. Why is that? Well, in the case of a symmetric key system, the attacker had to request the encryption of messages of his choice. In the case of a public key system, the attacker has the public key and therefore he can by himself encrypt for himself any message that he wants. He doesn't need the challenger's help to create encryptions of messages of his choice. And as a result, in the public key settings, a chosen plaintext attack is inherent. There's no reason to give the attacker extra power to mount a chosen plaintext attack. And that's why we never discuss chosen plaintext queries in the context of defining semantic security for public key systems. Now that we defined the game, we're going to say that a public key system, GED, is semantically secure if basically the attacker cannot distinguish experiment 0 from experiment 1. In other words, the adversary's probability of outputting 1 in experiment 0 is about the same as his probability of outputting 1 in experiment 1. So again, the attacker can't tell whether he was given the encryption of M0 or the encryption of M1. Now that we understand what public key encryption is, let's see how to use it to establish a shared secret. So here are our friends Alice and Bob. Alice will start off by generating a random public key secret key pair for herself using the key generation algorithm. And then she's going to send to Bob the public key PK. And she also says, hey, this message is from Alice. What Bob will do is he will generate a random 128-bit value X, and he will send back to Alice saying, hey, this message is from Bob, and he'll send back the encryption of X under Alice's public key. Alice will receive the ciphertext, she'll decrypt it using her secret key, and that will give her the value X. And now this value X can be used basically as a shared secret between the two of them. I want to emphasize that this protocol is very different from the Diffie-Hellman Protocol that we saw in the last segment, in the sense that here the parties have to take turns, in the sense that Bob cannot send his message until he receives the message from Alice. In other words, Bob cannot encrypt X to Alice's public key until he receives the public key from Alice. In the Diffie-Hellman protocol, however, the two parties could send their messages at arbitrary times, and there was no ordering enforced on those messages. As a result, we had this nice application of Diffie-Hellman where everybody could post their messages to Facebook, for example, and then just by looking at Facebook profiles, any pair would already have a shared key without any need for additional communication. Here, this is not quite true. Even if everybody posts their public keys to Facebook, there would still be a need to send this message before a shared key can be established. So now that we understand the protocol, the first question we need to ask is, why is this protocol secure? And as usual, we're only going to look at eavesdropping security. So in this protocol, the attacker gets to see the public key and the encryption of X under the public key, and what he wants to get is basically this value X. Now, we know that the public key system that we used is semantically secure. What that means is that the attacker cannot distinguish the encryption of X from the encryption of something random. In other words, just given encryption of X, the attacker can't tell whether the plaintext is X or just some random junk that was chosen from M. And because of that, that basically says that just by looking at messages in this protocol, the value of X is indistinguishable in the attacker's view from a random element in M, and as a result, X can be used as a session key between the two parties. It's just a random value which the attacker cannot actually guess, other than by trying all possible values in M. And I should say that showing that these two distributions are indistinguishable follows directly from semantic security, and in fact it's a simple exercise to show that if the attacker could distinguish this distribution from that distribution, then the attacker could also break semantic security. And as usual, even though this protocol is secure against eavesdropping, it's completely insecure against the man-in-the-middle attack. So let's see a simple man-in-the-middle attack. Well, so here we have Alice generating her public key-secret key pair. At the same time, the man in the middle is also going to generate his own public key secret key pair. And now when Alice sends her public key over to Bob, the man in the middle will intercept that, and instead he'll say, yeah, this is a message from Alice, but Alice's public key really is PK prime. So now Bob receives this message, he thinks he got a message from Alice. What he'll send back is, well, he's going to choose his random X, and he'll send back the encryption of X under PK prime. The man in the middle is going to intercept this message, and he's going to replace it with something else. So his goal is to make sure that the key exchange succeeds. In other words, Alice thinks that she got a message from Bob, and yet the man in the middle should know exactly what the exchange secret is. So what should the man in the middle send to Alice in this case? So here, let's call the ciphertext C. What the man in the middle will do is he will decrypt the ciphertext C using his own secret key, and that will reveal X to the man in the middle. And then he's going to go ahead and encrypt X under Alice's public key, send the value back to Alice. Alice will obtain this X, and as far as she's concerned, she just did a key exchange with Bob, where both of them learned the value X. But the problem, of course, is that the man in the middle also knows the value X. So this protocol becomes completely insecure once the man in the middle can tamper with messages from Alice to Bob and from Bob to Alice. So again, we have to do something to this protocol to make it secure, and we're going to see how to do that actually in 2 weeks after we introduce digital signatures. So now that I've shown you that public key encryption implies key exchange secure against eavesdropping, the next question is how do we construct public key encryption systems? And it turns out that these constructions generally rely on number theory and some algebra, and just like the Diffie-Hellman Protocol relied on some algebra. And so before we go into these protocols in more detail, what I'd like to do is kind of take a quick detour. In the next module, we're going to look at the relevant number theoretic background. We'll just do one module on this, and then we'll come back and talk about these public key constructions and more constructions for key exchange. So this is the end of this module, and as further reading, I just wanted to point to this paper that shows that if in fact all we do is rely on symmetric ciphers and hash functions, then Merkle puzzles are optimal for key exchange, and in fact we cannot achieve more than a quadratic gap as long as we treat the primitives we're given as a black box. So basically this shows that a quadratic gap is the best possible. And also I wanted to point to another paper that kind of summarizes some of these key exchange mechanisms that we talked about, key exchange using public key cryptography and key exchange using Diffie-Hellman. You can take a look at this paper, and it kind of will give you a look ahead into what's coming and how to make these key exchange protocols secure against man in the middle and not just secure against eavesdropping. Okay, so that's the end of this module, and the next module will take a brief detour and do a kind of a brief overview of algebra and number theory. In the last module, we saw that number theory can be useful for key exchange. In this module, we will review some basic facts from number theory that will help us build many public key systems next week. As we go through the material in this module, it might help to pause the video from time to time to make sure all the examples are clear. So as I said, we're going to use number theory to build key exchange protocols, we're going to use number theory to build digital signatures, public key encryption, and many, many other things. But before we can do all that, we have to review some basic facts from number theory, and in fact in this module we're going to do a quick course on the relevant concept. If you'd like to review some of the material discussed in this module offline, I reference at the end of the module a free textbook by Victor Shoup, and I point to some specific chapters in this book that will explain the material that we will cover here. So from here on I'm going to use the following notation. I'm going to use capital N to always denote a positive integer, and I'm going to use lowercase p to always denote a positive prime number. Now I'd like to introduce the following notation. There's this funny z that's written like two diagonal lines here with a subscript n. I'm going to use that to denote the set 0, 1, 2, up to n minus 1. This is actually very common notation that's used in crypto, and so I'll stick to that here. So again, z sub n denotes the set of integers 0, 1, up to n minus 1. And in fact, this is not just a set of integers. We can do addition and multiplication in this set as long as we always multiply modulo the number n. For those of you who know a little bit of algebra, I'll just say that z sub n denotes a ring where addition and multiplication are done modulo n. This is very common notation in crypto, although in modern mathematics, z sub n sometimes denotes something else. But as I said, I'm going to keep on using z sub n to denote the set of integers 0 to n minus 1 with addition and multiplication modulo n. So I want to make sure everybody is comfortable with modular arithmetic. And so let's just look at the number, say, n equals 12. And let's just see some basic facts about modular arithmetic. So I'm going to say that 9 plus 8 is 17. 17 is 5 modulo 12. So I'm going to write that 9 plus 8 is equal to 5 in Z12. Now, can someone tell me how much is 5 times 7 in Z12? In other words, how much is 5 times 7 modulo 12? Well, 5 times 7 is 35. And if you recall, 36 is divisible by 12. So 5 times 7 is really minus 1 modulo 12. 35 is minus 1 modulo 12. But minus 1 modulo 12 is basically the same as 11, because I just add 12 to minus 1 and I get 11. And the next question is, how much is 5 minus 7 in Z12? Well, 5 minus 7 is minus 2. Minus 2 modulo 12, well, I just add 12 to minus 2 and I get 10. As a result, we say that 5 minus 7 is equal to 10. So again, this is just to make sure everybody's comfortable with this notation of working in Z12. In other words, working modulo 12. Now, I'd just like to make a general statement that, in fact, arithmetic in Zn, in other words, arithmetic modulo n, works just as you would expect. So, for example, all the laws that you know about addition and multiplication work equally well in Zn. For example, the distributive law, x times y plus z, is still going to be equal to x times y plus x times z. So many of the things that you know about arithmetic when working over the integers or in the reals will translate to working in Zn, namely working modulo n. So the next concept we need is what's called a greatest common divisor, or a GCD. And so suppose I give you two integers x and y. We say that the GCD of x and y is basically the greatest common divisor. It's the largest number, the largest integer that divides both x and y. So for example, what is the GCD of 12 and 18? Well, the GCD is 6 because 6 divides both 12 and 18, and it's the largest number that divides both 12 and 18. Now, there's an important fact about GCDs. In particular, if I give you two numbers, two integers x and y, there will always exist two other integers, I'll call them a and b, such that if I look at a times x plus b times y, what I get is the GCD of x and y. In other words, the GCD of x and y is a linear combination of x and y using the integers a and b. So let's just look at a simple example. Here, let's look at our GCD from before. So the integers for this GCD would be 2 times 12 minus 1 times 18. That's 24 minus 18, which is equal to 6. So the integers a and b in this case would be 2 and minus 1. But this is just an example, and in fact these integers a and b will exist for any integers x and y. Now, not only do a and b exist, in fact there's a very simple and efficient algorithm to find these integers, to find a and b. The algorithm is what's called the extended Euclidean algorithm. This is actually one of the prettiest algorithms from ancient Greek times. due to Euclid, of course. I'm not going to show you how this algorithm works here. It's a fairly simple algorithm. I'll just tell you that, in fact, given x and y, this algorithm will find a and b in time roughly quadratic in the logarithms of x and y. And we'll come back to that and discuss the performance of Euclid's algorithm in a bit more detail in just a minute. But for now, all we need to know is that a and b can actually be found efficiently. Now, if the GCD of x and y happens to be 1, in other words, 1 is the largest integer that divides both x and y, then we say that x and y are relatively prime. For example, the GCD of 3 and 5, it's not difficult to see that that happens to be 1 because both 3 and 5 are prime. The next topic we need to talk about is modular inversion. So over the rationals, we know what the inverse of a number is. In other words, if I give you the number 2, the inverse of 2 is simply the fraction 1/2. The question is, what about inverses when we work modulo n? Well, so the inverse of an element x in Zn is simply another element y in Zn, such that x times y is equal to 1 in Zn. In other words, x times y is equal to 1 modulo n. And this number y is denoted by x inverse. And it's not difficult to see that if y exists, then in fact it's unique. And as I said, we'll use x inverse to denote the inverse of x. So let's look at a quick example. Suppose n is some odd integer, and I ask you what is the inverse of 2 in Zn. So it's not too difficult to see that the inverse of 2 in Zn, in fact, is n plus 1 over 2. And you can see that this is an integer because n is odd, therefore n plus 1 is even, and therefore n plus 1 over 2 is in fact an integer in the range 1 to n as required. Now why is n plus 1 over 2 the inverse of 2? Well, let's just multiply the 2. So we do 2 times n plus 1 over 2. And what do we get? Well, that's simply equal to n plus 1, and n plus 1 is simply equal to 1 in Zn. So since their product is equal to 1, we know that n plus 1 over 2 is the inverse of 2 in Zn. Now that we understand what a modular inverse is, the question is which elements actually have an inverse in Zn. And so there's a very simple lemma that says that if for an element x in Zn, that element has an inverse if and only if it is relatively prime to the modulus n, to the number n. So I'll say that again. X in Zn is invertible if and only if x is relatively prime to n. Now let's quickly prove that. It's actually fairly simple to see. So suppose the GCD of x and n happens to be equal to 1, so x is relatively prime to n. Well, by this property of GCDs, we know that there exist integers a and b, such that a times x plus b times n is equal to the GCD of x and n, which happens to be 1. So a times x plus b times n is equal to 1. Now, we can actually take this equation here and reduce it modulo n. So what this means is that a times x is equal to 1 in Zn. Once we reduce this equation modulo n, this term simply falls off because b times n is divisible by n, and therefore is 0 modulo n. But what we just showed is that in fact x inverse is simply a in Zn. So because x is relatively prime to n, we were able to show that x is invertible by actually building the inverse of x modulo n. Now what about the other direction? What happens if the GCD is greater than 1? Then we want to show that there is no inverse. But that's actually very easy to see because in this case, if you claim that a happens to be the inverse of x modulo n, well, let's look at a times x. A times x we know should be equal to 1 modulo n. But if the GCD of x and n is bigger than 1, then the GCD of a times x and n is bigger than 1. But if the GCD of a times x and n is bigger than 1, then it's not possible that a times x is equal to 1. So a times x must also be bigger than 1, and therefore a cannot be the inverse of x modulo n. So this proves that in fact when the GCD is greater than 1, x cannot have an inverse because there is no a such that a times x is equal to 1 mod n. And this might be a bit confusing, so it might be best to do an example. So let's suppose that the GCD of x and n happens to be equal to 2. I claim that x therefore is not invertible modulo n. Well, why is that true? Well, for all a, we know that a times x is going to be even. And the reason we know that is because, well, 2 divides x and 2 divides n. Well, since 2 divide x, 2 is also going to divide a times x, and therefore a times x must be even. But what that means is that there's no way that a times x is equal to 1 modulo n, In particular, there's no way that a times x is equal to b times n plus 1. This simply can't happen. This equality must not hold, because this side happens to be even, as we said. B times n, for exactly the same reason, is also even. N is divisible by 2, therefore b times n is also divisible by 2, but therefore b times n plus 1 is odd. And since even can't equal to odd, it's not possible that a times x is equal to some multiple of n plus 1. And in particular, this means that a cannot be the inverse of x, because a times x cannot be 1 mod n. So x is not invertible modulo n. So now we have a complete understanding of what are the invertible elements. Basically, we know that an element is invertible if and only if it's relatively prime to n. And what I like about this proof is I would say this is what's called a computer science proof, in the sense that not only does it prove to you that the inverse exists, it also shows you how to efficiently calculate the inverse. And the way we calculate the inverse is basically by using this extended Euclidean algorithm to find the numbers a and b. And once we found the numbers a and b, we're done, because a is the inverse of x. And the numbers a and b can be found very efficiently. So along the way, I've also shown you an algorithm for inverting elements modulo n. Okay, so bear with me and let's introduce just a little bit more of notation. So we're going to denote by Zn star as the set of invertible elements in Zn. In other words, Zn star is the set of all elements in Zn such that GCD of x and n is equal to 1. Okay, but I want you again to think of Zn star as basically those elements in Zn that have an inverse. So let's look at a few examples. So let's start with a prime p. We know that of the integers from 0 to p minus 1, all of them are going to be relatively prime to p, except one integer, namely the integer 0. 0 is not relatively prime to p, because the GCD of p and 0 is 0, not 1. So therefore, if p is a prime, the set zp star is simply zp minus 0, which means that everything in zp star is invertible except for 0. So if you like, the size of zp star is simply p minus 1. Now let's look at our favorite integer again. So why don't you tell me what is z12 star? What is the set of invertible elements modulo 12? And the answer, of course, is all the numbers that are relatively prime to 12, namely 1, 5, 7, and 11. So for example, 3, 4, 6, all of those are not invertible because they all have a non-trivial GCD with 12. And as we said before, if I give you an element x in Zn star, you can find its inverse using the extended Euclidean algorithm. You can find its inverse very efficiently, in fact, using this algorithm. So what we just learned is basically how to solve modular linear equations. In other words, if I give you a linear equation and I ask you to solve it mod n, it's actually very easy to do. All you do is you move b to the other side, so you have a minus b, and then you multiply by a inverse. So the answer is minus b times a inverse. And you can find a inverse using the Euclidean algorithm. And once you have a inverse, you'd simply multiply it by minus b modulo n, and that gives you the solution to this linear equation. Now, the Euclidean algorithm actually takes time that's quadratic in logarithm of n. So it takes time proportional to log squared n. And as a result, we say that this is a quadratic algorithm for solving linear equations modulo n. And in fact, this is the best known algorithm. And so if you think back to your high school algebra days, after you learned how to solve linear equations, the next question was, well, what about quadratic equations? And that problem is actually quite interesting, and we're going to see that in the next few segments. In the previous segment, we talked about modular inversion, and we said that Euclid's algorithm gives us an efficient way to find the inverse of an element modulo n. In this segment, we're going to forward through time, and we're going to move to the 17th and 18th century, and we're going to talk about Fermat's and Euler's contributions. Before that, let's do a quick review of what we discussed in the previous segment. So as usual, I'm going to let n denote a positive integer, and let's just say that n happens to be an n-bit integer. In other words, it's between 2 to the n and 2 to the n plus 1. As usual, we're going to let p denote a prime. Now we said that z sub n is the set of integers from 0 to n minus 1, and we said that we can add and multiply elements in the set modulo n. We also said that Zn star is basically the set of invertible elements in Zn, and we proved the simple lemma to say that x is invertible if and only if x is relatively prime to n. And not only that we completely understand which elements are invertible and which aren't, we also showed a very efficient algorithm based on Euclid's extended algorithm to find the inverse of an element x in Zn. And we said that the running time of this algorithm is basically order n squared, where again n is the number of bits of the number capital N. So as I said, now we're going to move from Greek times all the way to the 17th century and talk about Fermat. So Fermat stated a number of important theorems. The one that I want to show you here says the following. So suppose I give you a prime p, then in fact for any element x in zp star, it so happens that if I look at x and raise it to the power of p minus 1, I'm going to get 1 in zp. So let's look at a quick example. Suppose I set the number p to be 5, and I look at 3 to the power of p minus 1, in other words 3 to the power of 4. 3 to the power of 4 is 81, which in fact is 1 modulo 5. This example satisfies Fermat's theorem. Interestingly, Fermat actually didn't prove this theorem himself. The proof actually waited until Euler, who proved it almost 100 years later, and in fact he proved a much more general version of this theorem. So let's look at a simple application of Fermat's theorem. Suppose I look at an element x in zp star, and I want to remind you here that p must be a prime. Well, then what do we know? We know that x to the p minus 1 is equal to 1. Well, we can write x to the p minus 1 as x times x to the power of p minus 2. Well, so now we know that x times x to the power of p minus 2 happens to be equal to 1. And what that says is that really the inverse of x modulo p is simply x to the p minus 2. So this gives us another algorithm for finding the inverse of x modulo a prime. Simply raise x to the power of p minus 2, and that will give us the inverse of x. It turns out, actually, this is a fine way to compute inverses modulo a prime, but it has two deficiencies compared to Euclid's algorithm. First of all, it only works modulo primes, whereas Euclid's algorithm worked modulo composites as well. And second of all, it turns out this algorithm is actually less efficient. When we talk about how to do modular exponentiations, we're going to do that in the last segment in this module, you'll see that the running time to compute this exponentiation is actually cubic in the size of p. So this will take roughly log cube of p, whereas if you remember, Euclid's algorithm was able to compute the inverse in quadratic time in the representation of p. So not only is this algorithm less general, it only works for primes, it's also less efficient. So score 1 for Euclid, but nevertheless, this fact about primes is extremely important, and we're going to be making extensive use of it in the next couple of weeks. So let me show you a quick and simple application of Fermat's theorem. Suppose we wanted to generate a large random prime. Say our prime needed to be 1,000 bits or so. So the prime we're looking for is on the order of 2 to the 1024, say. So here's a very simple probabilistic algorithm. What we would do is we would choose a random integer in the interval that was specified, and then we would test whether this integer satisfies Fermat's theorem. In other words, we would test, for example, using the base 2, we would test whether 2 to the power of p minus 1 equals 1 in zp. If the answer is no, then if this equality doesn't hold, then we know for sure that the number p that we chose is not a prime. And if that happens, all we do is we go back to step 1 and we try another prime. And we do this again and again and again until finally we find an integer that satisfies this condition. And once we find an integer that satisfies this condition, we simply output it and stop. Now, it turns out, this is actually a fairly difficult statement to prove, but it turns out if a random number passes this test, then it's extremely likely to be a prime. In particular, the probability that p is not a prime is very small. It's like less than 2 to the minus 60 for the range of 1024-bit numbers. As the number gets bigger and bigger, the probability that it passes this test here but is not a prime drops to 0 very quickly. So this is actually quite an interesting algorithm. You realize we're not guaranteed that the output is in fact a prime. All we know is that it's very, very likely to be a prime. In other words, the only way that it's not a prime is that we got extremely unlucky. In fact, so unlucky that a negligible probability event just happened. Another way to say this is that if you look at the set of all 1024-bit integers, then, well, there's the set of primes. Let me write prime here. And then there's a small number of composites that actually will falsify the test. Let's call them F for false primes. Let's call them FP for false primes. There's a very small number of composites that are not prime and yet will pass this test. But as we choose random integers, we choose one here, one here, one here, and so on. As we choose random integers, the probability that we fall into the set of false primes is so small that it's essentially a negligible event that we can ignore. In other words, one can prove that the set of false primes is extremely small and a random choice is unlikely to pick such a false prime. Now, I should mention, in fact, this is a very simple algorithm for generating primes. It's actually by far not the best algorithm. We have much better algorithms now. And in fact, once you have a candidate prime, we now have very efficient algorithms that will actually prove beyond a doubt that this candidate prime really is a prime. So we don't even have to rely on probabilistic statements. And nevertheless, this Fermat test is so simple that I just wanted to show you that it's an easy way to generate primes, although in reality, this is not how primes are generated. As a last point, I'll say that you might be wondering how many times this iteration has to repeat until we actually find the prime. And that's actually a classic result. It's called the prime number theorem, which says that after a few hundred iterations, in fact, we'll find the prime with high probability. So in expectation, one would expect a few hundred iterations and no more. Now that we understand Fermat's theorem, the next thing I want to talk about is what's called the structure of ZP star. So here we're going to move 100 years into the future, into the 18th century, and look at the work of Euler. And one of the first things Euler showed is, in modern language, is that ZP star is what's called a cyclic group. So what does it mean that ZP star is a cyclic group? What it means is there exists some element G in ZP star, such that if we take G and raise it to a bunch of powers, G, G squared, G cubed, G to the fourth, and so on and so forth, up until we reach G to the P minus 2, notice there's no point going beyond G to the P minus 2 because G to the P minus 1 by Fermat's theorem is equal to 1. So then we will cycle back to 1. If we go back to G to the P minus 1, then G to the P will be equal to G, G to the P plus 1 will be equal to G squared, and so on and so forth. So we'll actually get a cycle if we keep raising to higher and higher powers of G. So we might as well stop at the power of G to the P minus 2. And what Euler showed is that in fact there is an element G such that if you look at all of its powers span the entire group ZP star. The powers of G give us all the elements in ZP star. An element of this type is called a generator. So G would be said to be a generator of ZP star. So let's look at a quick example. So let's look, for example, at P equals 7, and let's look at all the powers of 3. So 3 squared, 3 cubed, 3 to the fourth, 3 to the fifth. 3 to the 6th, already we know, is equal to 1 modulo 7 by Fermat's theorem. So there's no point in looking at 3 to the 6th. We know we would just get 1. So here I calculated all these powers for you and I wrote them out. And you see that in fact we get all the numbers in Z7 stars. In other words, we get 1, 2, 3, 4, 5, and 6. So we would say that 3 is a generator of Z7 star. Now I should point out that not every element is a generator. For example, if we look at all the powers of 2, well, that's not going to generate the entire group. In particular, if we look at 2 to the 0, we get 1. 2 to the 1, we get 2. 2 squared is 4. And 2 cubed is 8, which is 1 modulo 7. So we cycled back. And then 2 to the 4th would be 2. 2 to the 5th would be 4. And so on and so forth. So if we look at the powers of 2, we just get 1, 2, and 4. We don't get the whole group, and therefore we say that 2 is not a generator of Z7 star. Now again, something that we'll use very often is given an element G of ZP star, if we look at the set of all powers of G, the resulting set is going to be called the group generated by G. Okay, so these are all the powers of G. They give us what's called a multiplicative group. Again, the technical term doesn't matter. The point is we're going to call all these powers of G the group generated by G. In fact, there's this notation which I won't use very often, angle G angle, to denote this group that's generated by G. And then we call the order of G in ZP star, we simply let that be the size of the group that's generated by G. So in other words, the order of G in ZP star is the size of this group. But another way to think about that is basically it's the smallest integer a such that G to the a is equal to 1 in ZP. Okay, it's basically the smallest power that causes a power of G to be equal to 1. And it's very easy to see that this equality here, basically if we look at all the powers of G, then we look at 1, G, G squared, G cubed, and so on and so forth. up until we get to the g to the order of g minus 1. And then if we look at the order of at g to the order of g, this thing is simply going to be equal to 1 by definition. Okay, so there's no point in looking at any higher powers. We might as well just stop raising to powers here. And as a result, the size of the set, in fact, is the order of g. And you can see that the order is the smallest power, such that raising g to that power gives us 1 in ZP. So I hope this is clear, although it might take a little bit of thinking to absorb all this notation. But in the meantime, let's look at a few examples. So again, let's fix our prime to be 7. And let's look at the order of a number of elements. So what is the order of 3 modulo 7? Well, we're asking what is the size of the group that 3 generates modulo 7? Well, we said that 3 is a generator of Z7 star, so it generates all of Z7 star. There are 6 elements in Z7 star, and therefore we say that the order of 3 is equal to 6. Similarly, I can ask, well, what is the order of 2 modulo 7? And in fact, we already saw the answer. So I'll ask you, what is the order of 2 modulo 7, and see if you can figure out what this answer is. So the answer is 3, and again, the reason is, if we look at the set of powers of 2 modulo 7, well, we have 1, 2, 2 squared, and then 2 cubed is already equal to 1. So this is the entire set of powers of 2 modulo 7. There are only 3 of them, and therefore the order of 2 modulo 7 is exactly 3. Now let me ask you a trick question. What's the order of 1 modulo 7? Well, the answer is 1, because if you look at the group that's generated by 1, well, there's only one number in that group, namely the number 1. If I raise 1 to a whole bunch of powers, I'm always going to get 1. And therefore, the order of 1 modulo 7, in fact, the order of 1 modulo any prime, is always going to be 1. Now, there's an important theorem of Lagrange that, actually, this is a very, very special case of it, what I'm stating here. But Lagrange's theorem basically implies that if you look at the order of g modulo p, the order is always going to divide p minus 1. So in our 2 example, you see 6 divides 7 minus 1. 6 divides 6. And similarly, 3 divides 7 minus 1. Namely, again, 3 divides 6. But this is very general. The order is always going to be a factor of p minus 1. In fact, I'll tell you, maybe as a puzzle for you to think about, it's actually very easy to deduce Fermat's theorem directly from this fact, from this Lagrange's theorem fact. And so Fermat's theorem really, in some sense, follows directly from Lagrange's theorem. Lagrange, by the way, did his work in the 19th century, so you can already see how we're making progress through time. We started in Greek times, and already we ended up in the 19th century. And I can tell you that more advanced crypto actually uses 20th century math very extensively. Now that we understand the structure of ZP star, let's generalize that to composites and look at the structure of Zn star. So what I want to show you here is what's called Euler's theorem, which is a direct generalization of Fermat's theorem. So Euler defined the following function. So given an integer n, he defined what's called the phi function, phi of n, to be basically the size of the set Zn star. This is sometimes called Euler's phi function, the size of the set Zn star. So for example, we already looked at Z12 star. We said that Z12 star contains these 4 elements, 1, 5, 7, and 11. And therefore, we say that phi of 12 is simply the number 4. So let me ask you as a puzzle, what is phi of p? It'll basically be the size of ZP star. And so, in fact, we said that the ZP star contains all of ZP except for the number 0. And therefore, phi of p for any prime p is going to be p minus 1. Now, there's a special case which I'm going to state here and we're going to use later for the RSA system. If n happens to be a product of 2 primes, then phi of n is simply n minus p minus q plus 1. Now, let me just show you why that's true. So basically, n is the size of Zn. And now we need to remove all the elements that are not relatively prime to n. Well, how can an element not be relatively prime to n? It's got to be divisible by p, or it's got to be divisible by q. Well, how many elements between 0 and n minus 1 are there that are divisible by p? Well, there are exactly q of them. How many elements are there that are divisible by q? Well, there are exactly p of them. So we subtract p to get rid of those divisible by q. We subtract q to get rid of those divisible by p. And you notice we subtracted 0 twice, because 0 is divisible both by p and q, and therefore we add 1 just to make sure we subtract 0 only once. And so it's not difficult to see that 5n is n minus p minus q plus 1, and another way of writing that is simply p minus 1 times q minus 1. Okay, so this is a fact that we will use later on when we come back and talk about the RSA system. So far, this is just defining this phi function of Euler, but now Euler put this phi function to really good use. And what he proved is this amazing fact here that basically says that if you give me any element x in Zn star, in fact, it so happens that x to the power of 5n is equal to 1 in Zn. So you can see that this is a generalization of Fermat's theorem. In particular, Fermat's theorem only applied to primes. For primes, we know that phi of p is equal to p minus 1. And in other words, if n were prime, we would simply write p minus 1 here, and then we would get exactly Fermat's theorem. The beauty of Euler's theorem is it applies to composites and not just primes. So let's look at some examples. So let's look at 5 to the power of phi of 12. So 5 is an element of Z12 star. If we raise it to the power of phi of 12, we should be getting 1. Well, we know that phi of 12 is 4, so we're raising 5 to the power of 4. 5 to the power of 4 is 625, and it's a simple calculation to show that that's equal to 1 modulo 12. So this is proof by example, but of course it's not a proof at all, it's just an example. But in fact, it's not difficult to prove Euler's theorem, and in fact, I'll tell you that Euler's theorem is also a very special case of Lagrange's general theorem. Okay, so we said that this is a generalization of Fermat's theorem, and in fact, as we'll see, this Euler's theorem is the basis of the RSA crypto system. So I'll stop here and we'll continue with modular quadratic equations in the next segment. In a previous segment, we talked about how to solve modular linear equations. In this segment, we're going to talk about how to solve modular quadratic equations, and more generally, we're going to look at how to compute modular ETH roots. So as I said, now we know how to solve linear equations simply by using an inversion algorithm to compute A inverse and then multiplying the result by minus B. So the question is, what about higher degree polynomials? And in particular, we're interested in solving polynomials modulo primes, so solving polynomials in ZP, but polynomials particularly of the form x squared minus c, or y cubed minus c, or z to the 37 minus c, all in ZP. So solving this polynomial, for example, involves computing the square root of c. Solving this polynomial involves computing the cube root of c. Solving this polynomial involves computing the 37th root of c, and so on. So again, let's fix a primes p, and let's say that c is some element in ZP. We'll say that x in ZP that satisfies x to the e is equal to c. We'll call such an x the modular ETH root of c. So let's look at an example. We say that the cube root of 7 in Z11 is equal to 6 because 6 cubed is equal to 216, which happens to be 7 modulo 11. And therefore, the cube root of 7 modulo 11 is equal to 6. So let me ask you, what is the square root of 3 in Z11? So the answer is 5, because 5 squared is equal to 25, which is 3 modulo 11. And similarly, let me ask you, what is the cube root of 1 modulo 11? Well, the cube root of 1 is simply 1, because 1 cubed is equal to 1 in Z11. In fact, that's true in modulo any prime. One thing I'd like to point out is that these ETH roots don't always exist. For example, if I asked you to compute the square root of 2 modulo 11, you'd have a problem because the square root of 2 simply doesn't exist modulo 11. So now that we understand what an ETH root is, the next question is, when do these ETH roots exist? And when we know that they do exist, can we actually compute them efficiently? So let's start with the easy case. The easy case is when we want to compute an ETH root of something, and it so happens that E is relatively prime to P minus 1. In this case, C to the 1 over E always exists, and there's a very easy algorithm to actually compute the ETH root of C in ZP. So let's see how this works. So first, since E is relatively prime to P minus 1, we know that E has an inverse modulo P minus 1. So let's compute this inverse, and let's call it D. So let's let D be the inverse of E modulo P minus 1. then I claim that in fact c to the 1 over e is simply c to the d modulo p. So if this equation holds, then first of all, it proves that for all c in zp star, the eth root of c actually exists. And moreover, it gives a very efficient algorithm to compute this eth root of c simply by computing the inverse of e modulo p minus 1 and then raising c to the power of that inverse. Okay, so we kill two birds in one stone. So let's see why this equation holds. So first of all, the fact that d times e is equal to 1 mod p minus 1, what that means is there exists some integer k such that if I look at d times e, that's basically going to be k times p minus 1 plus 1. That's basically what it means that d times e is equal to 1 modulo p minus 1. But now what does that mean? Well, so now we can actually confirm that c to the d is an eth root of c. Well, how do we confirm that? Well, let's take c to the d and raise it to the power of e. If in fact c to the d is an eth root of c, then when we raise it to the power of e, we're supposed to get c back. So let's see why that's true. Well, that's simply equal to c times d to the e. And c times d to the e, well, by definition, is equal to c to the power of k times p minus 1 plus 1. Well, using the laws of exponentiation, we can write this as c to the power of p minus 1 to the power of k times c. All I did is I distributed the exponentiation using the standard laws of exponentiation. Now, what do we know about c to the p minus 1? Since c lives in zp star, by Fermat's theorem, we know that c to the p minus 1 is equal to 1 in zp. 1 to the k is also equal to 1. And as a result, this is simply equal to c in zp, which is exactly what we needed to prove that c to the d is an eth root of c. Okay, so this is what I call the easy case. In fact, the eth root always exists when e is relatively prime to p minus 1. And it's very easy to compute it simply by using this formula here. Now let's turn to the less easy case. So the less easy case is when e is not relatively prime to p minus 1. And the canonical example here is when e is equal to 2. So now suppose we want to compute square roots of c in zp. So if p is an odd prime, and in fact we're going to focus on odd primes from now on, then in fact p minus 1 is going to be even, which means that 2 divides p minus 1, and indeed the GCD of 2 and p minus 1 is not equal to 1. So this is not the easy case. So the algorithm that we just saw on the previous slide is not going to work when we want to compute square roots modulo an odd prime. So when we work modulo an odd prime, the squaring function is actually a 2-to-1 function. Namely, it maps x and minus x to the same value. It maps both of them to x squared. And as a result, we say that this function is a 2-to-1 function. So here's a simple example. Let's look at what happens when we compute squares modulo 11. So you can see that 1 and minus 1 modulo 11 both map to 1. 2 and minus 2 both map to 4. 3 and minus 3 both map to 9, and so on and so forth. So you can see that it's a 2-to-1 map. So in fact, these elements here, 1, 4, 9, 5, 3, all are going to have square roots. For example, the square root of 4 is simply going to be 2 and 9. And I claim that in fact, none of the other elements of Z11 star are going to have a square root. And that motivates this definition to say that an element x in ZP, we're going to say is called a quadratic residue if in fact it has a square root in ZP. Okay, and if it doesn't have a square root, we'll say that it's a non-quadratic residue. So for example, modulo 11, 4 is going to be a quadratic residue, 9 is going to be a quadratic residue, 5 is a quadratic residue, 3 is a quadratic residue, and of course 1 is a quadratic residue. So let me ask you, if p is an odd prime, what do you think is the number of quadratic residues in ZP? And I'll give you a hint, the squaring function is a 2-to-1 map, which means that half the elements in ZP can't have a pre-image under this map. So the number of quadratic residues is simply p minus 1 over 2 plus 1. And the reason that's true is because we know that exactly half the elements in ZP star are going to be quadratic residues because of the fact that the squaring function is a 2-to-1 map. So there can be at most p minus 1 over 2 elements in the image of that map. So half the elements in ZP star are quadratic residues. And then in ZP, there's also 0. We also have to account for 0. 0 is always a quadratic residue because 0 squared is equal to 0. So overall, we get p minus 1 over 2 quadratic residues in ZP star plus 1, the 0 element, which is a quadratic residue in ZP. So overall in ZP, there are p minus 1 over 2 plus 1 quadratic residues. Okay, so the main point to remember is that roughly half the elements have a square root, and the other half does not have a square root. I want to emphasize that this is very different from the easy case, where E was relatively prime to p minus 1. If you remember, in the easy case, every element in ZP star had an ETH root. When E is not relatively prime to p minus 1, that's no longer the case, and in particular in the case of E equals 2, only half the elements in ZP star have a square root. Well, so the natural question then is, can we, given an element x in ZP star, can we tell whether it has a square root or not? So Euler did some important work on that too, and in fact he came up with a very clean criteria to test exactly which elements are quadratic residues and which are not. And in particular, he said that x in ZP star is a quadratic residue if and only if x to the power of p minus 1 over 2 is equal to 1 modulo p. Okay, very, very elegant and very simple condition. Let's see a simple example in Z11, so when we work mod 11. So here I computed the fifth power of all the elements in 11 for you, and you can see that this symbol, this x to the p minus 1 over 2, is always either 1 or minus 1, and it's 1 precisely at the quadratic residues. So 1, 3, 4, 5, and 9. Okay, those are the quadratic residues, and the other elements are not quadratic residues here. I'll circle them in green. These are the elements that do not have a square root when we work modulo 11. One thing I'd like to point out is, in fact, if we take an x that's not equal to 0, and we look at x to the p minus 1 over 2, well, we can write that as the square root of x to the p minus 1, right? The kind of the half bubbles out, and this is simply the square root of x to the p minus 1. Well, x to the p minus 1 by Fermat's theorem is 1, so x to the p minus 1 over 2 is simply a square root of 1, which must be 1 or minus 1. So what this proves is that really this exponentiation here must output 1 or minus 1, and we actually saw that happening here. It outputs 1 when x is a quadratic residue, and it outputs minus 1 when x is not a quadratic residue. This is not a particularly difficult proof, but I'm not going to show it to you here. It's in the reference that I point to at the end of the module. And just for completeness, I'll mention that this value, x to the p minus 1 over 2, has a name. It's called the Legendre symbol of x over p, and as we said, this for elements in ZP star, this symbol is either 1 or minus 1, depending on the quadratic residuosity of x. Now, the sad thing about Euler's theorem is that it's not constructive. Even though it's a very, very cute theorem, it tells us exactly which elements are quadratic residues and which aren't. This theorem doesn't do it constructively in the sense that if we want to compute the square root of a quadratic residue, the theorem doesn't actually tell us how to do that. And in fact, even if you look at the proof is by an existential argument. So it proves that the square root exists, but it doesn't show us how to compute the square root when we want it. So the next question is then, how do we compute square roots modulo primes? So it turns out that's actually not so hard, and again, it breaks up into two cases. The first case is when p is equal to 3 modulo 4, in which case it's really easy to compute the square root, and I'll just tell you there's a simple formula. The square root of c in this case is simply c to the power of p plus 1 over 4. You notice that because p is equal to 3 modulo 4, p plus 1 is necessarily p plus 1 is equal to 0 modulo 4, which means that p plus 1 is divisible by 4, and therefore p plus 1 over 4 is an integer. And that's exactly what allows us to compute this exponentiation, and I claim that that actually gives us the square root of c. Very simple formula that directly gives us the square root of c. So let's verify that that's actually true. Well, I'll take c to the power of p plus 1 over 4 and square that. And if in fact, if c to the p plus 1 over 4 is the square root of c, when I square it, I should get c. So let's see what happens. So first of all, by laws of exponentiation, this is simply equal to c to the power of p plus 1 over 2. And that I can write as c to the power of p minus 1 over 2 times c. Okay, again, this is basically I took 1/2 and moved it out of the exponentiation. Now, what do we know about c to the power of p minus 1 over 2? Since C is a quadratic residue, we know that C to the power of P minus 1 over 2 is 1. And therefore, this is really equal to 1 times C, which is C in ZP as we wanted to show. Okay, so this basically proves that C to the power of P plus 1 over 4 is the square root of C, at least in the case when P is equal to 3 mod 4. Now you should ask me, well, what about the case when P is equal to 1 mod 4? In that case, this formula doesn't even make sense, because P plus 1 over 4, this exponent here, P plus 1 over 4, is going to be a rational fraction, and I don't know how to raise C to the power of a rational fraction. Nevertheless, it turns out that even in the case when P is equal to 1 mod 4, we can efficiently find square roots, although it's a little bit harder. And in particular, we don't have a deterministic algorithm to do it. We have to use a randomized algorithm to do it. But this randomized algorithm will actually find the square root of x mod p very efficiently. I guess I should mention that if someone could prove that the extended Riemann hypothesis, this is some deep hypothesis in analytic number theory, if someone can prove that that hypothesis is true, in fact, it would give a deterministic algorithm for computing square roots even when p is equal to 1 modulo 4. So the reason I like to mention that is because you notice that as soon as you put the computational lens on something, for example, I ask you to compute the square roots of a number x modulo p, coming up with an algorithm already requires extremely deep results in mathematics, some of which are not even known to be true today. So as things stand today, we simply don't have a deterministic algorithm to compute square roots where p is 1 mod 4, but as I said, we have good randomized algorithms, and this problem is considered easy. Essentially, it boils down to a few exponentiations, and as a result, as we'll see, the running time of computing square roots essentially is cubic in the number of bits of p. So excellent. So now we know how to compute square roots mod p, and so now we can talk about solving quadratic equations modulo p. So suppose I give you a quadratic equation, and I ask you to find a solution of this quadratic equation in ZP. Well, so now I claim that you know how to solve it. The way you would solve it is basically you would use the high school formula for solving quadratic equations. So the solution is minus b plus minus square root of b squared minus 4ac over 2a. And I claim that you know how to compute all the elements in this formula. So you know how to compute the inverse of 2a, so you can divide by 2a. That's done using the extended Euclidean algorithm. And we know how to compute the square root of b squared minus 4ac using one of the square root algorithms from the previous slide. And of course, the formula will only be solvable if the square root actually exists in ZP. So that's cool. So now you guys know how to solve quadratic equations in ZP. So now the next obvious question is, what about computing ETH roots modulo composites rather than modulo primes? So we can ask exactly the same questions that we asked before. So when does the ETH roots modulo n exist? And if we know that it exists, can we actually compute it efficiently? And here the problem is much harder. And in fact, it turns out that for all we know, computing ETH roots modulo composites is as hard as factoring that composite. Now for a general E, this is actually not known to be true, but the best algorithm that we have for computing ETH roots modulo n requires us to factor the modulus. And once we factor the modulus, then it's actually easy to compute ETH roots modulo each of the prime factors, and we can combine all the ETH roots together to get an ETH roots modulo the composite n. So it's a very interesting case where computing ETH roots modulo a prime was very easy. In fact, for many E's it was very easy, but computing ETH roots modulo composites is much harder, and in fact requires the factorization of n. So that's all I wanted to tell you about ETH roots. In the next segment, we're going to turn to modular algorithms, and we're going to talk about addition and multiplication and exponentiation algorithms, modulo primes and composites. The next thing we're going to look at is how to compute modulo large integers. So the first question is, how do we represent large integers in a computer? So that's actually fairly straightforward. So imagine we're on a 64-bit machine. What we would do is we would break the number we want to represent into 32-bit buckets. And then we would basically have these n over 32-bit buckets, and together they would represent the number that we want to store on the computer. Now I should mention that I'm only giving 64-bit registers as an example. In fact, many modern processors have 128-bit registers and more, and you can even do multiplications on them. So normally you would actually use much larger blocks than just 32 bits. The reason, by the way, you want to limit yourself to 32 bits is so that you can multiply two blocks together, and the result will still be less than 64 bits, less than the word size on the machine. So now let's look at the particular arithmetic operations to see how long each one takes. So addition and subtraction, basically what you would do is as addition with carry or subtraction with borrow, and those are basically linear time operations. In other words, if you want to add or subtract two n-bit integers, the running time is basically linear in n. Multiplication naively will take quadratic time. In fact, this is what's called the high school algorithm. This is what you kind of learn in school, where if you think about this for a minute, you'll see that that algorithm basically is quadratic in the length of the numbers that are being multiplied. So a big surprise in the 1960s was an algorithm due to Karatsuba that actually achieved much better than quadratic time. In fact, it achieved a running time of n to the 1.585. And there's actually no point in me showing you how the algorithm actually works. I'll just mention the main idea. What Karatsuba realized is that in fact when you want to multiply two numbers, you can write them as, you can take the first number x and write it as 2 to the b times x2 plus x1, where x2 and x1 are roughly the size of the square root of x. Okay, so you can kind of break the number x into the left part of x and the right part of x. And basically you're writing x as if it was written base 2 to the b. So it's got two digits base 2 to the b. And you do the same thing with y. You write y base 2 to the b. Again, you would write it as the sum of the left half plus the right half. And then normally if you try to do this multiplication, when you open up the parentheses, you see that this would require 4 multiplications, right? It would require x2 times y2, x2 times y1, xy times y2, and xy times y1. What Karatsuba realized is there's a way to do this multiplication of x by y using only 3 multiplications of x1, x2, and y1, y2. Since it's the big multiplication of x times y only takes 3 little multiplications, you can now recursively apply exactly the same procedure to multiplying x2 by y2 and x2 by y1 and so on and so forth. And you would get this recursive algorithm, and if you do the recursive analysis, you'll see that basically you get a running time of n to the 1.585. This number is basically, the 1.585 is basically log of 3 base 2. Surprisingly, it turns out that Karatsuba isn't even the best multiplication algorithm out there. It turns out that in fact you can do multiplication in about n log n time. So you can do multiplication in almost linear time. However, this is an extremely asymptotic result. The big O here hides very big constants, and as a result this algorithm only becomes practical when the numbers are absolutely enormous. And so this algorithm is actually not used very often. But Karatsuba's algorithm is very practical, and in fact most crypto libraries implement Karatsuba's algorithm for multiplication. However, for simplicity here, I'm just going to ignore Karatsuba's algorithm, and just for simplicity, I'm going to assume that multiplication runs in quadratic time. But in your mind, you should always be thinking, oh, multiplication really is a little bit faster than quadratic. And then the next question after we do multiplication, the question is, what about division with remainder? And it turns out that's also a quadratic time algorithm. So the main operation that remains, and one that we've used many times so far, and I've actually never ever told you how to actually compute it, is this question of exponentiation. So let's solve this exponentiation problem a bit more abstractly. So imagine we have a finite cyclic group G. All this means is that this group is generated from the powers of some generator little g. So for example, think of this group as simply ZP star, and think of little g as some generator of big G. The reason I'm stating it this way is I want you to start getting used to this abstraction where we deal with a generic group G, and ZP star really is just one example of such a group. But in fact, there are many other examples of finite cyclic groups. And again, I want to emphasize basically the group G, all it is simply this powers of this generator up to the order of the group. I'll write it as G to the Q. So our goal now is, given this element G and some exponent x, our goal is to compute the value of G to the x. Now normally what you would say is you would think, well, if x is equal to 3 and I want to compute G cubed, well, there's really nothing to do. All I do is I just do G times G times G, and I get G cubed, which is what I wanted. So that's actually pretty easy. But in fact, that's not the case that we're interested in. In our case, our exponents are going to be enormous. And so if you try, think of like a 500-bit number. And so if you try to compute g to the power of a 500-bit number simply by multiplying g by g by g by g, this is going to take quite a while. In fact, it'll take exponential time, which is not something that we want to do. So the question is whether, even though x is enormous, can we still compute g to the x relatively fast? And the answer is yes. And the algorithm that does that is called the repeated squaring algorithm. And so let me show you how repeated squaring works. So let's take as an example 53. Naively, you would have to do 53 multiplications of g by g by g by g by g until you get g to the 53, but I want to show you how you can do it very quickly. So what we'll do is we'll write 53 in binary. So here, this is the binary representation of 53. And all that means is, you notice this one corresponds to 32, this one corresponds to 16, this one corresponds to 4, and this one corresponds to 1. So really, 53 is 32 plus 16 plus 4 plus 1. But what that means is that g to the power of 53 is g to the power of 32 plus 16 plus 4 plus 1, and we can break that up using, again, the rules of exponentiation. We can break that up as g to the 32 times g to the 16 times g to the 4 times g to the 1. Now that should start giving you an idea for how to compute g to the 53 very quickly. What we'll do is simply we'll take g and we'll start squaring it. So square g once to get g squared. We square it again to get g to the 4th, then g to the 8th, then g to the 16th, g to the 32. So we've computed all these squares of g. And now what we're going to do is we're simply going to multiply the appropriate powers to give us the g to the 53. So this is g to the 1 times g to the 4th times g to the 16th times g to the 32 is basically going to give us the value that we want, which is g to the 53. So here you see that all we had to do was just compute, let's see, we had to do 1, 2, 3, 4, 5 squarings plus 4 more multiplications. So with 9 multiplications, we computed g to the 53. Okay, so that's pretty interesting. And it turns out this is a general phenomena that allows us to raise g to very, very high powers and do it very quickly. So let me show you the algorithm. As I said, this is called the repeated squaring algorithm. So the input to the algorithm is the element g and the exponent x, and the output is g to the x. So what we're going to do is we're going to write x in binary notation. So let's say that x has n bits, and this is the actual bit representation of x as a binary number. And then what we'll do is the following. We'll have these two registers. Y is going to be a register that's constantly squared, and then z is going to be an accumulator that multiplies in the appropriate powers of g as needed. So all we do is the following. We loop through the bits of x starting from the least significant bits, and then we do the following. At every iteration, we're simply going to square y. Okay, so y just keeps on squaring at every iteration, and then whenever the corresponding bit of the exponent x happens to be 1, we simply accumulate the current value of y into this accumulator z, and then at the end we simply output z. That's it. That's the whole algorithm, and that's the repeated squaring algorithm. So let's see an example with g to the 53. So you can see the two columns. Y is one column as it evolves through the iterations, and z is another column, again, as it evolves through the iterations. So y is not very interesting. Basically, all that happens to y is that at every iteration it simply gets squared, and so it just walks through the powers of 2 and the exponent, and that's it. Z is the more interesting register, where what it does is it accumulates the appropriate powers of g whenever the corresponding bits of the exponent is 1. So for example, the first bit of the exponent is 1, therefore at the end of the first iteration, the value of z is simply equal to g. The second bit of the exponent is 0, so the value of z doesn't change at the end of the second iteration. At the end of the third iteration, well, the third bit of exponent is 1, so we accumulate g to the 4th into z. The next bit of the exponent is 0, so z doesn't change. The next bit of the exponent is 1, and so now we're supposed to accumulate the previous value of y into the accumulator z. So let me ask you, so what's going to be the value of z? Well, we simply accumulate g to the 16 into z, and so we simply compute the sum of 16 and 5. We get g to the 21. Finally, the last bit is also set to 1, so we accumulate it into z. We do 32 plus 21, and we get the final output, g to the 53. Okay, so this gives you an idea of how this repeated squaring algorithm works. It's quite an interesting algorithm, and it allows us to compute enormous powers of g very, very, very quickly. So the number of iterations here essentially would be log base 2 of x. Okay, you notice the number of iterations simply depends on the number of digits of x, which is basically the log base 2 of x. So even if x is a 500-bit number, in 500 multiplications, well, in 500 iterations, really 1,000 multiplications, because we have to square and we have to accumulate. So in 1,000 multiplications, we'll be able to raise g to the power of a 500-bit exponent. Okay, so now we can summarize kind of the running times. So suppose we have an n-bit modulus capital N. As we said, addition and subtraction in Zn takes linear time. Multiplication, I'm just, as I said, Karatsuba actually makes this more efficient, but for simplicity, we'll just say that it takes quadratic time. And then exponentiation, as I said, basically takes log of x iterations, and in each iteration, we basically do 2 multiplications. So it's O of log of x times the time to multiply. And let's say that the time to multiply is quadratic, so the running time would be really n squared log x. And since x is always going to be less than n, by Fermat's theorem, there's no point in raising g to a power that's larger than the modulus. So x is going to be less than n. Let's suppose that x is also an n-bit integer. Then really exponentiation is a cubic time algorithm. Okay, so that's what I wanted you to remember, that exponentiation is actually relatively slow. These days it actually takes a few microseconds on a modern computer, but still microseconds for say a 4 gigahertz processor is quite a bit of work. And so just keep in mind that all the exponentiation operations we talked about, for example, for determining if a number is a quadratic residue or not, all those exponentiations basically take cubic time. Okay, so that completes our discussion of arithmetic algorithms. And then in the next segment, we'll start talking about hard problems, modulo, primes, and composites. In this module, we're going to look at some hard problems that come up in the context of modular arithmetic. These problems are going to be the basis of the crypto systems that we build next week. So first, I'd like to mention that there are many easy problems in modular arithmetic. For example, if you give me an integer n, and you give me an element x in Zn, finding the inverse of x is actually very easy using the Euclidean algorithm. Similarly, if you give me a prime p, and you give me some polynomial f, then finding an element in Zp that's a root of this polynomial is also relatively easy. And in fact, there's an efficient algorithm that can do it in linear time in the degree of the polynomial. So at least for low degree polynomials, finding roots of these polynomials modulo primes is actually quite easy. However, many problems in modular arithmetic are actually quite difficult, and as I say, these difficult problems form the basis of many public key crypto systems. So let's look at some classic hard problems, modulo primes. So fix some large prime p, so think of p as some 600-digit prime, and let's fix some element g in Zp star. And let's assume that the order of this element g happens to be a number q. Now consider the exponentiation function that simply maps a number x to the element g to the x. We showed in the last segment that this function is easy to compute using the repeated squaring algorithm. So in fact, computing g to the x can be done quite efficiently. But now let's look at the inverse question. So the inverse problem is basically given g to the x. Now I want you to find its logarithm, namely the value x. As I said, over the real numbers, given g to the x, find x is exactly the definition of the logarithm function. But here I ask you to find the logarithm modulo a prime p. So this problem is called the discrete logarithm problem, d-log. And I'll say that the discrete logarithm of g to the x base g is basically the exponent x. Okay, so the discrete logarithm of g to the x is x. So our goal is to output some exponent x in 0 to q minus 2 that happens to be the logarithm of g to the x. So let's look at an example. Suppose we look at the integers modulo 11. And here I wrote down the discrete log function in Z11 base 2. So let's look at how this function behaves. So first of all, the discrete logarithm of 1 is 0 because 2 to the 0 is equal to 1. Similarly, the discrete logarithm of 2 is 1 because 2 to the 1 is equal to 2. The discrete logarithm of 4 is 2 because 2 squared is equal to 4. The discrete logarithm of 8 is 3 because 2 cubed is equal to 8. And so on and so forth. So here I wrote down the discrete logarithm values for you, and let me ask you a puzzle. What's the discrete logarithm of 5 modulo 11? See if you can calculate it yourself. And so the answer is 4 because 2 to the 4 is equal to 16, and 16 is equal to 5 modulo 11. Okay, so this says that the discrete logarithm base 2 of 5 is this number 4. Now I can tell you that the discrete logarithm function in general is actually quite difficult to compute. Of course, for small primes, it's quite easy. You can just make a table and you can read off the discrete log values. But if the prime p happens to be a large number, say a 2000-bit number, then in fact computing discrete log is quite difficult and we don't have good algorithms to do it. So let's define the discrete log problem more generically. Instead of just focusing on the group ZP star, let's abstract and look at a generic group G. So we have a finite cyclic group with a generator G. All that means is that this group just consists of all the powers of G. So we take all the powers up to the order, in this case the order of G happens to be Q. So we take all the powers of G, and those powers actually make up the group capital G. Now we're going to say that the discrete log problem is hard in the group G if in fact no efficient algorithm can compute the discrete log function. So what do we mean by that? What we mean is if you choose a random element G in the group capital G and you choose a random exponent X, if I give the algorithm G and G to the X, of course I also have to give it the description of the group. So I give it the description of the group G and the order of the group, but the primary elements are G and G to the X. The probability that the algorithm will actually compute the discrete log is negligible. Okay, so if this is true for all efficient algorithms, then we say that the discrete log problem is hard in this group capital G. And again, the reason we say that is because no efficient algorithm is able to compute discrete log with non-negligible probability. So as I mentioned, we have a couple of candidate examples for groups where discrete log is hard. The canonical example is ZP star. This is actually the example that Diffie-Hellman came up with in 1974. But it turns out there are other candidate groups where the discrete log problem happens to be hard. And I think I already mentioned that one candidate is what's called the elliptic curve group, or rather the set of points on an elliptic curve. I'm not going to define that here, but as I said, if you'd like me to talk about elliptic curve cryptography, I can do that actually in the very last week of the class. So these are two groups where the discrete log problem is in fact believed to be hard, but it so happens that the discrete log problem actually is harder, as far as we know, on elliptic curves than it is in ZP star. In other words, if you give me equal size problems, one set in the group ZP star and one set in an elliptic curve group, the problem set in the elliptic curve group is going to be much harder than the problem in ZP star. Again, assuming these two problems are of the same size. And because the elliptic curve problem, the discrete log elliptic curve problem, is harder than in ZP star, this means that we can use smaller parameters when using elliptic curves than we can for ZP star, and as a result, the resulting systems with elliptic curves are going to be more efficient because the parameters are smaller, and yet the attacker's job is as hard as for a much larger prime in ZP star. So to make that concrete, I'll tell you that in ZP star, there's what's called a sub-exponential algorithm for discrete log. So I think I already mentioned this. If you have an n-bit prime, this algorithm will run in a roughly cube root of n time. In fact, there are many other terms in the exact running time of this algorithm, but the dominant term is cube root of the number of bits in the prime, so cube root of n. And because of this algorithm, you see that if we want a discrete log problem to be hard, as hard as it is to break a corresponding symmetric key, we have to use relatively large moduli p. Now in contrast, if you look at an elliptic curve group, the numbers look much better, and then in fact on an elliptic curve group, the best algorithm for discrete log that we have runs in time e to the n over 2. So this is what we would call a proper exponential time algorithm, because for a problem of size n, the running time is roughly e to the n. It's an exponential in n, not an exponential in cube root of n. And because the problem is so much harder, again, the best algorithm we have actually takes exponential time, you notice that on elliptic curves we can use much smaller parameters and still remain secure. By the way, the reason the elliptic curve size is exactly twice the symmetric key size is exactly because of this factor of 2 in the exponent here. So we have to double the size of the elliptic curve for the problem to actually take e to the n time. And actually I made a small typo here in that this is actually supposed to be 2 to the n over 2. But the exact base of the logarithm doesn't really matter. So I think I mentioned before that because the parameters are smaller with elliptic curves than they are with ZP star, there's a slow transition from doing crypto modulo P to doing crypto over elliptic curves. And again, I'll mention that if you want me to describe elliptic curves in more detail, I can do that at the last week of the class. So now that we understand what the discrete log problem is, let me give you a direct application of the hardness of discrete log. And in particular, let's build a collision-resistant hash function from the discrete log problem. So let's choose some group capital G where the discrete log problem is hard. So if you like, you can think of capital G as the group ZP star. And let's assume that the group capital G has prime order Q. So Q is some prime number that happens to be the order of G, the number of elements in group capital G. Now to define our hash function, what we'll do is we'll choose two elements in the group capital G, let's call them G and H, and then we'll define the hash function as follows. The hash function on input X and Y will output an element in G defined as G to the X times H to the Y. That's it. Okay, a very, very, very simple hash function. And if you recall, we even talked about this hash function when we talked about compression functions before. I want to show you that this function capital H is in fact collision resistant in the sense that finding a collision for capital H is as hard as computing discrete log in the group capital G. Okay, so in particular, if you can find a collision for capital H, you can compute a discrete log of H base G. And since we said the discrete log in the group capital G is hard, computing this discrete log should be difficult, and therefore finding collisions for capital H is going to be difficult. Okay, so let's see how we do this. It's actually a very cute proof. What we'll do is we'll do the following. Suppose we're given a collision on the function capital H. So we're given two distinct pairs, x0, y0, and x1, y1, that happen to collide on the function capital H. What does it mean that they collide on the function capital H? What it means is if I evaluate the function capital H at x0, y0, and x1, y1, I'll get a collision, namely I'll get an equality. Well, so now I can just do a little bit of manipulation, and you see that this means I just move all the g's to one side, all the h's to the other side. So this means that g to the x0 minus x1 is equal to h to the y1 minus y0. Okay, this is just a simple manipulation. Now I can raise both sides to the power of y1 minus y0. In other words, I'm taking a y1 minus y0th root of both sides. So one side will become simply h, and the other side will become g to the power of this fraction, x0 minus x1 divided by y1 minus y0. But now look at what we just got. Basically, we expressed h as g to some known power. Basically, all we did is just division, and boom, we're done. We've just expressed h as g to some known power. So we've computed the discrete log of h based g. So you might be wondering, what does this division in the exponent mean? What does it mean to divide by y1 minus y0 in the exponent? Well, what it means is basically we compute the inverse of y1 minus y0 modulo q, and then we multiply the result by x0 minus x1. And that gives us the exponent in the clear, and so we've just learned the discrete log of h base g. So this also shows you why we wanted q to be prime, because we need to make sure that y1 minus y0 is always invertible. Okay, so in fact we know that when we work modulo prime, everything is invertible except for 0. So that actually raises a subtle point. What happens if y1 minus y0 actually happens to be equal to 0? If that's the case, then we're not going to be able to get the discrete log because we won't be able to divide by 0. But if you think about this for a minute, you realize, well, let's see here. If y1 minus y0 equals 0, that means that y1 is equal to y0. But if y1 is equal to y0, just look at this equation here, that means that, well, that necessarily means that x0 is also equal to x1. Yeah, this takes a minute to convince yourself. If y0 is equal to y1, basically these two terms simply cancel out, and then we get that x0 is equal to x1. But then if x0 is equal to x1 and y0 is equal to y1, what you gave me is not a collision. You simply gave me the same pair twice. So that's cheating. So that's not considered a collision, and therefore, I don't need to find discrete log. But if you give me a collision, necessarily y0 is not going to be equal to y1, and then as a result, I'm going to get the discrete log of g base h. And as we said, since discrete log is believed to be hard in the group capital G, this means that this very, very simple function capital H must be collision resistant. So this is a very elegant example of a reduction from finding collisions to computing discrete log. I should tell you, by the way, that this function is not really used. Even though this function has a nice proof of collision resistance, it's not really used because it's relatively slow. Essentially, on every hash, you have to compute 2 exponentiations, and that's much, much, much slower than, say, functions like SHA-256 and other kind of ad hoc collision-resistant hash functions. Okay, so that's what I wanted to say about intractable problems modulo primes. Now let's look at some intractable problems modulo composites. So here we're going to say, again, let's look at, say, 1024-bit numbers. And let's define the set z sub 2n. This is going to be the set of all integers that happen to be a product of 2 primes, where those 2 primes are n-bit primes. Okay, so the 2 here corresponds to the fact that the numbers in this set basically have 2 prime factors, and those 2 prime factors are roughly the same size. They're both n-bit primes. So there are 2 classic intractable problems in the set. The first problem is if I choose a random integer in the set z2n, the problem is factor it. And already this is quite a difficult problem for 1024 bits. Although it hasn't been done yet, it's very likely that numbers of this magnitude will be factored soon. And so the recommended value these days is actually to use 2048-bit numbers. That's still beyond our reach, and those are numbers that we still cannot factor. Another example of an intractable problem modulo composites is if I give you some polynomial that's nonlinear, its degree is bigger than 1, and I give you some random composite in the set z2n, your goal is to find a root of this polynomial. Find an x that happens to be a root of this polynomial. And again, we don't know how to do that. Of course, if the degree is equal to 1, that just amounts to solving linear equations, and we already know that. That's easy. But the minute the degree becomes nonlinear, we don't know how to solve this modulo n without actually first factoring the modulus and then computing roots. So there are some systems, for example RSA, that depend on the hardness of this particular problem for specific polynomials, which we're going to see next week. And just as an example, I should mention that, for example, taking square roots or cube roots modulo a random composite in z2n is believed to be difficult. So there's actually quite a bit known about the factoring problem. It's actually a very old problem. Already the Greeks were interested in factoring, but Gauss actually has a wonderful, wonderful quote that talks about the problem of factoring and the problem of primality testing. So in his famous dissertation from 1805, he writes, "The problem of distinguishing prime numbers from composite numbers," this is what's called primality testing, "and the problem of resolving the latter, namely composites, into their prime factors, is known to be one of the most important and useful in arithmetic." So he had the foresight to realize that these are extremely interesting problems. These are computer science problems, essentially. How do we test if a number is prime? How do we factor a number if it's not a prime, if it's a composite? And already Gauss realized that these are extremely, extremely important and interesting problems. And now, these days, these problems are actually used on the web all over the place. So let's see. So, in fact, testing if a number is prime has been completely solved. We now know completely how to do it efficiently using a randomized algorithm, and we even know how to do it using a deterministic algorithm. Factoring numbers, factoring composite into their prime factors, this is still believed to be a difficult problem. I would encourage you actually to think about it. It's a wonderful problem to think about. If any of you can solve it, if any of you can come up with an algorithm to factor composites into prime factors, again, as I said, it's instant fame in the crypto world, and it would have tremendous impact on security of the web in general. So it's a fun problem to think about. Let me tell you what's known about the problem of factoring. So the best algorithm that we have is called the number field sieve. Again, its running time is one of these exponentials by the cube root of an exponential, which is why the composites has to be quite large for the problem to be difficult. Although the current world record is really just factoring a 768-bit number. This is called the RSA 768 number. It's a challenge number that was recently factored. The number is about 200 digits, and already factoring this number took an enormous amount of work. It took about 2 years on hundreds of machines, and finally they were able to factor this number. And the estimate is that actually factoring a 1024-bit number is about 1,000 times harder than factoring RSA 768. So instead of 2 years, it would take 2,000 years. But of course, computers are getting faster. We have more cores at our disposal. We have more computers. And so this factor of 1,000 assuming Moore's law and so on, really just means a decade. Computers get faster by about a factor of 1,000 every decade. So it's very likely that within the next decade, we'll see a factorization of a 1024-bit number, which would be the end of 1024 bits being used for public key cryptography. So that's the state of the art in the factoring world. And this concludes this module. I'll mention that if you want to read more about any of the topics that we discussed, there is a good book on the internet. It's a free book that you can download, written by Victor Shoup. And in particular, the topics that we discussed are covered in chapters 1 to 4, 11, and 12. So I would encourage you to take a look at that, and hopefully that will help with understanding the material. And next week, we'll start building cryptosystems using the topics we just learned about. Last week, we learned the number theory that's needed for public key encryption. This week, we're going to put this knowledge to work, and we're going to construct a number of secure public key encryption schemes. But first, we need to define what is public key encryption and what does it mean for public key encryption to be secure. So let me remind you that in a public key encryption scheme, there is an encryption algorithm, which we, as usual, denote by E, and there's a decryption algorithm, which we denote by D. However, here, the encryption algorithm takes a public key, while the decryption algorithm takes a secret key. This pair is called a key pair, and the public key is used for encrypting messages, while the secret key is used for decrypting messages. So in this case, a message M is encrypted using the public key, and what comes out of that is the ciphertext C. And similarly, the ciphertext is fed into the decryption algorithm, and using the secret key, what comes out of the decryption algorithm is the original message M. Now, public key encryption has many applications. Last week, we saw the classic application, which is session setup, namely key exchange. And for now, we're just looking at key exchange that is secure against eavesdropping only. And if you remember the way the protocol works, basically Alice, what she would do is she would generate a public key, secret key pair. She would send the public key to Bob. Bob would generate a random X, which is going to serve as their shared secret. And then he sends X encrypted to Alice, encrypted under her public key. Alice can decrypt, recover X, and now both of them have this shared secret X, which they can use to communicate securely with one another. The attacker, of course, all he gets to see is just the public key and the encryption of X under the public key, from which he should not be able to get any information about X. And we're going to define that more precisely to understand what it means to not be able to learn anything about X. Public key encryption actually has many other applications. For example, it's very useful in non-interactive applications. So think of an email system, for example. So here, Bob wants to send mail to Alice. And as Bob sends the email passes from mail relay to mail relay until finally it reaches Alice, at which point Alice should decrypt. The way the email system is set up is designed for kind of non-interactive settings where Bob sends the email and then Alice is supposed to receive it, and Alice should not need to communicate with Bob in order to decrypt the email. So in this case, because of the non-interactivity, there's no opportunity for setting up a shared secret between Alice and Bob. So in this case, what would happen is Bob basically would send the email encrypted using Alice's public key. So he sends the email. Anyone in the world can send the email encrypted to Alice, encrypted using her public key. When Alice receives this email, she uses her secret key to decrypt the ciphertext and recover the plaintext message. Of course, the one caveat in a system like this is that, in fact, Bob needs to somehow obtain Alice's public key. So for now, we're just going to assume Bob already has Alice's public key. But later on, actually, when we talk about digital signatures, we're going to see how this can actually be done very efficiently using what's called public key management. And as I said, we'll actually get back to that at a later time. But the main thing I want you to remember is that public key encryption is used for session setup. This is very common on the web, where public key encryption is used to set up a secure key between a web browser and a web server. And public key encryption is also very useful for non-interactive applications where anyone in the world non-interactively needs to send a message to Alice. They can encrypt the message using Alice's public key, and Alice can decrypt and recover the plaintext. So let me remind you in a bit more detail what a public key encryption system is. Well, it's made up of three algorithms, G, E, and D. G is called a key generation algorithm. Basically, what it will do is it will generate this key pair, the public key and the secret key. As written here, G takes no argument, but in real life, G actually does take an argument called a security parameter, which specifies the size of the keys that are generated by this key generation algorithm. Then there are these encryption algorithms, as usual, that take a public key and a message and produce a ciphertext, and a decryption algorithm that takes the corresponding secret key and the ciphertext and produces their corresponding message. And as usual, for consistency, we say that if we encrypt a message under a given public key and then decrypt with a corresponding secret key, we should get the original message back. Now, what does it mean for a public key encryption to be secure? I'm going to start off by defining security against eavesdropping, and then we're going to define security against active attacks. So the way to define security against eavesdropping is very similar to the symmetric case. We've already seen this last week, so I'm going to go through this quickly just as a review. Basically, the attack game is defined as follows. We define these two experiments, experiment 0 and experiment 1. In either experiment, the challenger is going to generate a public key and a secret key pair. He's going to give the public key to the adversary. The adversary is going to output two messages, M0 and M1 of equal length. And then what he gets back is either the encryption of M0 or the encryption of M1. In experiment 0, he gets the encryption of M0. In experiment 1, he gets the encryption of M1. And then the adversary is supposed to say, which one did he get? Did he get the encryption of M0 or did he get the encryption of M1? So in this game, the attacker only gets one ciphertext. This corresponds to an eavesdropping attack where he simply eavesdropped on that ciphertext C, and now his goal is to tell whether the ciphertext C is the encryption of M0 or M1. No tampering on the ciphertext C is allowed just yet. And as usual, we say that the public key encryption scheme is semantically secure if the attacker cannot distinguish experiment 0 from experiment 1. In other words, he cannot tell whether he got the encryption of M0 or the encryption of M1. Before we move on to active attacks, I wanted to mention a quick relation between the definition that we just saw and the definition of eavesdropping security for symmetric ciphers. If you remember, when we talked about eavesdropping security for symmetric ciphers, we distinguished between the case where the key is used once and the case where the key is used multiple times. And in fact, we saw that there's a clear separation. For example, the one-time pad is secure if the key is used to encrypt a single message, but is completely insecure if the key is used to encrypt multiple messages. And in fact, we had two different definitions. If you remember, we had a definition for one-time security, and then we had a separate definition which was stronger when the key was used multiple times. The definition that I showed you on the previous slide is very similar to the definition of one-time security for symmetric ciphers. And in fact, it turns out that for public key encryption, if a system is secure under a one-time key, in a sense, it's also secure for a many-time key. So in other words, we don't have to explicitly give the attacker the ability to request encryptions of messages of his choice, because he could just create those encryptions all by himself. He's given the public key, and therefore he can by himself encrypt any message he likes. As a result, any public key secret key pair, in some sense inherently, is used to encrypt multiple messages, because the attacker could have just encrypted many, many messages of his choice using the given public key that we just gave him in the first step. And so as a result, in fact, the definition of one-time security is enough to imply many-time security, and that's why we refer to the concept as indistinguishability under a chosen plaintext attack. So this is just a minor point to explain why in the settings of public key encryption, we don't need a more complicated definition to capture eavesdropping security. Now that we understand eavesdropping security, let's look at more powerful adversaries that can actually mount active attacks. So in particular, let's look at the email example. So here we have our friend Bob, who wants to send mail to his friend Caroline. And Caroline happens to have an account at Gmail, and the way this works is basically the email is sent to the Gmail server, encrypted. The Gmail server decrypts the email, looks at the intended recipient, and then if it's the intended recipient is Caroline, it forwards the email to Caroline. If the intended recipient is the attacker, it forwards the email to the attacker. This is similar to how Gmail actually works, because the sender would send the email encrypted over SSL to the Gmail server. The Gmail server would terminate the SSL and then forward the email to the appropriate recipient. Now, suppose Bob encrypts the email using a system that allows the adversary to tamper with the ciphertext without being detected. For example, imagine this email is encrypted using counter mode or something like that. Then when the attacker intercepts this email, he can change the recipient so that now the recipient says attacker@gmail.com, and we know that for counter mode, for example, this is quite easy to do. The attacker knows that the email is intended for Caroline. He's just interested in the email body, so he can easily change the email recipient to be attacker@gmail.com. And now when the server receives the email, he will decrypt it, see that the recipient is supposed to be attacker, and forward the body to the attacker. And now the attacker was able to read the body of the email that was intended for Caroline. So this is the classic example of an active attack. And you notice what the attacker could do here is it could decrypt any ciphertext where the intended recipient is /attacker. So any ciphertext where the plaintext begins with the words /attacker. So our goal is to design public key systems that are secure even if the attacker can tamper with ciphertext and possibly decrypt certain ciphertexts. And again, I want to emphasize that here the attacker's goal was to get the message body. The attacker already knew that the email is intended for Caroline, and all he had to do was just change the intended recipient. So this tampering attack motivates the definition of chosen ciphertext security, and in fact this is the standard notion of security for public key encryption. So let me explain how the attack game proceeds, and as I said, our goal is to build systems that are secure under this very, very conservative notion of encryption. So here we have an encryption scheme GED, and let's say that's defined over a message space and a ciphertext M, C. And as usual, we're going to define two experiments, experiment 0 and experiment 1. So B here says whether the challenger is implementing experiment 0 or experiment 1. The challenger begins by generating a public key and a secret key, and then he gives the public key to the adversary. Now the adversary can say, well, here are a bunch of ciphertexts, please decrypt them for me. So here the adversary submits ciphertext C1, and he gets the decryption of ciphertext C1, namely M1. And he gets to do this again and again, so he submits ciphertext C2, and he gets the decryption, which is M2. Ciphertext C3, and he gets the decryption M3. And so on and so forth. Finally, the adversary says, this querying phase is over, and now he submits basically two equal length messages, M0 and M1 as normal, and he receives in response the challenge ciphertext C, which is the encryption of M0 or the encryption of M1, depending on whether we're in experiment 0 or in experiment 1. Now the adversary can continue to issue these ciphertext queries, so he can continue to issue decryption requests. So he submits a ciphertext and he gets a decryption of that ciphertext. But of course now there has to be a caveat. If the attacker could submit arbitrary ciphertext of his choice, of course he could break the challenge. What he would do is he would submit the challenge ciphertext C as a decryption query, and then he would be told whether in the challenge phase he was given the encryption of M0 or the encryption of M1. As a result, we put this limitation here that says that he can in fact submit any ciphertext of his choice except for the challenge ciphertext. So the attacker could ask for the decryption of any ciphertext of his choice other than the challenge ciphertext, and even though he was given all these decryptions, he still shouldn't be able to tell whether he was given the encryption of M0 or the encryption of M1. So you notice this is a very conservative definition. It gives the attacker more power than what we saw on the previous slide. On the previous slide, the attacker could only decrypt messages where the plaintext began with the words /attacker. Here we're saying the attacker can decrypt any ciphertext of his choice as long as it's different from the challenge ciphertext C. Okay, and then his goal is to say whether the challenge ciphertext is the encryption of M0 or the encryption of M1. And as usual, if he can't do that, in other words, his behavior in experiment 0 is basically the same as his behavior in experiment 1, so he wasn't able to distinguish the encryption of M0 from the encryption of M1, even though he had all this power, then we say that the system is chosen ciphertext secure. CPA-secure, and sometimes there's an acronym. The acronym for this is indistinguishability under a chosen ciphertext attack. But I'm just going to say CPA-security. So let's see how this captures the email example we saw before. So suppose the encryption system being used is such that just given the encryption of a message, the attacker can change the intended recipient from /Alice, say, to /Charlie. Then here's how we would win the CCA game. Well, in the first step, he's given the public key, of course. And then what the attacker would do is he would issue two equal length messages. Namely, in the first message, the body is 0. In the second message, the body is 1. But both messages are intended for Alice. And in response, he would be given the challenge ciphertext C. Okay, so now here we have our challenge ciphertext C. Now what the attacker is going to do is he's going to use his ability here to modify the intended recipient, and he's going to send back a ciphertext C prime, where C prime is the encryption of the message to Charlie, with body being the challenge body B. So B, remember, is either 0 or 1. Now, because the plaintext is different, we know that the ciphertext must also be different. So in particular, C prime must be different from the challenge ciphertext C. Yeah, so the C prime here must be different from C. And as a result, the poor challenger now has to decrypt. By definition of the CCA game, the challenger must decrypt any ciphertext that's not equal to the challenge ciphertext. So the challenger decrypts, give the adversary M prime. Basically, he gave the adversary B, and now the adversary can output the challenge B, and he wins the game with advantage 1. So his advantage with this particular scheme is 1. So simply because the attacker was able to change the challenge ciphertext from one recipient to another, that allows him to win the CCA game with advantage 1. So as I said, chosen ciphertext security, it turns out, actually is the correct notion of security for public key encryption systems. And it's a very, very interesting concept, right? Basically, somehow, even though the attacker has this ability to decrypt anything he wants, other than the challenge ciphertext, he can't learn what the challenge ciphertext is. And so our goal for the remainder of this module, and actually the next module as well, is to construct CPA-secure systems. It's actually quite remarkable that this is achievable, and I'm going to show you exactly how to do it. And in fact, those CPA-secure systems that we build are the ones that are used in the real world. And every time a system has tried to deploy a public key encryption mechanism that's not CPA-secure, someone has come up with an attack and was able to break it. And we're going to actually see some of these example attacks actually in the next few segments. In the last segment, we explained what is a public key encryption system, and we defined what it means for a public key encryption system to be secure. If you remember, we required security against active attacks, and in particular, we defined chosen ciphertext security as our goal. This week, we're going to construct two families of public key encryption systems that are chosen ciphertext secure, and in this segment, we're going to start by constructing public key encryptions from a concept called a trapdoor permutation. So let's start by defining a general concept called a trapdoor function. So what is a trapdoor function? Well, a trapdoor function basically is a function that goes from some set x to some set y, and it's really defined by a triple of algorithms. There's a generation algorithm, the function f, and the inverse of the function f. So the generation algorithm, basically what it does when you run it, it will generate a key pair, a public key and a secret key. The public key is going to define a specific function from the set x to the set y. And then the secret key is going to define the inverse function now from the set y to the set x. So the idea is that you can evaluate the function at any point using the public key pk, and then you can invert that function using the secret key sk. So what do I mean by inversion? More precisely, if we look at any public key and secret key pair generated by the key generation algorithm G, then it so happens that if I evaluate the function at the point x, and then I evaluate the inverse at the resulting point, I should get the original point x back. So the picture you should have in your mind is there's this big set x and this big set y, and then this function will map any point in x to a point in y, and this can be done using the public key. So again, any point in x can be mapped to a point in y. And then if someone has the secret key, then basically they can go in the reverse direction by applying this secret key sk. So now that we understand what a trapdoor function is, let's define what it means for a trapdoor function to be secure. And so we'll say that this triple GF inverse is secure if in fact this function fpk is what's called a one-way function. Now let me explain what is a one-way function. The idea is that basically the function can be evaluated at any point, but inverting it is difficult without the secret key sk. So let's define that more precisely. As usual, we define that using a game. So here we have our game between the challenger and the adversary, and the game proceeds as follows. Basically, the challenger will generate a public key and a secret key, and then it will generate a random x. It will send the public key over to the adversary, and then it will evaluate the function at the point x and send the resulting y also to the adversary. So all the adversary gets to see is just a public key, which defines what the function is, and then he gets to see the image of this function on a random point x. And his goal is basically to invert the function at this point y. Okay, so he outputs some x prime, and we say that the trapdoor function is secure if the probability that the adversary inverts the given point y is negligible. In other words, given y, the probability that the adversary is able to output a pre-image of y is in fact a negligible probability. And if that's true for all efficient algorithms, then we say that the trapdoor function is secure. So again, abstractly, it's a really interesting concept in that you can evaluate the function in the forward direction very easily, but then no one can evaluate the function in the reverse direction unless they have this trapdoor, this secret key sk, which then all of a sudden lets them invert the function very, very easily. So using the concept of a trapdoor function, it's not too difficult to build a public key encryption system, and let me show you how to do it. So here we have our trapdoor function, g, f, and f inverse. The other tool we're going to need is a symmetric encryption scheme, and I'm going to assume that this encryption scheme is actually secure against active attacks. So in particular, I needed to provide authenticated encryption. Notice that the symmetric encryption system takes keys in K, and the trapdoor function takes inputs in X. Those are two different sets. And so we're also going to need a hash function that goes from X to K. In other words, it maps elements in the set X into keys for the symmetric encryption system. And now once we have these three components, we can actually construct the public key encryption system as follows. So the key generation for the public key encryption system is basically exactly the same as the key generation for the trapdoor function. So we run G for the trapdoor function, we get a public key and a secret key, and those are going to be the public key and secret keys for the public key encryption system. Now, how do we encrypt and decrypt? Well, let's start with encryption. So the encryption algorithm takes a public key and a message as input. So what it will do is it will generate a random x from the set capital X. It will then apply the trapdoor function to this random x to obtain y. So y is the image of x under the trapdoor function. Then it will go ahead and generate a symmetric key by hashing x. So this is a symmetric key for the symmetric key system. And then finally, it encrypts the plaintext message m using this key that is just generated. And then it outputs the value y that it just computed, which is the image of x, along with the encryption under the symmetric system of the message m. So that's how encryption works, and I want to emphasize again that the trapdoor function is only applied to this random value x, whereas the message itself is encrypted using a symmetric key system using a key that was derived from the value x that we chose at random. So now that we understand encryption, let's see how to decrypt. Well, the decryption algorithm takes a secret key as input and the ciphertext. The ciphertext itself contains two components, the value y and the value c. So the first step we're going to do is we're going to apply the inverse transformation, the inverse trapdoor function to the value y, and that'll give us back the original x that was chosen during encryption. So now let me ask you, how do we derive the symmetric decryption key, k, from this x that we just obtained? Well, so that's an easy question. We basically hash x again. That gives us k just as during encryption. And now that we have the symmetric encryption key, we can apply the symmetric decryption algorithm to decrypt the ciphertext C. We get the original message m, and that's what we output. So that's how the public key encryption system works, where this trapdoor function is only used for encrypting some sort of a random value x, and the actual message is encrypted using the symmetric system. So in pictures here we have the message m, obviously the plaintext could be quite large. So here we have the body of the ciphertext, which can be quite long, is actually encrypted using the symmetric system. And again, I emphasize that the key for the symmetric system is simply the hash of x. And then the header of the ciphertext is simply this application of the trapdoor function to this random x that we picked. And so during decryption, what happens is we first decrypt the header to get x, and then we decrypt the body using the symmetric system to actually get the original plaintext m. So as usual, when I show you a system like this, obviously you want to verify that decryption, in fact, is the inverse of encryption. But more importantly, you want to ask, why is this system secure? And in fact, there's a nice security theorem here that says that if the trapdoor function that we started with is secure, in other words, it's a one-way function if the adversary doesn't have the secret key, the symmetric encryption system provides authenticated encryption, and the hash function is a random oracle, which simply means that it's a random function from the set x to the set of keys k. So a random oracle is some sort of an idealization of what a hash function is supposed to be. In practice, of course, when you come to implement a system like this, you would just use SHA-256 or any of the other hash functions that we discussed in class. So under those three conditions, in fact, the system that we just described is chosen ciphertext secure, so it is CPA-secure The little RO here just denotes the fact that security is set in what's called a random oracle model, but that's a detail that's actually not so important for our discussion here. What I want you to remember is if the trapdoor function is in fact a secure trapdoor function, the symmetric encryption system is secure against tampering, so it provides authenticated encryption. And H is in some sense a good hash function. It's a random function, which in practice you would just use SHA-256. Then in fact the system that we just showed is CPA-secure, is chosen ciphertext secure. I should tell you that there's actually an ISO standard that defines this mode of encryption, of public key encryption. ISO stands for International Standards Organization. So in fact, this particular system has actually been standardized, and this is a fine thing to use. So I'll refer to this as the ISO encryption in the next few segments. To conclude this segment, I want to warn you about an incorrect way of using a trapdoor function to build a public key encryption system. And in fact, this method might be the first thing that comes to mind, and yet is completely insecure. So let me show you how not to encrypt using a trapdoor function. Well, the first thing that might come to mind is, well, let's apply the trapdoor function directly to the message M. So we encrypt simply by applying the function to the message M, and then we decrypt simply by applying F inverse to the ciphertext C to recover the original message M. Right, so functionally, this is in fact, decryption is the inverse of encryption, and yet this is completely insecure for many, many different reasons. The easiest way to see that this is insecure is that it's simply, this is deterministic encryption. You notice there's no randomness being used here when we encrypt the message M, and since it is deterministic, it cannot possibly be semantically secure. But in fact, as I said, when we instantiate this trapdoor function with particular implementations, for example, with the RSA trapdoor function, then there are many, many attacks that are possible on this particular construction, and so you should never, ever, ever use it, and I'm going to repeat this throughout this module, and in fact, in the next segment, I'll show you a number of attacks on this particular implementation. Okay, so what I would like you to remember is that you should be using an encryption system like the ISO standard, and you should never apply the trapdoor function directly to the message M. Although in the next segment we'll see other ways to encrypt using a trapdoor function that are also correct, but this particular method is clearly incorrect. Okay, so now that we understand how to build public key encryption given a trapdoor function, the next question is how to construct trapdoor functions, and we're going to do that in the next segment. In the previous segment, we saw how to build public key encryption from trapdoor functions. In this segment, we're going to build a classic trapdoor function called RSA. But first, let's quickly review what a trapdoor function is. So recall that a trapdoor function is made up of three algorithms. There's a key generation algorithm, the function itself, and the inverse of the function. The key generation algorithm outputs a public key and a secret key, and in this case, in this lecture, the public key is going to define a function that maps the set X onto itself, which is why I call these things trapdoor permutations as opposed to trapdoor functions, simply because the function maps X onto itself, whereas a trapdoor function might map the set X to some arbitrary set Y. Now, given the public key, the function, as we say, basically defines this function from the set X to the set X, and then given the secret key, we can invert this function. So this function f evaluates the function in the forward direction, and this function f inverse, which needs the secret key sk, computes f in the reverse direction. Now we say that the trapdoor permutation is secure if the function defined by the public key is in fact a one-way function, which means that it's easy to evaluate, but without the trapdoor, the secret trapdoor, it's difficult to invert. Before we look at our first example of a trapdoor permutation, I want to do a quick review of some necessary arithmetic facts that we're going to need. And in particular, let's look at some arithmetic facts modulo composites. So here we have our modulus n, which happens to be a product of two primes, and you should be thinking of p and q as roughly equal size numbers. So in particular, p and q are both roughly on the size of square root of n. So both are roughly the same size. Recall that we denoted by Zn the set of integers from 0 to n minus 1, and we said that we can do addition and multiplication modulo n. We denoted by Zn star the set of invertible elements in Zn. So these are all the elements which have a modular inverse. And we said that actually x is invertible if and only if it's relatively prime to n. Moreover, I also told you that the number of invertible elements in Zn star is denoted by this function phi of n. So phi of n is the number of invertible elements in Zn star. And I told you that when n is a product of two distinct primes, then in fact phi of n is equal to p minus 1 times q minus 1. And if you expand it out, you see that this is really equal to n minus p minus q plus 1. Now remember that I said that p and q are on the order of square root of n, which means that p plus q is also on the order of square root of n, which means that really phi of n is on the order of n minus 2 square root of n. So, in other words, it's very, very close to n. Basically, subtracting square root of n from a number. This is from, n is going to be a huge number in our case, like 600 digits. And so subtracting from a 600-digit number, the square root of that 600-digit number, namely a 300-digit number, hardly affects the size of the number, which means that phi of n is really, really, really close to n. And I want you to remember that because we'll actually be using this now and again. And so the fact that phi of n is really close to n means that if we choose a random element modulo n, it's very, very, very likely to be in Zn star. So it's very unlikely that by choosing a random element in Zn, we'll end up choosing an element that's not invertible. Okay? So just remember that in fact, almost all elements in Zn are actually invertible. And the last thing that we'll need is Euler's theorem, which we covered last week, which basically says that for any element x in Zn star, if I raise x to the power of phi of n, I get 1 in Zn. So in other words, I get 1 modulo n. I'll say it one more time because this is going to be critical for what's coming. Again, x to the phi of n is equal to 1 modulo n. So now that we have the necessary background, we can actually describe the RSA trapdoor permutation. This is a classic construction in cryptography. It was first published in Scientific American back in 1977. This is a very well-known article in cryptography. And ever since then, this was 35 years ago, the RSA trapdoor permutation has been used extensively in cryptographic applications. For example, SSL and TLS use RSA both for certificates and for key exchange. There are many secure email systems and secure file systems that use RSA to encrypt emails and encrypt files in the file system. And there are many other applications of this system. So this is a very, very classic crypto construction, and I'll show you how it works. I should say that RSA is named for its inventors, Ron Rivest, Adi Shamir, and Len Adelman, who were all at MIT at the time they made this important discovery. So now we're ready to describe the RSA trapdoor permutation. To do that, I have to describe the key generation algorithm, the function f, and the function f inverse. So let's see. So the way the key generation algorithm works is as follows. What we do is we generate two primes, p and q. Each would be, say, on the order of 1,000 bits, so roughly 300 digits. And then the RSA modulus is simply going to be the product of those two primes. The next thing we do is we pick two exponents, e and d, such that e times d is 1 modulo phi of n. What this means is that e and d, first of all, are relatively prime to phi of n. And second of all, they're actually modular inverses of one another, modulo phi of n. And then we output the public key as the pair n comma e, and the secret key is the pair n comma d. I should mention that the exponent e, that the number e is sometimes called the encryption exponent, and the exponent d is sometimes called the decryption exponent. And you'll see why I keep referring to these as exponents in just a second. Now, the way the RSA function itself is defined is really simple. For simplicity, I'm going to define it as a function from Zn star to Zn star. And the way the function is defined is simply given an input x. All we do is we simply take x and raise it to the power of e in Zn. So we just compute x to the e modulo n. That's it. And then to decrypt, what we do is we simply, given an input y, we simply raise y to the power of d modulo n. And that's it. So now you can see why I refer to e and d as exponents. They're the things that x and y are being raised to. So let's quickly verify that f inverse really does invert the function f. So let's see what happens when we compute y to the d. So suppose y itself happens to be the RSA function of some value x, in which case what y to the d is really RSA of x to the power of d. Well, x by itself is simply going to be x to the e modulo n, and therefore y to the d is simply x to the e times d modulo n. Again, just using rules of exponentiation, the exponents multiply, so we get x to the e times d. But what do we know about e times d? E times d we said is 1 modulo phi of n, and what that means is there exists some integer such that e times d is equal to k times phi of n plus 1. This is what it means that e times d is 1 modulo phi of n. So we can simply replace e times d by k times phi of n plus 1. So that's what I wrote here. So we have x to the power of k times phi of n plus 1. But now again, just using rules of exponentiation, we can rewrite this as x to the power of phi of n to the power of k times x. This is really the same thing as k times phi of n plus 1 in the exponent. I just kind of separated the exponent into its different components. Now x to the phi of n, by Euler's theorem, we know that x to the phi of n is equal to 1. So what is this whole product here equal to? Well, since x to the phi of n is equal to 1, 1 to the k is also equal to 1, so this whole thing over here is simply equal to 1, and what we're left with is x. So what we just proved is that if I take the output of the RSA function and raise it to the power of d, I get back x, which means that raising to the power of d basically inverts the RSA function, which was what we wanted to show. So that's it. That's the whole description of the function. We described the key generation, the function itself, which is simply raising things to the power of e modulo n, and the inversion function, which is simply raising things to the power of d, also modulo n. The next question is, why is this function secure? In other words, why is this function one way if all I have is just a public key, but I don't have the secret key? And so to argue that this function is one way, we basically state the RSA assumption, which basically says that the RSA function is a one-way permutation. And formally, the way we state that is that basically for all efficient algorithms A, it so happens that if I generate two primes P and Q, random primes P and Q, I multiply them to get the modulus n, and then I choose a random y in z n star, and now I give the modulus, the exponent, and this y to algorithm A, the probability that I'll get the inverse of RSA at the point y, namely I'll get y to the power of 1 over e, that's really what the inverse is, this probability is negligible. So this assumption is called the RSA assumption. It basically states that RSA is a one-way permutation just given the public key, and therefore it is a trapdoor permutation because it has a trapdoor and makes this easy to invert for anyone who knows the trapdoor. So now that we have a secure trapdoor permutation, we can simply plug that into our construction for public key encryption and get our first real-world public key encryption system. And so what we'll do is we'll simply plug the RSA trapdoor permutation into the ISO standard construction that we saw in the previous segment. So if you recall, that construction was based on a symmetric encryption system that had to provide authenticated encryption. And it was also based on a hash function that mapped, transferring it into the world of RSA, it maps elements in Zn into secret keys for the symmetric key system. And now the way the encryption scheme works is really easy to describe. Basically, algorithm G just runs the RSA key generation algorithm and produces a public key and a secret key, just as before. So you notice the public key contains the encryption exponent and the secret key contains the decryption exponent. And the way we encrypt is as follows. Well, we're going to choose a random x in Zn. We're going to apply the RSA function to this x. We're going to deduce a symmetric key from this x by hashing it. So we compute h of x to obtain the key k. And then we output this y along with the encryption of the message under the symmetric key k. And in practice, the hash function h would be just implemented using SHA-256, and you would use the output of SHA-256 to generate a symmetric key that could then be used for the symmetric encryption system. So that's how we would encrypt, and then the way we would decrypt is pretty much as we saw in the previous segment. The first thing we would do is we would use the secret key to invert the header of the ciphertext. So we would compute RSA inverse of y. That would give us the value x. Then we would apply the hash function to x so that this would give us the key k. And then we would run the decryption algorithm for the symmetric system on the ciphertext, and that would produce the original message m. And then we stated a theorem in the previous segment to say that if the RSA trapdoor permutation is secure, ES and DS, the symmetric encryption scheme, provides authenticated encryption. And as we said, H is this random oracle. It's a kind of a random function from Zn to the key space. Then in fact, this system is chosen ciphertext secure and is a good public key system to use. So now that we have our first example of a good public key system to use, I want to quickly warn you about how not to use RSA for encryption. And this is, again, something that we said in the previous segment, and I'm going to repeat it here, except I'm going to make it specific to RSA. So I like to call this textbook RSA, which basically is the first thing that comes to mind when you think about encrypting using RSA. Namely, the secret key and the public key would be as before, but now instead of running through a hash function to generate a symmetric key, what we would do is we would directly use RSA to encrypt the given message m, and then we would directly use the decryption exponent to decrypt the ciphertext and obtain the plaintext m. I'm going to call this textbook RSA because there are many textbooks that describe RSA encryption in this way, and this is completely wrong. This is not how RSA encryption works. It's an insecure system. In particular, it's deterministic encryption, and so it can't possibly be semantically secure. But in fact, there are many attacks exist, and I'm going to show you an attack in just a minute. But the message that I want to make clear here is that RSA, all it is a trapdoor permutation. By itself, it's not an encryption system. You have to embellish it with this ISO standard, for example, to make it into an encryption system. By itself, all it is just a function. So let's see what goes wrong if you try to use textbook RSA. In other words, if you try to encrypt a message using RSA directly. And I'll give you an example attack from the world of the web. So imagine we have a web server, and the web server has an RSA secret key. Here it's denoted by N and D. And here we have a web browser who's trying to establish a secure session, a secure SSL session with the web server. So the way SSL works is that the web browser starts off by sending this client hello message saying, hey, I want to set up a secure session with you. The web server responds with a server hello message that contains the server's public key. And then the web browser will go ahead and generate a random, what's called a pre-master secret K. It will encrypt the pre-master secret using K and send the resulting ciphertext over to the web server. The web server would decrypt, and then the web server would also get K. So now the two have a shared key that they can use to then secure a session between them. So I want to show you what goes wrong if we directly use the RSA function for encrypting K. In other words, if directly K is encrypted as K to the E modulo N. So just for the sake of the argument, let's suppose that K is a 64-bit key. We're going to treat K as an integer in the range 0 to 2 to the 64, or more precisely, 2 to the 64 minus 1. And now what we're going to do is the following. First of all, suppose it so happens that K factors into a product of roughly equal size numbers. So K we can write as K1 times K2, where K1 and K2 are integers and both are, say, less than 2 to the 34. And it turns out this happens with probability roughly 20%. So 1 in 5 times, K can actually be written in this way. But now if we plug this K equals K1 times K2, if we plug that into the equation that defines the ciphertext, you see that we can simply substitute K by K1 times K2, and then we can move K1 to the other side. So then we end up with this equation here, namely C over K1 to the E is equal to K2 to the E. You notice if I multiply both sides by K1 to the E, I get that C is equal to K1 times K2 to the E, which is precisely this equation here. Okay, so all I did is I just replaced K by K1 times K2 and then divided by K1 to the E. So by now this should look familiar to you. So now we have two variables in this equation. Of course, C is known to the attacker, E is known to the attacker, and N is known to the attacker. The two variables in this equation are K1 and K2, and we've separated them into different sides of the equation, and as a result we can do now a meet in the middle attack on this equation. So let's do the meet in the middle attack. What we would do is we would build a table of all possible values of the left-hand side, so all possible values of C over K1 to the E. There are 2 to the 34 of them. And then for all possible values of the right-hand side, namely for all possible values of K2 to the E, we're going to check whether this value here lives in the table that we constructed in step 1. And if it is, then we found a collision, and basically we have a solution to this equation. So as soon as we find an element of the form K2 to the E that lives in the table that we built in step 1, we've solved this equation, and we found K1 and K2. And of course, once we found K1 and K2, we can easily recover K simply by multiplying them. So then we multiply K1 and K2, and we get the secret key K. Okay, so we've broken basically this encryption system. And how long did it take? Well, by brute force, we could have broken it in time 2 to the 64 simply by trying all possible keys. But this attack, you notice it took 2 to the 34 time for step number 1. Well, it took a little bit more than 2 to the 34 because we had to do these exponentiations. It took 2 to the 34 time for step 2. Again, slightly more than 2 to the 34 because of the exponentiations. So let's say that the whole algorithm took time 2 to the 40. The point is that this is much, much less time than 2 to the 64. So here you have an example where if you encrypt using RSA directly, in other words, you directly compute K to the E mod n, instead of going through the ISO standard, for example, then you get an attack that runs much faster than exhaustive search. You get an attack that runs in time 2 to the 40 rather than time 2 to the 64. Okay, so this is a cute example of how things can break if you use the RSA trapdoor permutation directly to encrypt a message. So the message to remember here is never, ever, ever use RSA directly to encrypt. You have to go through an encryption mechanism, for example, like the ISO standard. And in fact, in the next segment, we're going to see other ways of using RSA to build public key encryption. In this segment, I want to show you how RSA is used in practice, and in particular, I want to tell you about a standard called Public Key Cryptography Standard Number 1, PKCS1. So I've already told you a couple of times that you should never use what's called textbook RSA. You should never directly encrypt a message using RSA because that's insecure. You always have to do something to the message before you actually apply the RSA function. We saw the ISO standard in a previous segment where what we did is we generated a random X, encrypted X using RSA, and then from this X we derived a symmetric encryption key. But that's actually not how RSA is used in practice. In practice, things work a little differently in that typically what happens is the system generates a symmetric encryption key, and then RSA is asked to encrypt the given symmetric encryption key rather than generating the symmetric key as part of RSA encryption. So in practice, as I say, what happens, the RSA system is given as input a symmetric encryption key to encrypt. For example, this could be an AES key that would be like 128 bits. And then the way this key is actually encrypted is first we take these 128 bits and we expand them into the full modular size. For example, this would be 2048 bits. And then we apply the RSA function. And so the question is, how should this pre-processing be done? How should we expand the 128-bit AES key that was given to us into a 2048-bit value that can then be applied with RSA? And then furthermore, the question is, how do we argue that the resulting system is secure? So an old way of doing it, which is actually very widely deployed in practice, is what's called PKCS1 version 1.5. Public Key Cryptography Standards. That's what PKCS stands for. So I want to show you how this mechanism works, and in particular I'll show you what's called PKCS1 Mode 2. Mode 2 denotes encryption, Mode 1 denotes signatures. So here we're going to just focus on encryption. So the way PKCS1 works is as follows. You take your message, this would be the 128-bit AES key for example, and you put it as the least significant bit of the value that you're creating. The next thing you do is you append 16 bits of 1 to it, FF, this is 16 bits of 1. And then the next thing you do is you append a random pad that actually does not contain FF anywhere inside the random pad. So this is basically something like on the order of, 1900 random bits, except that there are no FFs inside those random bits. And finally, at the very top, you put the number 02. This indicates that this plaintext has been encoded using PKCS1 Mode 2. And then this whole value here, this whole thing that we just created, this is this 2048-bit string, is the thing that gets fed into the RSA function and is raised to the power of e modulo n. And the resulting thing is the PKCS1 ciphertext. Now the decryptor, of course, is going to invert the RSA function. He's going to get back this blob. He's going to look at the most significant bits and he's going to say, there's a 02 in there. That means that this is PKCS1 formatted. Since it's PKCS1 formatted, it's going to remove those 02. It's going to remove all the random pad up until the FF. And then anything that stays beyond that is the original message, which is then used, to say, decrypt the actual body of the ciphertext. And as I said, this mechanism is extremely widely deployed. For example, it's used in HDPS. Now, interestingly, this PKCS1 version 1.5 was designed in the late 80s. There was really no security proof to argue that this mechanism is in fact secure. And as it turns out, as is very common when there is no security proof, it turns out that actually things break. And there's a very, very elegant attack due to Bleichenbacher back in 1998, Daniel Bleichenbacher, which shows how to attack PKCS1 when it's used, for example, inside of HDPS. So let's see how the attack works. So the idea is this. Suppose the attacker intercepted a certain ciphertext. So this is a PKCS1 ciphertext. So the plaintext is encoded using PKCS1, and then the result is fed into the RSA function, and we call the ciphertext the output of the RSA function. The attacker wants to basically decrypt the ciphertext. So let me show you abstractly what the attacker is going to do. We're going to just simplify SSL and just say that the attacker can basically send the ciphertext directly to the web server. The web server is going to try and decrypt the ciphertext using its secret key. And then what is it going to do? Well, the first thing he does after decryption, it's going to ask, is the decryption of the ciphertext PKCS1 encoded? In other words, it's going to look at the most significant bits and ask, is there a 02 in the most significant positions? If there are, it's going to continue properly decrypting and then continuing with the protocol. And if there is no 02 with those positions, it's going to announce an error. So if the most significant bits of the plaintext are 02, it's going to continue with the protocol as expected. If the most significant bits are not 02, it's going to send back an error message and tell the attacker, hey, you sent me an invalid ciphertext. Now the amazing thing is that this lets the attacker test whether the 16 most significant bits of the decryption of a given ciphertext are 02 or not. In other words, the attacker can submit whatever ciphertext he wants to the web server. The web server will invert the RSA function and then tell the attacker whether the inversion started with 02 or not. So it in some sense gives the attacker an oracle that lets him test whether the inversion of any ciphertext begins with 02 or not. And it turns out that's actually enough to completely decrypt any ciphertext the attacker wants. Just that little bit of information leakage, just by properties of RSA, lets the attacker completely decrypt a given ciphertext C. Well, so here's what the attacker is going to do. Well, he has a ciphertext that he wants to decrypt. So what he'll do is he'll take his ciphertext and, of course, feed that directly into the web server and ask, does it begin with a 02 or not? The next thing he's going to do is he's going to choose a random value r, and he's going to build a new ciphertext C prime, which is r to the e times c, modulo n. Now what does that do? If we pull the r into the RSA function, really what we just did is we multiplied the RSA plaintext, the PKCS1 encoding of m, we multiplied that by r, and that whole thing gets raised to the power of e. Okay, so that's the effect of multiplying c by r to the e. It multiplies the plaintext by r, a value that the attacker controls. And then he's going to send C prime to the web server, and the web server is going to say, yes, this starts with 02, or no, this doesn't start with 02. So now we can abstract this problem to something more general, which you can think of as the following. So I have this number x in my head. This is the number I'm trying to get, the PKCS1 encoding of m. I'm thinking of this number x, and then what I let you do is for arbitrary r's of your choice, I will tell you whether r times x mod n starts with 02 or not. And it turns out by asking enough questions, it turns out you need about 1 million questions of this type, you can basically recover all of x. Just by learning whether r times x begins with 02 or not, by asking enough questions, you can actually recover x. So in reality, what this means is that the attacker can capture a given ciphertext. This maybe correspond to a ciphertext where the user entered a credit card number or a password, and now the attacker wants to decrypt the ciphertext. What he would do is he would send about 1 million ciphertexts like this. The web server for each ciphertext is going to respond whether the plaintext begins with 02 or not, and at the end of the attack, the attacker just walks away with the decryption of the ciphertext C. So this might seem a little magical to you. How are you able to, just from learning whether the most significant bits are 02 or not, how are you able to recover the entire plaintext? So let me show you a simple example of this. I'll call this baby ablation blocker just to kind of get the idea across for how this attack might work. So imagine that the attacker is able to send the ciphertext C. The web server is going to use his secret key to decrypt, but let's suppose that instead of checking for a 02 or not, all the web server does is he asks, is the most significant bit 1 or not? If the most significant bit is 1, the web server says yes. If the most significant bit is not 1, the web server says no. Moreover, to simplify things, let's assume that the RSA modulus n is a power of 2. So n is equal to 2 to the little, and of course this is not a valid RSA modulus. An RSA modulus needs to be a product of 2 distinct primes. But again, just to keep things simple, let's pretend for a second that n is actually a power of 2. So now you realize that by sending the ciphertext C over to the web server, the adversary just learned the most significant bits of the plaintext x. Basically, the server's behavior completely reveals what the most significant bit is. Now what the attacker can do is he can multiply the ciphertext by 2 to the e. Now multiplying by 2 to the e has the effect of multiplying the plaintext x by 2. Simply multiplying x by 2. And because we're working mod 2 to the n, multiplying by 2 basically means shift left. Okay, so now when we shift left, in fact, we get to learn now the most significant bits of 2x, which is really the second most significant bit of x. Okay, so again, the most significant bit of 2x, basically we shift x to the left and we reduce modulo n. So now the most significant bit of 2x modulo n is basically the second most significant bit of x. So now we learned another bit of x. And now we're going to repeat this again. We're going to query at 4 to the e times c. That corresponds to querying at 4x to the power of e. Querying at 4x basically reveals the most significant bit of 4x mod n. 4x multiplying by 4 corresponds to shifting by 2 bits, which means that now we get to learn the third most significant bit of x. And we repeat this again and again and again for different multiples of c, and you can see that after just a few queries, about 1,000 or 2,000 queries, we'll recover all of x. The reason Bleichenbacher needed about 1,000,000 queries is because he wasn't testing for 1, he was actually testing for 0, 2, or not 0, 2, and that basically means that he needs, instead of 2,000 queries, he needs actually 1,000,000 queries, but that's still enough to recover all of the plaintext x. Okay, so I hope this explains why this attack is possible, why just this little bit of information about the most significant bits of the RSA inverse is enough to completely decrypt RSA. So the bottom line here is that PKCS1, as implemented in web servers up until this attack was discovered, was basically insecure because the attacker could essentially decrypt any ciphertext he wants just by issuing enough queries to the web server. So how do we defend against this attack? Well, so in the SSL community basically wanted the minimum change to their code that would prevent this attack from working. And so if you look at the RFC, what they propose is the following. Well, there's a lot of text here, but basically what they propose is to say that if after you apply the RSA decryption, you get a plaintext that's not PKCS1 encoded. In other words, it doesn't start with 0, 2. What you're supposed to do is basically choose some random string R and just pretend that the plaintext is this random string R and continue as if nothing happened. And of course, the protocol will fail later on. So to be concrete, you see if the PKCS1 encoding is not correct, what you would do is you would just say the pre-master secret is this random string R that we just picked out of thin air, and let's continue the protocol. And of course, the session setup will fail because the client and the server will end up agreeing on different keys, and that will cause the session to terminate. So we actually don't tell the attacker whether the plaintext begins with 0, 2 or not. All we do is we just pretend that the plaintext is some random value. So this was a minor code change to many web servers, and it was fairly easy to get deployed. And in fact, most web servers out there today implement this version of PKCS1. However, this kind of raises the question of whether PKCS1 should be changed altogether so that we actually are able to prove chosen ciphertext security. And that brings us to a different way of doing encryption using RSA, which is called optimal asymmetric encryption padding, OAEP. And in fact, the PKCS standard was updated, and PKCS1 version 2.0 actually has support for OAEP, which is a better way of doing RSA encryption. So let me explain how OAEP works. So OAEP is due to Belara and Rogaway back in 1994. And the way OAEP works is as follows. So you take your message that you want to encrypt. This, for example, could be the 128-bit AES key. And then the first thing you do is you append a short pad to it. So in this case, you put a 0, 1 at the beginning, and then you append a whole bunch of zeros. How many zeros is actually depends on the standard, but let's suppose that there are like 128 zeros in here. And then you also choose a random value so that this whole string is as big as your RSA modulus. So let's just say this is 2047 bits. Now, before you apply the RSA function, you first of all take the random value that you chose and you feed it into a hash function. This hash function produces a value that's as big as the left-hand side of your encoding. You XOR the outputs. You feed the result into another hash function, which we call G. You XOR that with a random value. And then finally, you get these two values that you can concatenate together. Okay, so you concatenate the left side and the right side. That gives you something that, say, is 2047 bits long. And that's the thing that you apply the RSA function to. And the result is the RSA encryption. Now, there's a theorem that was proved in 2001 due to Fujisaki, Okamoto, Poinchevel, and Stern that shows that, in fact, if all you do is you assume that the RSA function is a trapdoor permutation, a secure trapdoor permutation, that, in fact, this mode of encrypting using RSA is, in fact, chosen ciphertext secure. But we have to assume that the functions h and g are kind of ideal hash functions. And as I said, these are called random oracles. Basically, we assume that h and g are just random functions from their domain to their range. In practice, of course, when OAEP is implemented, people just use SHA-256, say, for h and g. Why is this called optimal asymmetric encryption padding? Why is this O? Why does it stand for optimal? Well, the reason is if you look at the ciphertext, you notice that the ciphertext is basically as short as it can be. The ciphertext is exactly the length of one RSA output. There are no trailing values that are appended to the ciphertext. Whereas, for example, the ISO standard, if you remember, even if you had to encrypt a very short message, what you would have to do is you would have to encrypt X using RSA, and then append to that X the encryption of the short message under the symmetric encryption system. So even if you have just to encrypt a 128-bit AES key, with the ISO standard you would get one RSA output plus a symmetric cipher. Whereas with OOEP, you just get one RSA output and nothing else. So in that sense, it's optimal. Optimal in terms of the length of the ciphertext. Interestingly, this theorem here really relied on properties of RSA, and in fact, this theorem is known to be false if you use a general trapdoor permutation, some other permutation that doesn't have the algebraic properties of RSA. So that left this question of, if we have a general trapdoor permutation, what is the correct way to do OOEP? And it turns out there's a minor modification to OOEP which makes the result more general. This is a result due to Shoup back in 2001. Just shows that if you give me a general trapdoor permutation F, it turns out if you replace the fixed pad that's used in OOEP by a hash function, this hash function W, which happens to be a hash function of the message M and the randomness R that you're encrypting with, and then during decryption, you actually check that this hash function value is correct. So when you decrypt, you actually check that W of MR is really what's written in this position in the plaintext. If you do that, then basically this OEP called OEP plus is in fact CPA-secure, it's chosen ciphertext secure for any trapdoor permutation. You don't have to rely on specific properties of RSA. There's another result called simple asymmetric encryption padding, SAEP+, which basically says that if you are going to rely on properties of RSA, then in particular with RSA when the public exponent is equal to 3, it turns out you actually don't need a second stage of encryption. The simple padding scheme here, again using the function W, is actually already enough to guarantee chosen ciphertext security. So these are variants of OEP, but they're not really used. I just wanted to mention, and so that you know they exist. These are not really used. Mainly OEP has been standardized, is what's used, although again in reality the most common application of RSA for public encryption is in fact this PKCS1 that's standardized in the HTTPS RFC. So just to make sure it's clear in your mind how decryption actually works, let me ask you, how would you decrypt an SAEP ciphertext CT? So here you're given the ciphertext CT here, and the question is which of these three methods is the correct way of decrypting the ciphertext? So the correct answer is the first one, and let's see why. Well, given the ciphertext, the first thing we would need to do is apply the RSA inverse function to ciphertext, and that would give us the RSA plaintext, which happens to be in this case X and R. So we get these X and R here. The next thing we need to do is we need to hash R using the function H and XOR the result with X, and that would give us M and WM comma R. And the last thing we need to do is to make sure that the pad WMR is correct. So we check that in fact W is equal to WMR, and if so we output M, and if not we output bottom to say that the ciphertext is invalid and the decryption algorithm rejects it. And by the way, I'd like to emphasize that this checking of the pad during decryption is crucial in all these schemes that we just saw. So for example, in both OEP plus and SAEP plus, it's during decryption it's very important to check that the pad is in fact correct, so that the value of W that you get here during encryption really is the hash under capital W of M and R. And similarly in OEP, it's very important to check that during decryption, in fact, the value of the pad is the constant 010000000. And of course, if it happens to be not 01000, then you output bottom and you say the ciphertext is invalid. The last thing I want to point out is that actually implementing OEP can be quite tricky, and let's see why. So suppose you have you write an OEP decryption routine that takes the ciphertext as input. The first thing you would do is you would apply the RSA inverse function to the ciphertext, and you would say, well, you expect to get an n-bit value out, 2047 bits in the case of a 2048-bit RSA modulus, and if you get something that's bigger than 2 to the 2047, you say reject. We say error equals 1, and we go to exit. The next thing we're going to do is we're going to check whether the pad is in fact the correct pad. And again, if the pad is not the correct pad, then again, we're going to reject and go to exit. The problem with this implementation is, well, by now I hope you kind of guessed it, is that it's vulnerable to a timing attack, right? So essentially by leaking timing information, the attacker can now figure out what caused the error. Was there an error because the RSA decryption happened to be too big, or was there an error because the pad happened to be too large? And if the attacker can distinguish these two errors, say by timing, then it turns out, similar to the Bleichen-Bacher attack, it's possible to completely decrypt any ciphertext of your choice. Just that very, very, very small leak of information would completely allow the attacker to decrypt completely any ciphertext he wants to. So this shows that even if you implement the mathematics of OEP decryption correctly, you can very easily mess up and open yourself up to a timing attack, which would make your implementation completely insecure. So as usual, the lesson is don't implement crypto yourself. In particular, RSA OEP is particularly dangerous to implement yourself. Just use one of the standard libraries. For example, OpenSSL has an OEP implementation. And of course, what they do is they're very careful to make sure that the running time of OEP decrypt is always the same, no matter what causes the error. Okay, so we'll stop here, and then in the next segment, we'll talk about the security of the RSA trapdoor permutation. The next question we're going to ask is RSA really a one-way function? In other words, is it really hard to invert RSA without knowing the trapdoor? So if an attacker wanted to invert the RSA function, well, what the attacker has is basically the public key, namely he has n and e, and now he's given x to the e, and his goal is to recover x. Okay, so the question really is, given x to the e modulo n, how hard is it to recover x? So what we're really asking is, how hard is it to compute eth roots modulo a composite? If this problem turns out to be hard, then RSA is in fact a one-way function. If this problem turns out to be easy, which of course we don't believe it's easy, then RSA would actually be broken. So it turns out the best algorithm for this problem requires us to first factor the modulus n, and then once we factor the modulus, we've already seen last week that it's easy to compute the eth root modulo p, it's easy to compute the eth root modulo q, and then given both those eth roots, it's actually easy to combine them together using what's called the Chinese remainder theorem and actually recover the eth root modulo n. So once we're able to factor the modulus, computing eth roots modulo n becomes easy, but factoring the modulus, as far as we know, is a very, very difficult problem. But a natural question is it true that in order to compute eth roots modulo n, we have to factor the modulus n? As far as we know, the best algorithm for computing eth roots modulo n requires factorization of n, but who knows, maybe there's a shortcut that allows us to compute eth roots modulo n without factoring the modulus. To show that that's not possible, we have to show a reduction. That is, we have to show that if I give you an efficient algorithm for computing eth roots modulo n, that efficient algorithm can be turned into a factoring algorithm. So this is called a reduction, namely given an algorithm for eth roots modulo n, we obtain a factoring algorithm, and that would show that one cannot compute eth roots modulo n faster than factoring the modulus. If we had such a result, it would show that actually breaking RSA, in fact, is as hard as factoring. But unfortunately, this is not really known at the moment. And in fact, this is one of the oldest problems in public key crypto. And so let me just give you a concrete example. Suppose I give you an algorithm that will compute cube roots modulo n. So for any x in Zn, the algorithm will compute the cube root of x modulo n. And my question is, can you show that using such an algorithm, you can factor the modulus n? And even that's not known. What is known, I'll tell you, is, for example, that for e equals 2, that is, if I give you an algorithm for computing square roots modulo n, then in fact that does imply factoring the modulus. And so computing square roots is in fact as hard as factoring the modulus. Unfortunately, if you think back to the definition of RSA, that required that e times d be 1 modulo phi of n. And what that means is that e necessarily needs to be relatively prime to phi of n. Right? What the first equation says is that e is invertible modulo phi of n, but if e is invertible modulo phi of n, necessarily that means that e must be relatively prime to phi of n. But phi of n, if you remember, that's equal to p minus 1 times q minus 1, and since p and q are both large primes, p minus 1 times q minus 1 is always even. And as a result, the GCD of 2 and phi of n is equal to 2, because phi of n is even. and therefore the public exponent 2 is not relatively prime to phi of n, which means that even though we have a reduction from taking square roots to factoring, e equals 2 cannot be used as an RSA exponent. So really the smallest RSA exponent that's legal is in fact e equals 3, but for e equals 3, the question of whether computing cube roots is as hard as factoring is an open problem. It's actually a lot of fun to think about this question, so I would encourage you to think about it just a little bit. That is, if I give you an efficient algorithm for computing cube roots, modulo n, can you use that algorithm to actually factor the modulus n? I'll tell you that there is a little bit of evidence to say that a reduction like that actually doesn't exist, but it's very, very weak evidence. What this evidence says is basically if you give me a reduction of a very particular form, in other words, if your reduction is what's called algebraic, I'm not going to explain what that means here, that is, if given a cube root oracle, you could actually show me an algorithm that would then factor, that reduction by itself would actually imply a factoring algorithm. Okay, so that would say that if factoring is hard, a reduction actually doesn't exist. But as I say, this is very weak evidence, because who's to say that the reduction needs to be algebraic? Maybe there are some other types of reductions that we haven't really considered. So I would encourage you to think a little bit about this question. It's actually quite interesting. How would you use a cube root algorithm to factor the modulus? But as I said, as far as we know, RSA is a one-way function, and in fact, breaking RSA, computing ETH roots, that is, actually requires factoring the modulus. We all believe that's true, and that's the state of the art. But now there's been a lot of work on trying to improve the performance of RSA, either RSA encryption or improve the performance of RSA decryption. And it turns out there's been a number of false starts in this direction. And so I want to show you this wonderful example as a warning. And so this is an example of how not to improve the performance of RSA. So you might think that if I wanted to speed up RSA decryption, remember decryption is done by raising the ciphertext to the power of d, and you remember that the exponentiation algorithm ran in linear time in the size of d, linear time and log of d. So you might think to yourself, well, if I wanted to speed up RSA decryption, why don't I just use a small d? I'll say a decryption exponent that's on the order of 2 to the 128. So it's clearly big enough so that exhaustive search against d is not possible. But normally, the decryption exponent d would be as big as the modulus, say 2,000 bits. By using a d that's only 128 bits, I basically speed up RSA decryption by a factor of 20. Right? I went down from 2,000 bits to 100 bits. So exponentiation would run 20 times as fast. It turns out this is a terrible idea. Terrible, terrible idea. In the following sense, there's an attack by Michael Wiener that shows that in fact, as soon as the private exponent d is less than the fourth root of the modulus, let's see, if the modulus is around 2048 bits, that means that if d is less than 2 to the 512, then RSA is completely insecure. And it's insecure in the worst possible way, namely, just given a public key n and e, you can very quickly recover the private key d. Well, so some folks said, well, this attack works up to 512 bits, so why don't we make the modulus, say, 530 bits? Then this attack actually wouldn't apply, but still we get to speed up RSA decryption by a factor of 4 because we shrunk the exponent from 2,000 bits to, say, 530 bits. Well, it turns out even that's not secure. In fact, there's an extension to Wiener's attack that's actually much more complicated that shows that if d is less than n to the 0.292, then also RSA is insecure. And in fact, the conjecture is that this is true up to n to the 0.5. So even if d is like n to the 0.4999, RSA should still be insecure, although this is an open problem. It's, again, a wonderful open problem. It's been open for 14 years now, and no one can progress beyond this 0.292. Somehow, it seems kind of strange. Why would 0.292 be the right answer, and yet no one can go beyond 0.292? So just to be precise, when I say that RSA is insecure, what I mean is just given the public key n and e, your goal is to recover the secret key d. If you're curious where 0.292 comes from, I'll tell you that what it is basically 1 minus 1 over square root of 2. Now, how could this possibly be the right answer to this problem? It's much more natural that the answer is n to the 0.5, but this is still an open problem. Again, if you want to think about that, it's kind of a fun problem to work on. So the lesson in this is that one should not enforce any structure on D for improving the performance of RSA. And in fact, now there's a slew of results like this that show that basically any kind of tricks like this to try and improve RSA's performance is going to end up in disaster. So this is not the right way to improve RSA's performance. Initially, I wasn't going to cover the details of Wiener's attack, but given the discussions in the class, I think some of you would enjoy seeing the details. All it involves is just some manipulating some inequalities. If you're not comfortable with that, feel free to skip over the slide, although I think many of you would actually enjoy seeing the details. So let me remind you, in Wiener's attack, basically, we're given the modulus and the RSA exponent n and e, and our goal is to recover d, the private exponent d, and all we know is that d is basically less than fourth root of n. In fact, I'm going to assume that d is less than the fourth root of n divided by 3. This 3 doesn't really matter, but the dominating term here is that d is less than the fourth root of n. So let's see how to do it. So first of all, recall that because e and d are RSA public and private exponents, we know that e times d is 1 modulo phi of n. Well, what does that mean? That means that there exists some integer k such that e times d is equal to k times phi of n plus 1. Basically, that's what it means for e times d to be 1 modulo phi of n. It's basically some integer multiple of phi of n plus 1. So now let's stare at this equation a little bit. And in fact, this equation is the key equation in the attack. And what we're going to do is, first of all, divide both sides by d times phi of n. And in fact, I'm going to move this term here to the left. So after I divide by d times phi of n, what I get is that e divided by phi of n minus k divided by d is equal to 1 over d times phi of n. Okay? So all I did is I just divided by d times phi of n, and I moved the k times phi of n term to the left-hand side. Now, just for the heck of it, I'm going to add absolute values here. Those will become useful in just a minute, but of course they don't change this equality at all. Now, phi of n, of course, is almost n. Phi of n is very, very close to n, as we said earlier. And all I'm going to need then for this fraction is just to say that it's less than 1 over square root of n. It's actually much, much smaller than 1 over square root of n. It's actually on the order of 1 over n, or even more than that. But for our purposes, all we need is that this fraction is less than 1 over square root of n. Now let's stare at this fraction for just a minute. You realize that this fraction on the left here is a fraction that we don't actually know. We know e, but we don't know phi of n, and as a result, we don't know e over phi of n. But we have a good approximation to e over phi of n, namely, we know that phi of n is very close to n, therefore e over phi of n is very close to e over n. So we have a good approximation to this left-hand side fraction, namely e over n. What we really want is the right-hand side fraction, because once we get the right-hand side fractions, basically that's going to involve d, and then we'll be able to recover d. Okay? So let's see if we replace e over phi of n by e over n, let's see what kind of error we're going to get. So to analyze that, what we'll do is first of all remind ourselves that phi of n is basically n minus p minus q plus 1, which means that n minus phi of n is going to be less than p plus q. Actually, to be precise, I should really write p plus q plus 1, but you know, who cares about this 1? It's not, it doesn't really affect anything, so I'm just going to ignore it for simplicity. Okay? So n minus phi of n is less than p plus q. Both p and q are roughly half the length of n, so you know, they're kind of both on the order of square root of n. So basically, p plus q, we'll say, is less than 3 times square root of n. Okay, so we're going to use this inequality in just a minute. But now we're going to start using the fact that we know something about d, namely that d is small. So if we look at this inequality here, d is less than the fourth root of n divided by 3. It's actually fairly easy to see. If I square both sides and I just manipulate things a little bit, it's difficult to see that this directly implies the following relation, basically 1 over 2d squared minus 1 over square root of n is greater than 3 over square root of n. As I said, this basically follows by squaring both sides, then taking the inverse of both sides, and then I guess multiplying one side by a half. Okay, so you can easily derive this relation, and we'll need this relation in just a minute. So now let's see. What we'd like to do is bound the difference of e over n and k over d. Well, what do we know? By the triangular inequality, we know that this is equal to the distance between e over n and e over phi n, plus the distance from e over phi n to k over d. Okay, this is just what's called a triangular inequality. This is just a property of absolute values. Now, this absolute value here, we already know how to bound. If you think about it, it's basically the bound that we've already derived. So we know that this absolute value here is basically less than 1 over square root of n. Now, what do we know about this absolute value here? What is e over n minus e over phi of n? Well, let's do common denominators and see what we get. So the common denominator is going to be n times phi of n And the numerator in this case is going to be e times phi of n minus n, which we know from this expression here is less than 3 times square root of n. So really what this numerator is going to be is e times 3 square root of n. The numerator is going to be less than e times 3 square root of n. So now I know that e is less than phi of n, so I know that e over phi of n is less than 1. In other words, if I erase e and I erase phi of n, I've only made the fraction larger. Okay, so this initial absolute value is now going to be smaller than 3 square root of n over n, which is simply 3 square root of n over n is simply 3 over square root of n. Okay, but what do we know about 3 over square root of n? We know that it's less than 1 over 2d squared minus 1 over square root of n. Okay, so that's the end of our derivation. So now we know that the first absolute value is less than 1 over 2d squared minus square root of n. The second absolute value is less than 1 over square root of n, and therefore their sum is less than 1 over 2d squared. And this is the expression that I want you to stare at. So here, let me circle it a little bit. So let me circle this part and this part. Now, so let's stare a little bit at this fraction here. And what we see is, first of all, as before, now we know the value of e over n. And what we'd like to find out is the value k over d. But what do we know about this fraction k over d? We know somehow that the difference of these two fractions is really small. It's less than 1 over 2d squared. Now, this turns out to happen very infrequently, that k over d approximate e over n so well that the difference between the two is less than the square of the denominator of k over d. It turns out that that can't happen very often. It turns out there are very few fractions of the form k over d that approximate another fraction so well that their difference is less than 1 over 2d squared. And in fact, the number of such fractions is going to be at most logarithmic in n. So now there's a continued fraction algorithm. It's a very famous fraction that basically what it will do is from the fraction e over n, it will recover log n possible candidates for k over d. So we just try them all one by one until we find the correct k over d, and then we're done. We're done because we know that, well, e times d is 1 mod k, therefore d is relatively prime to k. So if we just represent k over d as a rational fraction, numerator by denominator, the denominator must be d. And so we've just recovered, we've tried all possible log n fractions that approximate e over n so well that the difference is less than 1 over 2d squared. And then we just look at the denominator of all those fractions, and one of those denominators must be d. And then we're done. We've just recovered the private key. So this is a pretty cute attack, and it shows basically how if the private exponent is smaller than the fourth root of n, then we can recover d completely, and quite easily. Okay, so I'll stop here. To conclude this module, I want to say a few words about how RSA is used in practice. So first of all, if you want to speed up RSA encryption, it's perfectly fine to use a small encryption exponent e. So rather than using a random e, one can use a small value of e, and in fact the minimum value that's possible is e equals 3. So it's not difficult to see that the smallest possible value for e is in fact e equals 3. And let's see why. Well, e equals 1 is a bad idea because that's not particularly hard to invert with e equals 1. E equals 2 is not a valid RSA exponent because remember in the definition of RSA, e had to be relatively prime to phi of n. Phi of n, if you remember, is p minus 1 times q minus 1, which is an even number. If p and q are odd primes, p minus 1 times q minus 1 is an even number. But if e is even, if e is equal to 2, it's not going to be relatively prime to phi of n. So e equals 2 is not valid either. And then e equals 3 is the first minimum value that can be used. And then we just have to make sure that, in fact, p is equal to 2 mod 3 and q is equal to 2 mod 3, so that p minus 1 times q minus 1 is not divisible by 3. So in fact, this is a fine public exponent to use. However, the recommended value is 2 to the 16 plus 1, so 65537. It's a good idea to use this recommended value of e. To compute x cubed mod n, you would basically need 3 multiplications. To compute x to the 65537 mod n, using repeated squaring, you would need 17 multiplications. Basically what you would do is you would repeatedly square 16 times, and then you would multiply by x one more time. Okay, so just with 17 multiplications, you can do this exponentiation. So this is still much, much faster than using a random e, which would require something like 2,000 multiplications. So this leads us into what's called the asymmetry of RSA, where in fact the encryption is quite fast. Encryption only requires 17 multiplications. However, decryption is much, much, much slower. It requires something on the order of 2,000 multiplications. I should point out that there's a standard trick for slightly speeding up RSA decryption. This is called RSA CRT. It stands for RSA with Chinese remaindering. It's a method for speeding up RSA decryption by about a factor of 4, but nevertheless it's still going to be much, much, much slower than encryption. The ratio of encryption to decryption in RSA is roughly a factor of 10 to 30. So encryption could be up to like 30 times faster than decryption, depending on the size of your modulus. Interestingly, this is a special property of RSA where encryption is so much faster than decryption. And other public key systems, for example, in the next module we're going to look at ElGamal encryption, don't have this property where both encryption and decryption take roughly the same amount of time. We've already discussed key lengths for RSA before, so I just wanted to flash these numbers to remind you that if you're using a 128-bit AES key, really you should be using a 3000-bit modulus, although everybody just uses a 2048-bit modulus. And then if you're really using a long AES key, like a 256-bit AES key, the RSA modulus gets to be quite big. Now I wanted to mention a number of implementation attacks on RSA. These are attacks that have been demonstrated against particular mathematically correct implementations of RSA. However, these implementations were vulnerable to certain side channel attacks that make the implementation completely insecure. So the first example of this is due to Paul Kocher back in '97. He showed a timing attack where all you do is you measure the time for an RSA decryption, and simply by measuring the time, you can actually expose the secret exponent d. And so this says that if you're going to implement an RSA decryption, you had better make sure that the decryption time is independent of the arguments. Another attack, also by Paul Kocher 2 years later, showed that if you have a smart card that's implementing RSA decryption, you can actually measure the power consumption of the card while it's doing RSA decryption. And then simply by looking at the peaks and troughs, you can literally read off the bits of D one bit at a time as the smart card is running through the repeated squaring algorithm. So using a power analysis attack, it's actually fairly easy to get the secret bits of the secret key unless the smart card defends against power analysis attacks. And finally, another attack called a fault attack shows that RSA is very vulnerable to decryption errors. And in particular, if for some reason an error occurs during an RSA decryption, one error is actually completely enough to reveal the secret key. So this attack is actually fairly significant. Just one error completely reveals your secret key. And as a result, many crypto libraries will actually check the result of the RSA decryption before returning it to the caller. And the way you would check it is you would take the output of this exponentiation and simply raise it to the power of e and check that you actually get back c modulo n. And if so, you know that your decryption was done correctly. Now the reason you can do this is because, again, e is much smaller than d, therefore checking takes much less time than actually raising something to the power of d. Nevertheless, even though checking is 10 times faster than the actual decryption, this still introduces a 10% slowdown, and so sometimes this is actually turned off, but nevertheless it's actually a good idea to check that your RSA output is correctly computed. And so all these attacks kind of, again, make the point that if you just implement RSA naively, it would be mathematically correct, it would work. However, there would be all these potential attacks on the implementation, and as a result, you should never implement RSA yourself. Always use standard libraries and just use the implementation available there. So to be concrete, I wanted to show you an example of one of these attacks. And in particular, I'll show you the fault attacks on RSA. And again, this will be a fault attack on what's called RSA with Chinese remaindering. So in fact, as I said at the beginning of the segment, RSA decryption is often implemented as follows. What you do is you decrypt the ciphertext C modulo P, then you decrypt the ciphertext C modulo Q, and then you combine the two to actually get the decryption modulo N. And this combination is done using what's called a Chinese remainder theorem, which I'm not going to explain here, but it's not too difficult to see how that works. Basically, once you have the result, the decryption mod P and the decryption mod Q, you can combine it to get the decryption mod N. And it turns out this gives about a factor of 4 speed up over the naive implementation of directly doing the exponentiation modulo N. Okay, so let's see why this is vulnerable to faults. Suppose it so happens that when your decryption library is computing the decryption modulo Q, for some reason the processor makes an error. And actually what it gets is not the correct XQ, it gets an incorrect XQ. So let's call this XQ hat. However, when it computed the decryption modulo P, no error occurred. So these errors are fairly infrequent. And so let's just assume that an error occurred modulo 1 prime, but it did not occur modulo the other prime. Well, if that's the case, our computation is correct modulo P and incorrect modulo Q. That says that when we combine the two results, we're actually going to get an output, I'll call it X prime, such that the output is correct modulo P, so X prime is really equal to C to the D mod P, but is incorrect modulo Q. If we raised both these equations to the power of E, what we obtain is the following two relations. Well, let's see, this guy we raise it to the power of E. What happens is the left-hand side becomes X prime to the E. The right-hand side, here it's C to the D. If I raise C to the D to the power of E, E and D, remember, are inverses of one another. And as a result, if I raise C to the D to the power of E, both exponents cancel out, and I simply get C back. So I know that X prime to the E is equal to C, but modulo Q, there was a mistake. So X prime to the E is not equal to C modulo Q. So therefore, if I look at this difference, X prime to the E minus C, we know that it's 0 modulo P, and it's not 0 modulo Q. So now if we compute the GCD of this value with n, what do we get? Well, as I said, this is 0 mod P, but is not equal to 0 mod Q, which means that this quantity here is divisible by P, but is not divisible by Q. So therefore, when I compute the GCD, what I'll get is simply P. And again, this is because P divides this quantity here when Q does not divide this quantity here. So now basically what I've just obtained is the factorization of n. Once I have the factorization of n, I can compute phi of n. And then given phi of n, I can actually compute myself the decryption exponent from the public key. So now I've just recovered the secret key from the public key from a single mistake that happened during decryption. So this is why typically when you do RSA decryption, it's a good idea to check the results, especially when you use Chinese remaindering to speed up RSA decryption. The last attack I want to talk about is a very recent observation that was observed by Henninger et al. And Lenstra et al. That shows that RSA key generation can be problematic when it's done with bad entropy. So here's how things go wrong. So the way OpenSSL generates RSA keys is as follows. Well, it starts by basically seeding the pseudo-random number generator, and then it uses random bits from the pseudo-random number generator to generate the first prime P. Then it will go ahead and seed the random number generator some more, and will generate bits from the pseudo-random number generator to generate Q, and finally it will output the product of P and Q. Okay, so there are two steps where we seed the pseudo-random number generator. Now suppose that this is implemented on a router or a firewall of some sort, and suppose that the key generation happens right after the firewall starts up. So the firewall boots up. At the time of the boot, there's not a lot of entropy in the pseudo-random number generator. And as a result, the firewall is likely to generate a prime P that comes from a very low entropy pool, which means that this P is going to be one of a small number of possibilities. However, after we've generated P, generating the prime actually takes a little bit of time, a few microseconds. And so by then the firewall will have generated more entropy. And so after we add more entropy to the entropy pool, the prime Q, say, is generated from a much larger entropy pool and is therefore unique to this firewall. Now the problem is that many different firewalls, if they generate an RSA key in this way, many of them will actually end up using the same prime P, but a different prime Q. So what this says is that if we look at two RSA moduli from two different firewalls, N1 and N2, if we compute the GCD of N1 and N2, well, both of them had different Qs, but the same P. So if we compute the GCD, actually we'll end up with a factorization of N, of both N1 and N2, and then we can actually figure out the private key, both for N1 and for N2. So this has actually been observed in practice. Both of these groups, what they did is they scanned the web and recovered all the public keys out there that are used on various web servers. They then ran a massive GCD using some arithmetic tricks. They were able to compute this massive GCD of all pairs of public keys N1 and N2, and lo and behold, they actually realized that a fair number of these keys have a common factor, so they were actually able to factor these moduli. So in the experiment, they were actually able to factor about 0.4% of all public SSL keys. This is an amazing fact that, in fact, so many web server public keys out there are vulnerable just because they happen to generate the RSA key using low entropy. So they have a common factor with somebody else's factor, and GCDing the two together gives you the factorization. So the lesson from all this is when you generate keys, no matter whether they're RSA keys or ElGamal keys or symmetric keys, it's crucial that the number that your generator is properly seeded. So don't generate keys immediately after startup. You have to kind of make sure the seeding of the generator has had enough time to actually generate enough entropy, and only then you can start generating keys. So this is a really nice example of how a bad random number generator can mess up your RSA public keys. Okay, so this is the end of our discussion of public key encryption from RSA. I wanted to mention a few further readings if you want to read more about this. So there's a nice paper by Victor Shoup that talks about why chosen ciphertext security is so important in the public key settings. So if the Bleichen-Bacher attack wasn't convincing enough, there are many other attacks like this that are possible if you don't use a chosen ciphertext secure system. So if you want to learn more about chosen ciphertext security, please look at Victor Shoup's paper. There's a survey that I guess I wrote a couple of years ago that looks at many different attacks on the RSA system. I guess I wrote this when RSA was 20. I actually need to update this to 30 years of attack on the RSA crypto system. There have been some developments in the last decade, but for now this is actually a decent survey to look at and read about more attacks on RSA. The OEP results that I mentioned are referenced here, OEP reconsidered. And finally, if you're interested in key length analysis of RSA and other public key systems, there's a nice paper by Arjan Lenstra that discusses how you should choose key lengths for your public key systems and even for your symmetric key systems. Okay, so those are the 4 references. I hope you have the time to look through them, and I will stop here. And in the next module, we're going to look at another family of public key encryption systems, this time based on discrete log. In the previous lecture, we looked at a public key encryption system that's built from RSA, or more generally from trapdoor functions. In this lecture, we're going to look at public key encryption schemes that are built from the Diffie-Hellman Protocol. So first, recall that a public key encryption system is made up of 3 algorithms. There's a key generation algorithm that I'll denote by gen, that basically generates a public key and a secret key. And then there are 2 algorithms, E and D, that encrypt and decrypt. And the point is the encryption algorithm encrypts using the public key, and the decryption algorithm decrypts using the secret key. The physical world analogy for public key encryption is a locked box where anyone can put a message inside the box and then lock the box. That corresponds to the public key. And then no one can open this box except the person who has the secret key that has the key can put it in the lock, unlock the box, and recover the message in the box. Now, in the previous lecture, we looked at a number of applications for public key encryption. In particular, we looked at the key exchange application. And in fact, this is how public key encryption is used in SSL, where the server sends its public key to the browser chooses a secret, and then encrypts the secret using the server's public key, sends it back to the server decrypts, and now both the browser and the server have a common secret that they can then use to encrypt data going back and forth between them. So in the interactive settings, such as in a networking protocol, public key encryption would primarily be used for setting up a shared symmetric key, which the 2 parties can then use to exchange information. However, there are many settings where interaction is simply not possible, and then public key encryption is directly used to encrypt messages. One example of this is secure email. The email system in some sense is designed to be non-interactive in the sense that the sender sends an email, the email travels from relay to relay to relay until it finally arrives at the destination, and the destination should be able to decrypt without interacting with the sender at that point. That can be done basically by the sender encrypting the message using the recipient's public key. The ciphertext would travel along the SMTP chain until it reaches the recipient. The recipient would use a secret key and recover the original sent message. However, there are many other cases where interaction is not possible, and I want to show you 2 such cases. The first example is file systems. And in fact, public key encryption is a good way to manage file sharing in an encrypted file system. So let me show you what I mean by that. So imagine we have our friend Bob here who wants to store an encrypted file on some storage server. So he'll go ahead and write the encrypted file to the storage server. What he actually writes on the server is basically the following. He will generate a random file encryption key, we'll call it K sub f, and then he will use a symmetric encryption system to encrypt the file using the key K sub f. Then he'll encrypt the key K sub f using his own public key, so public key of Bob. This will give Bob access to the file at a later time, right? Using his secret key, Bob can decrypt this header, recover K sub f, then he'll decrypt the actual encrypted file and recover the plaintext file. So decryption will work in 2 steps. However, if Bob now wants to also give access to Alice to this file, what he'll do is he'll go ahead and in addition, he'll also include in the file header an encryption of K sub f under Alice's public key. Okay, so notice that there was no interaction here. All Bob knows is Alice's public key, and yet he was able to make the file accessible to Alice at a later time. So now Bob disappears, and then Alice comes and accesses the disk at a later time. She'll read the ciphertext, decrypt her part of the header, recover KF, and then she can decrypt the symmetrically encrypted file and recover the actual file contents. Okay, so you can see that without any interaction, Bob was able to write to the file system and enable Alice to access the file as well. Again, at the time that Alice was reading the file, there's no interaction with Bob because maybe Bob is already inaccessible, and yet Alice can still read the file and recover it by herself. So another example of a non-interactive application of public key encryption is what's called key escrow. Now, key escrow may actually sound like a bad thing, but in fact, it's a mandatory feature in corporate environments. So the idea here is this. So imagine Bob writes data to a disk, and then later Bob becomes inaccessible. Maybe Bob is fired, maybe Bob is out sick, and somehow the company needs to have access to Bob's files. So having Bob be the only one able to decrypt these files is simply unacceptable in a corporate settings. The corporation might need access to those files. So the question is what to do, and the answer is to introduce this entity called a key escrow service. And the way the system then would work is as follows. Basically, when Bob writes his file to disk, his system, as it's writing the file to this shared storage medium, what it would do, of course, as before, it would encrypt the file using the file encryption key KF. It would encrypt KF using Bob's public key, but it would also encrypt KF using an escrow service. So here, the escrow service is completely offline. We never talk to it unless we actually need its services. As Bob is writing the file, all he does is he simply writes the encryption of KF under the escrow authority's public key into the file header. Now later, Bob disappears, and now the company needs to recover Bob's file. What does it do? Well, at this point, it would contact the escrow service. The escrow service would read this part of the header, use its secret key to decrypt the header and recover KF, and then use KF to decrypt the actual file. Okay, so in this way, again, you notice that the escrow service was completely offline. There was no interaction with the escrow service until the point at which the escrow services were actually needed. And again, you can see that this is a very clean and elegant application of public key encryption. So as I said in the previous lecture, we saw constructions for public key encryption based on trapdoor functions. In particular, we looked at RSA. We looked at the generic construction we call the ISO standard. We looked at constructions like OEP+, and so on and so forth. In this lecture, we're going to look at public key constructions from the Diffie-Hellman Protocol. This is another family of public key systems, and I'm going to show you how they work. These public key systems are generally called ElGamal public key encryption schemes. Taher ElGamal was actually Marty Hellman's student. He came up with this ElGamal encryption system as part of his PhD thesis. And in fact, ElGamal encryption, for historical reasons, is used in an email encryption system called GPG, the GNU Privacy Guard. As usual, when we construct public key encryption systems, our goal is to build systems that have chosen ciphertext security so that they are secure both against eavesdropping and tampering attacks. So before I show you the ElGamal system, let's do a very brief review of the Diffie-Hellman Protocol. So in my description here, I'm going to abstract it a little bit from the version that we saw last week. And in fact, I'm just going to use the concept of a finite cyclic group. In fact, we have an arbitrary finite cyclic group. For example, it could be the group ZP star, but it could also be the points of an elliptic curve. And as I mentioned, there are some benefits to doing Diffie-Hellman over an elliptic curve. But for simplicity, I'm just going to refer to G as an abstract finite cyclic group. But in your heads, you should be thinking G is the group ZP star. And let's suppose that the group has order n for some integer n. Now we're going to fix a generator G of this group, and all this means is basically if you look at the successive powers of G, then basically you get all the elements in the group G. You notice that because the group has order n, we know that G to the power of n is equal to 1, and therefore there's no reason to go beyond the n minus first power of G. G to the n is equal to 1, so that we just wrap around. Okay, so we have this cyclic group G, we have this generator whose powers give us all the elements of G, and now let me remind you how the Diffie-Hellman Protocol works. Basically what Alice does is she chooses a random A, she computes G to the A and sends that over to Bob. Bob chooses a random B, and let's see who remembers. What does Bob send over to Alice? So Bob sends over to Alice G to the B, and of course I should remind you that both G to the A and G to the B are just elements in this group G. And now they can derive a shared secret. If you remember, the shared secret is G to the AB, and these equalities here show that both sides can actually compute the shared secret given the values at their disposal. So Alice, for example, has B and she has A, and so raising B to the power of A gives her the shared secret. The attacker, of course, the poor attacker, he gets to see A and B, and his goal is now, of course, he also gets to see the generator G, and his goal now is to compute G to the AB, but we said that this is believed to be a hard problem given G, G to the A, and G to the B. In a group like ZP star, computing G to the AB is difficult. So now let's see how to convert the Diffie-Hellman protocol into an actual public key system. And as I said, this was a brilliant idea due to Tahir ElGamal. So as before, we're going to fix our cyclic group G and a generator little g inside of G. Now here I wrote the Diffie-Hellman protocol again, except now we're going to assume that these guys are separated in time. So these two steps don't have to occur simultaneously. They could actually take place at quite different times. The first step of the Diffie-Hellman protocol is what we're going to view as key generation. That is, the public key is going to be this capital A, and the secret key is simply going to be the little a. So you notice, of course, that extracting the secret key from the public key, namely extracting little a from capital A, is a discrete log problem, so that recovering a secret key is actually difficult. Okay, so this gives us our public key. So now at a later time, Bob wants to encrypt a message to Alice, encrypted using her public key. So how does Bob encrypt? Well, what he's going to do is he's going to compute his contribution to the Diffie-Hellman protocol. Namely, he's going to send over G to the little b. Of course, he's going to choose this little b at random. And now he's going to compute by himself the shared secret. So he's going to compute by himself G to the AB. From this G to the AB, he's going to derive a symmetric key for a symmetric encryption system, and then he's going to encrypt the message M using the symmetric key that he just derived. And that's the pair that he's going to send. So he's going to send over his contribution to the Diffie-Hellman protocol plus the symmetric encryption of the message M that he wants to send over to Alice. Okay, so you can see basically we are doing the exact same thing as we would do in the Diffie-Hellman protocol, except now where Bob directly, immediately is using his Diffie-Hellman secret to encrypt the message that he wants to send over to Alice. Now what does Alice do to decrypt? Basically she's going to also compute the Diffie-Hellman secret. Remember, now she just received Bob's contribution to the Diffie-Hellman protocol, and she has her secret key A, so she can compute also the Diffie-Hellman secret, namely G to the AB, from which she's going to derive the symmetric encryption key K, and then she's going to decrypt the message to recover the actual plaintext. Okay, so that's the intuition for how we convert the Diffie-Hellman protocol into a public key system. By the way, this was kind of an interesting development at the time that it came out, partially because you notice this is a randomized encryption scheme. So every time Bob encrypts a message, it's required that he choose a new random B and encrypt the message using this new random B. So let's see the ElGamal system actually in more detail. So now actually let's view it as an actual public key encryption system, namely algorithm Gen, algorithm E, and algorithm D. So as usual, we're going to fix our finite cyclic group of order n. Another ingredient that we're going to need is a symmetric encryption system. So I'm going to refer to it as E sub s and D sub s. These are the encryption and decryption algorithms of a symmetric encryption system that happens to provide authenticated encryption. And the key space for this system is capital K. And then we're also going to need a hash function that maps pairs of elements in the group, namely elements in G squared, into the key space. Now here's how the public key encryption system works. So I have to describe three algorithms. Algorithm that generates the public key and the secret key, and then the encryption and decryption algorithms. So the key generation algorithm works as follows. All we do is basically build up Alice's contribution to the Diffie-Hellman protocol. What we're going to do is we're going to choose a random generator G and G, and then we're going to choose a random exponent A. The secret key is going to be A, and then the public key is going to be the generator G and Alice's contribution to the Diffie-Hellman protocol. The reason, by the way, we don't use a fixed generator is because it allows us to somewhat use a weaker assumption in proving security, and so it's actually better to choose a random generator every time. It's easy enough to choose a random generator. All we do is we take the generator that we started with, and then we raise it to some power that's relatively prime to n. And that will give us another generator, a random generator of the group capital G. Okay, so you can see here that, again, public key is simply Alice's contribution to the Diffie-Hellman protocol, and the secret key is the random A that she chose. Now, how do we encrypt and decrypt? Well, when Bob wants to encrypt a message, he's going to use the public key. Remember, it consists of G and H. And here he wants to encrypt a message M. So here's what he's going to do. So he's going to choose his contribution to the Diffie-Hellman protocol. So this is the secret B that he would normally choose in Diffie-Hellman. And now he's going to compute G to the B, which is actually his message that gets sent to Alice in the Diffie-Hellman protocol. He's going to compute the Diffie-Hellman secret. That's H to the B. If you remember, H was G to the A. Therefore, this value here is really G to the AB. That's the Diffie-Hellman secret. That's the one thing that the attacker doesn't actually know. Next, he's going to compute a symmetric key by basically hashing this pair U comma V. So U, of course, is something that the attacker is going to know because that's going to be sent as part of the ciphertext. But V, the attacker isn't going to know. Again, for the proof of security, actually it helps to hash both U and V. And so we hash both of them together. Although strictly speaking, we just needed to hash V because V is the only value that the attacker doesn't know. The attacker already knows U because that's going to be part of the data that's sent on the network. So anyhow, so Bob derives this symmetric key K by hashing U and V. Then he goes ahead and encrypts the message using the symmetric key K. And finally, he outputs his contribution to the Diffie-Hellman protocol, the value U, and then the symmetric ciphertext that directly encrypts the message M. That's it. So the ciphertext consists of these two parts, and that's the thing that gets sent over the network. Let's see how does Alice decrypt now. So she's going to use her secret key A to decrypt, and she receives here Bob's contribution to the Diffie-Hellman protocol, plus the symmetric encryption of the message that Bob sent. What she'll do is she'll compute herself the Diffie-Hellman secret. If you remember, U to the A is simply G to the B to the A, which is G to the AB. So here, Alice computed the Diffie-Hellman secret. And now let me ask you, how does she derive the symmetric key K, given the Diffie-Hellman secret G to the AB and the ciphertext that she was given? Well, what she'll do is simply, again, now she has U from the ciphertext, and she has V because she just computed it herself. So now she can rederive the symmetric encryption key by hashing U and V together to get the symmetric encryption key, and then she just decrypts the ciphertext to get the actual plaintext. Okay, so that's it. That's the whole encryption and decryption algorithm. In a picture, the way the ciphertext would look is also as kind of what we saw in the last lecture. Basically, there would be a short header that contains U, which, as you recall, is G to the B. And then the rest of the ciphertext would be the encryption of the message that's being sent under the symmetric key K. And then to decrypt, Alice would use this header to derive the Diffie-Hellman secret, from which she will derive K, and then decrypt the body to get the original plaintext. By the way, I should note that the way I describe the system here is actually not how ElGamal described it originally. This is in some sense a modern view of ElGamal encryption, but it's pretty much equivalent to how ElGamal viewed it. So now let's look at the performance of ElGamal. So here what I wrote is the kind of the time-intensive steps of ElGamal encryption. Namely, during encryption, there are these two exponentiations in the group G. Exponentiation, remember, is a cubic time algorithm using the repeated squaring algorithm, and as a result, it's fairly time-intensive. And when I say time-intensive, I mean that on a modern processor, it would take a few milliseconds to compute these exponentiations. And during decryption, basically, the decryptor computes one exponentiation, namely U to the A. This is the bottleneck during decryption. Okay, so you would think that encryption actually takes twice as long as decryption because encryption requires two exponentiations, whereas decryption requires only one. It turns out that's not entirely accurate because you notice that the exponentiation during decryption is done to a variable basis, namely U changes every time, whereas during encryption, the basis is fixed. G and H are derived from the public key and are fixed forever. So in fact, it turns out if you want to do exponentiation to a fixed basis, you can do a lot of pre-computation. In particular, you can do all the squaring steps in the repeated squaring algorithm offline. So here what you would do is you would compute all powers of 2 of g. So you would compute g squared, g to the 4th, g to the 8th, g to the 16th, g to the 32, and so on and so forth. These are all the squaring steps of the repeated squaring algorithm you would do offline. The same thing for h. And then when it comes time to actually do the real exponentiation, all you need to do is just do the multiplications to accumulate these powers of 2 into the exponent b that you're trying to compute. So if you think about it, this can actually speed up exponentiation by a factor of 3. In fact, it would speed up it even more if you allow me to store even larger tables. This is called a windowed exponentiation. But regardless, if you allow the encryptor to store large tables that are derived from the public key, then in fact encryption is not going to be slower than decryption. In fact, encryption will be faster than decryption. But again, this requires the encryptor to pre-compute these large tables and store them around. So if all the encryptor is doing is just constantly encrypting to a single recipient, that could be done actually fairly fast using these pre-computed tables. If the encryptor for every message is encrypting to a different recipient, for example, if every time you send an email to a different recipient, then in fact the encryption will be twice as slow as decryption. So this is a good trick to keep in mind. In fact, most crypto libraries don't do this. And so if you see that you're always encrypting to the same public key, and for some reason your encryption process takes a lot of time, is a bottleneck for you, keep in mind that you can actually really speed things up using pre-computation. Of course, if encryption is a bottleneck for you, you might as well be using RSA, where in RSA encryption is really fast. Okay, so that's the end of our description of ElGamal encryption. And now the next question, of course, is why is the system secure? In particular, can we prove that it's chosen ciphertext secure? And more importantly, kind of under what assumptions can we prove that the system is chosen ciphertext secure? And so we're going to discuss that in the next segment. In this segment, we're going to study the security of the ElGamal public key encryption system. So let me remind you that when we first presented the Diffie-Hellman Protocol, we said that its security is based on an assumption that says that given g to the a, and g to the b, it's difficult to compute the Diffie-Hellman secret at g to the ab. This is basically what the attacker has to do. He sees Alice's contribution, he sees Bob's contribution, and then his goal is to figure out what the Diffie-Hellman secret is. And we said that this problem is difficult. The statement that this problem is difficult is what's called the computational Diffie-Hellman assumption. So let's state this assumption more precisely. So as usual, we're going to look at a finite cyclic group of order n. So G is some group. In your head, you should be thinking ZP star, but there could be other groups, for example, like an elliptic curve group. And then we say that the computational Diffie-Hellman assumption, I'll often use the shorthand CDH for computational Diffie-Hellman, will say this assumption holds in G if the following condition holds, namely for all efficient algorithms, if we choose a random generator, and then we choose random exponents a and b and zn, then when we give the algorithm g to the a, and g to the b, the probability that the algorithm will produce the Diffie-Hellman secret is negligible. If this is true for all efficient algorithms, then we say that the CDH assumption holds for G. CDH, as I said, stands for computational Diffie-Hellman. As it turns out, this assumption is not ideal for analyzing the security of the ElGamal system, and instead I'm going to go ahead and make a slightly stronger assumption called a hash Diffie-Hellman assumption. Okay? So what is the hash Diffie-Hellman assumption? Again, we're focusing on a particular group G, and now we're going to also introduce a hash function H that maps pairs of elements in G into the key space of some symmetric encryption system. And then we say that the hash Diffie-Hellman assumption, or HDH for short, holds for this pair G, H for the group and the hash function if the following is true. Basically, if I choose a random generator, and then I choose random exponents a and b and zn, and then I also choose a random r and k, then the following distributions are computationally indistinguishable. That is, if I give you g to the a, g to the b, and then this hash value, this should look familiar to you. This is the hash value that's used in the ElGamal system to derive the symmetric encryption key. What we're saying is that this distribution is indistinguishable from a distribution where you're also given g to the a, g to the b, but now instead of giving the hash, you're given just truly random key. So what this assumption says is that the symmetric key that was derived during encryption in the ElGamal system essentially is indistinguishable from a truly random key that's derived independently from the rest of the parameters of the system. It's a truly independent random key. It looks basically the same as the key that we used to derive from the g to the a and g to the b. Now I'd like to point out that the hash Diffie-Hellman assumption is actually a stronger assumption than the computational Diffie-Hellman assumption. The way to see that is using the contrapositive. That is, suppose the computational Diffie-Hellman assumption happens to be easy in the group G. Then I claim that, in fact, the hash Diffie-Hellman assumption is also easy in the group G. In fact, I'll say for G comma H, and this is true, in fact, for all hash functions where the image of the hash function is contains at least 2 elements. In other words, all I want to say is that the hash Diffie-Hellman assumption then is easy for all hash functions that don't map everything to a single point, which is true for almost all hash functions of interest to us. So actually, this is a really simple statement to prove. Basically, if the computational Diffie-Hellman assumption is easy, what that says is that given g to the a and g to the b, I can actually calculate g to the ab myself. Because I know the hash function h, I can calculate this complete value here. So if you give me a tuple that's sampled from the left or sampled from the right, I can very easily tell where it's from. If it's sampled from the left, then once I've calculated g to the ab myself, I can just test that the last element in the tuple is in fact the hash of g to the b and g to the ab. If it is, I know the sample is from the left. If it isn't, I know the sample is from the right. Okay, so this gives me pretty high advantage in distinguishing these two distributions. So if CDH is easy, it's very easy to see that these distributions are distinguishable. This basically says that if the hash Diffie-Hellman is in fact hard, then CDH must also be hard, which then we say that therefore the hash Diffie-Hellman is a stronger assumption. There might be group where CDH is hard, but HDH is not hard. Okay, so we say that HDH is a stronger assumption. If you found this discussion of weak assumption versus strong assumption confusing, it's not really that important. It's fine to ignore it. The important thing that I want to show you is, in fact, that the hash Diffie-Hellman assumption is sufficient to prove the semantic security of the ElGamal system. Before we do that, let me quickly ask you the following puzzle, just to make sure the hash Diffie-Hellman assumption is clear. So imagine our key space is 01 to the 128, so 128-bit strings, and our hash function will map pairs of group elements into these 128-byte strings. Suppose it so happens that we chose a hash function such that it always outputs strings that begin with 0. In other words, of the 128-bit strings, the most significant bit of the output is always 0. If we chose such a hash function, does the hash Diffie-Hellman assumption hold for this pair g comma h? So the answer is no, it doesn't hold, and the reason is because it's now very easy to distinguish the two distributions that we have here, the distribution on the left and the distribution on the right. And the way you would distinguish the two is basically if I choose a truly random element in k, in 01 to the 128, the most significant bit will be 0 with probability 1/2. However, if the tuple that's given to me is chosen from the left distribution, then the most significant bit of the hash will always be 0. And therefore, if I see 0, I'm going to say the distribution is the distribution on the left. If I see 1, I'm going to say the distribution is the distribution on the right. And that will give me advantage 1/2 in distinguishing these two distributions. And so as a result, the hash Diffie-Hellman assumption is false in this case. So clearly you can see that even though CDH might be hard in a certain group G, if you choose a bad hash function, then HDH will not hold for the pair G comma H. Okay, but suppose it so happens that we choose a group G and a hash function H for which the hash Diffie-Hellman assumption holds. And in fact, if you choose the hash function to be just SHA-256, for all we know, the hash Diffie-Hellman assumption holds in the group ZP star and holds in elliptic curve groups. My goal now is to show you that ElGamal is in fact semantically secure under the hash Diffie-Hellman assumption. So let me quickly remind you how the ElGamal system works. Well, we're going to choose a random generator G. We're going to choose a random A and Zn. The public key is going to be G and G to the A. The secret key is simply going to be A. And now here I wrote shorthand for the ElGamal encryption. Basically what to encrypt, what we do is we choose a random B. We hash G to the B and H to the B. Remember, this H to the B is the value G to the AB. This is the Diffie-Hellman secret. The hash function gave us a symmetric encryption key K. We encrypt the message with K, and we output G to the B and the symmetric ciphertext. To decrypt, we hash the value U and the Diffie-Hellman secret U to the A. To derive the symmetric key, we decrypt the ciphertext, and then we output the plaintext message M. So now let's see how to argue that, in fact, ElGamal is semantically secure under this hash Diffie-Hellman assumption. It's fairly simple. So, well, we have to argue. Remember, we had in semantic security, we have these two experiments. In one experiment, the attacker is given the encryption of M0. In the other experiment, the attacker is given the encryption of M1. So I wrote the two experiments here. Here, you notice that the attacker starts by sending off the public key to the adversary. The adversary then chooses two equal length messages, M0 and M1. and then he gets the ElGamal encryption of M0, and I kind of wrote shorthand for what this ElGamal ciphertext is. Okay? Similarly, in encryption 1, he simply gets the encryption of M1 instead of M0, and everything else is the same about these two experiments. Now, because of the hash Diffie-Hellman assumption, we know that even though the attacker got to see G to the A, and G to the B, we know that the output of the hash of G to the B, G to the AB is indistinguishable from random. Therefore, if we replace the actual hash function by a truly generated random key K that's independent of everything else, by the hash Diffie-Hellman assumption, the attacker can't distinguish these two games. And again, it's a simple exercise for you to show that if he could distinguish these two games, then he would break the hash Diffie-Hellman assumption. But then the same is true for experiment 1. The attacker also could not distinguish the output of the hash function from a truly random key that was used to generate the challenge ciphertext. Okay? So now basically we look at these two experiments and you realize, wait a minute, what's going on in these two experiments? Basically everything is the same, except in one experiment the attacker gets the encryption under a symmetric encryption system of M0, and in the other one he gets the encryption under a symmetric encryption system of M1, and the key is chosen at random independently of everything else. So by the fact that the symmetric encryption system is semantically secure, these two games are indistinguishable. If they were distinguishable, then the attacker could break the semantic security of the symmetric encryption system. So now we kind of prove this, this chain of equivalences, and that proves that the original games, in fact, are indistinguishable, computationally indistinguishable, and therefore the ElGamal system is semantically secure. Okay, so it's like I said, a very simple proof by pictures, and you can make this into a rigorous proof without too much work. But semantic security isn't enough. What we really want is chosen ciphertext security. And the question is ElGamal chosen ciphertext secure? So it turns out to prove the chosen ciphertext security of ElGamal, we actually need a stronger assumption. Hash Diffie-Hellman or computational Diffie-Hellman are actually not enough to prove chosen ciphertext security of the system as far as we know. So to prove chosen ciphertext security, I'm going to introduce a new assumption called the interactive Diffie-Hellman assumption. And actually, technically, we really don't like this assumption. And we're going to try and get rid of this later on. But for now, we just want to analyze the security of the basic ElGamal system against chosen ciphertext attack. So to argue that it is chosen ciphertext secure, here is what the assumption says. Basically, the challenger starts, plays a game with the adversary. He generates a random G, generates two exponents, and then he sends to the adversary, as usual, G, G to the A, and G to the B. Now, the adversary's goal is basically to figure out the Diffie-Hellman secret, namely G to the AB. He outputs the value V, and he wins the game if V happens to be equal to G to the AB. So far, this looks identical to the computational Diffie-Hellman assumption. There's no difference. This is the computational Diffie-Hellman assumption. Except in interactive Diffie-Hellman, we give the attacker a little bit more power. So because the attacker has more power, it's harder to satisfy the assumption, which is why we say that this assumption is stronger than computational Diffie-Hellman. Now, what is this power that we give him? We give him the ability to make queries. In particular, he gets to submit two elements from the group G. So U1, V1 is a pair from the group G. And then he's told whether U1 to the A is equal to V1, so he gets 1 if U1 to the A is equal to V1, and he gets 0 otherwise. It's kind of a bizarre type of query. How can this possibly help the attacker? But it turns out we need to be able to answer these types of queries for the adversary in order to be able to prove chosen ciphertext security. And in fact, he can do these types of queries again and again and again, so he can issue as many queries like this as he wants. And then the assumption says that despite all these queries, he still can't figure out the Diffie-Hellman secret. Namely, despite making all these queries, the probability that he outputs the Diffie-Hellman secret is negligible. Okay? So clearly, if this assumption holds, then the computational Diffie-Hellman assumption holds, because here the adversary has more power, and as a result we say that this assumption is stronger than computational Diffie-Hellman. The thing we really don't like about this assumption is the fact that it's interactive, and that the adversary is allowed to make queries to the challenger, and as I said, we're going to try and get rid of this interaction later on. But for now, I'll tell you that under this interactive Diffie-Hellman assumption, and under the assumption that the symmetric encryption system provides authenticated encryption, and under the assumption that the hash function is kind of an ideal hash function, what we call the random oracle, then in fact the ElGamal system is chosen ciphertext secure, and again this RO here denotes the fact that it's in the random oracle model, which is not important so much for our purposes. The main thing to remember that under kind of this weird interactive assumption, we can actually prove that ElGamal is chosen ciphertext secure. And as far as we know, this assumption actually holds for the group ZP star. So what we're going to do next is basically answer this question of whether we can get rid of the interactive assumption. Can we prove security strictly based on CDH? And similarly, can we prove security without relying on random oracles? Just, without having to assume that the hash function is ideal, just, can we prove security using a concrete hash function? And we'll do that very briefly in the next segment. In the last segment, we saw that the ElGamal public key encryption system is chosen ciphertext secure under a somewhat strange assumption. In this segment, we're going to look at variants of ElGamal that have a much better chosen ciphertext security analysis. Now, I should say that over the past decade, there's been a ton of research on constructing public key encryptions that are chosen ciphertext secure. I actually debated for some time on how to best present this here, and finally I decided to kind of show you a survey of the main results from the last decades, specifically as they apply to the ElGamal system. And then at the end of the module, I suggest a number of papers that you can look at for further reading. So let me start by reminding you how the ElGamal encryption system works. I'm sure by now you all remember how ElGamal works, but just to be safe, let me remind you that key generation ElGamal picks a random generator, a random exponent from Zn, and then the public key is simply the generator and this element g to the a, whereas the secret key is simply the discrete log of h base g, this value a. Now the way we encrypt is we pick a random exponent b from Zn, we compute the hash of g to the b and h to the b, and again I remind you that h to the b is the Diffie-Hellman secret, g to the ab, and then we actually encrypt the message using a symmetric encryption system with the key k that's derived from the hash function. And finally the output ciphertext is g to the b and the symmetric ciphertext. The way we decrypt is, as we've seen before, basically by hashing u and the Diffie-Hellman secret, decrypting the symmetric system, and outputting the message m. Now, in the last segment, we said that ElGamal is chosen ciphertext secure under this funny interactive Diffie-Hellman assumption. I'm not going to remind you what that assumption is here, but I'll just say that this theorem kind of raises two very natural questions. The first question is, can we prove CCA security of ElGamal just based on the standard computational Diffie-Hellman assumption? Namely, that given g to the a, g to the b, you can't compute g to the ab. Can we prove chosen ciphertext security just based on that? And it turns out there are two ways to do it. The first option is to use a group where the computational Diffie-Hellman assumption is hard, but is provably equivalent to the interactive Diffie-Hellman assumption. And it turns out it's actually not that hard to construct such groups. These groups are called bilinear groups. And in such groups, we know that the ElGamal system is chosen ciphertext secure strictly based under the computational Diffie-Hellman assumption, at least in the random oracle model. I'll tell you that these bilinear groups are actually constructed from very special elliptic curves. So there's a bit more algebraic structure that enables us to prove this equivalence of IDH and CDH. But in general, who knows? Maybe you don't want to use elliptic curve groups. Maybe you want to use ZP star for some reason. So it's a pretty natural question to ask, can we change the ElGamal system such that chosen ciphertext security of ElGamal now can be proven directly based on CDH for any group where CDH is hard? Now, without assuming any additional structure about the group. And it turns out the answer is yes, and there's kind of an elegant construction called twin ElGamal. So let me show you how twin ElGamal works. It's a very simple variation of ElGamal that does the following. Again, in key generation, we choose a random generator, but this time we're going to choose two exponents, a1 and a2, as the secret key. So the secret key is going to consist of these two exponents, a1 and a2. And now the public key, of course, is going to consist of our generator, and then we're going to release g to the a1 and g to the a2. So remember that in regular ElGamal, what the public key is simply g to the a, and that's it. Here we have two exponents a1 and a2, and therefore we release both g to the a1 and g to the a2. Now the way we encrypt, you notice the public key here is one element longer than regular ElGamal. The way we encrypt using this public key is actually very similar to regular ElGamal. We choose a random b, and now what we'll hash is actually not just g to the b and h1 to the b, but in fact g to the b, h1 to the b, and h2 to the b. Okay, so we're basically hashing three elements instead of two elements. And then we basically encrypt the message using the derived symmetric encryption key. And as usual, we output g to the b and c as our final ciphertext. How do we decrypt? Well, so now the secret key consists of these two exponents, a1 and a2. And the ciphertext consists of u and the symmetric ciphertext c. So let me ask you a puzzle and see if you can figure out how to derive the symmetric encryption key k just given the secret key and the value u. So it's kind of a cute puzzle, and I hope everybody worked out the solution which is basically what we can do is we can take u to the power of a1, and that is basically g to the b a1, and u to the a2, which is g to the b a2. And that basically gives us exactly the same values as h1 to the b and h2 to the b. So this way, the decryptor arrives at the same symmetric key that the encryptor did, then he decrypts the ciphertext using the symmetric system, and finally outputs the message M. So you notice this is a very simple modification to regular ElGamal. All we do is we stick one more element in the public key. When we do the hashing, we hash one more element as opposed to just two elements. We hash 3 elements, and similarly we do during decryption. And nothing else changes. The ciphertext is the same length as before, and that's it. Now the amazing thing is that this simple modification allows us to now prove chosen ciphertext security directly based on the standard computational Diffie-Hellman assumption. Okay? Still, we're going to need to assume that we have a symmetric encryption system that provides authenticated encryption, and that the hash function that we're using is an ideal hash function in what we call a random oracle. But nevertheless, given that, we can prove chosen ciphertext security strictly based on the computational Diffie-Hellman assumption. So now what's the cost of this? Of course, if you think about this, during encryption and decryption, the encryptor has to do one more exponentiation, and the decryptor has to do one more exponentiation. So the encryptor now does 3 exponentiations instead of 2, and the decryptor does 2 exponentiations instead of 1. So the question is now it's a philosophical question. Is this extra effort worth it? So you do more work during encryption and decryption, and your public key is a little bit bigger, but that doesn't really matter. The work doing encryption and decryption is more significant. And as a result, you get chosen ciphertext security based on kind of a more natural assumption, namely computational Diffie-Hellman, as opposed to this odd-looking interactive Diffie-Hellman assumption. But is it worth it? Kind of the question is, are there groups where CDH holds, but IDH does not hold? If there were such groups, then it would definitely be worth it, because in those groups, the twin ElGamal would be secure, but the regular ElGamal would not be CCA-secure. But unfortunately, we don't know of any such groups, and in fact, as far as we know, it's certainly possible that any group where CDH holds, IDH also holds. So the answer is that really we don't know whether this extra cost is worth it or not, but nevertheless, this is a cute result that shows that if you wanted to achieve chosen ciphertext security directly from CDH, you can do it without too many changes to the ElGamal system. The next question is whether we can get rid of this assumption that the hash function is an ideal hash function, namely it's a random oracle. And this is actually a huge topic. There's a lot of work in this area on how to build efficient public key encryption systems that are chosen ciphertext secure without random oracles. This is a very active area of research, as I said, in the past decade and even longer. And I'll mention that as it applies to ElGamal, there are basically, again, 2 families of constructions. The first construction is a construction that uses these special groups called these bilinear groups that I just mentioned before. It turns out the extra structure of these bilinear groups allows us to build very efficient chosen ciphertext secure systems without referring to random oracles. And as I said at the end of the module, I point to a number of papers that explain how to do that. This is quite an interesting construction, but it would take me several hours to kind of explain how it works. The other alternative is actually to use groups where a stronger assumption called the decision Diffie-Hellman assumption holds. Again, I'm not going to define this assumption here. I'll just tell you that this assumption actually holds in subgroups of ZP star. In particular, if we look at a prime order subgroup of ZP star, the decision Diffie-Hellman assumption seems to hold in those groups. And then in those groups, we can actually build a variant of ElGamal called the Kramer-Shoup system that is chosen ciphertext secure under the decision Diffie-Hellman assumption without random oracles. Again, this is a beautiful, beautiful result, but again, it would take a couple of hours to explain, and so I'm not going to do that here. This is probably one of these things that I'm going to leave to either the advanced topics or to an advanced course that we'll do at a later time. But again, I point to a paper at the end of the module just in case you want to read more about this. So here's a list of papers that provides more reading material. So if you want to read about Diffie-Hellman assumptions, I guess I wrote a paper about this a long time ago that talks about various assumptions related to Diffie-Hellman, and in particular studies the decision Diffie-Hellman assumption. If you want to learn about how to build chosen ciphertext secure systems from decision Diffie-Hellman and assumptions like it, there's a very cute paper by Kramer and Shoup back from 2002 that shows how to do it. This is, again, a very highly recommended paper. If you want to learn how to build chosen ciphertext security from these bilinear groups, then the paper to read is the one cited here, which actually uses a general mechanism called identity-based encryption, which very surprisingly turns out to actually give us chosen ciphertext security almost for free. So once we build identity-based encryption, chosen ciphertext security follows immediately. And that's covered in this paper that I describe here. The twin Diffie-Hellman construction and its proof is described in this paper that I reference here. And finally, if you want to kind of see a very recent paper that gives a very general framework for building chosen ciphertext secure systems using what's called extractable hash proofs, then there's again a nice paper by Ho-Taek Kui that was just recently published. I definitely recommend reading. They're all have very, very elegant ideas in them. I wish I could cover all of them in the basic course, but I'm going to have to leave some of these to the more advanced course, or perhaps the more advanced topics at the end of this course. Okay, so I'll stop here, and in the next segment I'm going to tie ElGamal and RSA encryption together so that you see how the two kind of follow from a more general principle. This week we saw two families of public key encryption systems. One family was built from trapdoor functions, in particular RSA, and the other family was built from the Diffie-Hellman Protocol. In this last segment, I want to show you that both families, in fact, follow from a more general principle. The unifying theme is what's called a one-way function. So what is a one-way function? Well, we've already seen this concept briefly before, but basically a function from one set to another, say from x to y, is said to be one way if, in fact, there's an efficient algorithm that allows us to evaluate the function f. So anyone can evaluate the function f at any point of their choice. However, inverting the function f should be difficult. That's what makes the function one way. So what do I mean by that? Well, you can think of the function f as a function, again, mapping the set x to the set y. But it so happens that many points in x could actually be mapped into a single point in y. Now, when I say that the function is difficult to invert, what I mean is that when I give you some point inside of y and I ask you, find me a pre-image of this point, you won't be able to point to any of these as a pre-image. In other words, no efficient algorithm can find any point that is the inverse of the given point y. Now, the way we say that more precisely is that we say that for all efficient algorithm A, if I choose a random x in the set capital X, and now I'm going to give f of x to algorithm A, and then what I'm going to ask algorithm A to do is basically produce a pre-image of the point f of x. Well, what does it mean that A produced a pre-image of the point f of x? It means that if I apply the function f to the output of A, what I should get back is, well, f of x. Let's think through this one more time. So I choose a random point x in capital X, and now I give algorithm A f of x. So I'm going to give algorithm A this point here. And now A is going to produce some point. So let's pretend that A produces this point over here. And now I want to say that if I apply the function f to this point here that A produced, the probability that I get the same point that I started with is negligible. In other words, the probability that algorithm A was able to produce one of these 3 points is in fact negligible. All it could do is produce some other point that maps into something other than f of x. Okay, so again, all this is trying to do is just capture the fact that given f of x, it's hard to find some pre-image of f of x. So here are some easy examples of functions that are not one way. For example, the identity function f of x is equal to x is trivially not one way because given f of x, I can easily come up with an inverse of f of x, namely x. Similarly, the function that maps everything to 0 is also not one way. So in a picture, let's see, the function that maps everything to 0 simply looks as follows. It takes all its points and maps them all to a single point. Well, this function is not one way because if I give you this point in the image, it's trivial to find a pre-image, namely just pick any point in capital X and that will be a pre-image of 0. And so f of x equals to 0 is also not a one-way function. And by the way, I didn't want to do it here, but if I define one-way functions more formally, then it turns out that proving that one-way functions exist will have also proven that p is not equal to np. So since we can't today prove that p is not equal to np, basically we can't prove that one-way functions exist, and we just have to assume that they do. So let's look at our first example of a one-way function, or at least a presumed one-way function. And so we're going to build it from a pseudo-random generator. So suppose I have a function f from x to y that is a secure pseudo-random generator. So the output of f is much larger than the input. Remember, a pseudo-random generator takes a small seed and expands it into a much larger output. And for example, you can imagine, this pseudo-random generator maybe is built using deterministic counter mode out of AES. Well, it's fairly easy to see that if in fact f is a secure pseudo-random generator, then f is in fact a one-way function. So our first example of a one-way function is directly built from a pseudo-random generator. This is actually kind of a trivial proof, so let's prove the contrapositive. So suppose I have an efficient algorithm that inverts f. Okay, so I'm proving the contrapositive. Suppose f is not one way, then A is an efficient algorithm that inverts f. And now I need to build an algorithm B that breaks the pseudorandom generator. Okay, so I'm proving again contrapositive. Okay, so how do I break the pseudorandom generator? Well, all we do is the following. So algorithm B is given some y in the set y. And what it's going to do is the following. It's going to try and run algorithm A on the input y. And now, well, if y is the output of the pseudorandom generator, then algorithm A will output the seed, namely an element in x, with non-negligible probability. So what we'll do is we'll apply the pseudorandom generator again to the output of algorithm A. As I said, if y was the output of the generator, then A of A will have output the seed because it inverted the pseudorandom generator. So if we apply the pseudorandom generator again to the output of A, what we should get back is basically the y that we started with. Okay? So if this condition holds, we're going to say we're going to output 0. And if condition doesn't hold, we're going to output 1 otherwise. That's it. That's our distinguisher against the pseudorandom generator. So if our distinguisher is given a y that is the output of the pseudorandom generator, then with non-negligible probability, our distinguisher B will output 0. However, if our distinguisher B is given a truly random string, well, a truly random string doesn't have any seed that causes the generator to output that string. And therefore, our distinguisher will output 1 with also very high probability. And again, I hope that's clear. Basically, if we look at the set of all possible outputs, namely the set y, very few of those outputs happen to be the output of the pseudorandom generator. So if we're just given an output y over here, say, that's not the output of the pseudorandom generator, then when we run algorithm A on it, it can't possibly produce a seed that will output this point star, because there is no such seed. And as a result, since most points actually are not in the image of the pseudorandom generator, most points will not have a seed that maps the generator to them. And as a result, when we're given a random point in y, a truly uniform point in y, our distinguisher B will output 1 with very high probability. However, if we are given a pseudo-random output of the generator, then algorithm A will output the corresponding seed. When we apply the generator to that seed, we'll get the initial output y, and therefore we'll output 0 with non-negligible probability. Okay, so if A was able to invert f, then B is able to break the generator. And since the generator is secure, algorithm A can't invert f, and in particular, no efficient algorithm can invert f. And therefore, f is a one-way function. Excellent. So this is a long discussion of kind of a minor point. But all I wanted to show you is that, in fact, a pseudorandom generator directly gives us a one-way function. Unfortunately, this one-way function has no special properties, and what that means is it's actually difficult to use it for key exchange or for public key encryption. In some sense, the best key exchange we can do with this, as far as we know, is Merkle Puzzles. So now let's look at our second example. The second example is what I'm going to call the discrete log one-way function. So let's fix a group, a cyclic group of order n, the group G, and let G be some generator of the group capital G. So again, I remind you that all that means is that if I look at all powers of G, then I basically span the entire group capital G. And now let's define the following function. The function goes from Zn to G and is defined basically as the exponentiation to the power of x. Okay, so this maps any element between 0 and n minus 1 to an element of the group capital G simply by raising G, little g, to the appropriate power. And it's kind of obvious that if the discrete log problem in the group capital G is hard, then in fact f is one way. In fact, the one-wayness of f is the discrete log assumption. So if discrete log is hard, f is one way. Now the interesting thing about this one-way function is it's got some interesting properties. In particular, if I give you f of x and f of y, I claim that it's very easy to compute f of x plus y. Even though we have no idea what x or y are, all we're given is just f of x and f of y, nevertheless we can compute f of x plus y. Let me ask you, how would you do that? Well, just by rules of exponentiation, basically f of x plus y is simply f of x times f of y. And again, this is all done inside the group G. If you're not convinced, simply recall that f of x plus y is g to the x plus y, which is simply g to the x times g to the y, which is exactly what we have here. And this simple property, this simple fact that the function has this additive property, if you think about it, is exactly what enables key exchange and public key encryption. So this additional property of the one-way function is what enabled all of public key cryptography. So let's look at our next example. The next example is the RSA one-way function. So here we're going to choose two primes p and q. We're going to set n to be p times q. Then we're going to choose some e that's relatively prime to phi of n. And then we define the function simply, it's a function from zn star to zn star, simply as f of x equals x to the e. Okay, so raising x to the power of e. And again, we say that this function is one way simply under the RSA assumption. Again, the RSA assumption is the assumption that this function is one way. Now, the interesting thing about this function is that it has properties similar to the one that we saw on the previous slide, namely that given f of x and f of y, now we can compute f of x times y as opposed to f of x plus y. So we say that this function has a multiplicative property as opposed to the additive property on the previous slide. But more importantly, this is kind of not the most interesting thing about this function. The really exciting thing about this function is that it in fact has a trapdoor. In other words, there's a secret key that all of a sudden allows us to invert this function, even though without the secret key, the function is one way, as far as we know. And this property, I'll say, the fact that it has a trapdoor, again, enabled all of public key cryptography. I'll say that this trapdoor also makes the RSA function especially well suited for digital signatures. In week 7, we're going to see that both the RSA function and the discrete log functions let us construct digital signatures. But the RSA function, because it has a trapdoor, makes it very, very easy to construct digital signatures from it. And so, in fact, most digital signatures out there in the world, in fact, rely on the RSA function just because it's so simple to build digital signatures from it. So again, we see that this one-way function with the special properties, it has a multiplicative property and a trapdoor, essentially again enables all of public key crypto. So to summarize, the reason we're able to build public key cryptography, namely the reason we're able to do key exchange and public key encryption and so on, is because we're able to construct one-way functions that have very, very special properties. In particular, they have these properties that are sometimes called homomorphic properties, namely that given f of x and f of y, we can construct f of x plus y or f of x times y. And some functions like RSA even have trapdoors, which let us build digital signatures very, very easily. But the main thing I wanted to show you is that the magic of public key crypto is basically made possible because of these one-way functions with their special properties. So that's the end of this module, and then in week 7 we'll start with digital signatures. This brings us to the end of the 6 weeks course. I had a lot of fun teaching this course, and I hope you enjoyed it too. I really love this material, and I always enjoy teaching it. Before we say our farewells, let's do a quick review of the topics that we discussed and see what's left to cover. So here's a brief diagram of the primitives that we discussed in the class. If you remember, in week 1, we started off by discussing the pseudorandom generators and stream ciphers. In week 2, we talked about block ciphers, and we said that the right way to think about block ciphers is as pseudorandom permutations and pseudorandom functions. We said that using counter mode, we can convert a block cipher into a PRG. And we said that using the GGM construction, we can construct block ciphers from pseudorandom generators. Then in week 3, we talked about data integrity. In particular, we talked about MACs, and we looked at various constructions of MACs from pseudorandom functions, like the CMAC, the HMAC, the PMAC constructions, and so on. We also discussed collision resistance, and we said that collision resistance can be used for data integrity where one has access to read-only memory. Basically, you would hash the data using a collision-resistant hash function, write the hash into read-only memory, and then later when you want to verify authenticity of your data, you just compare its hash to whatever is written in read-only memory. Then in week 4, we talked about how to combine integrity and confidentiality. In particular, we kind of talked about how to combine encryption and MACs to build what we called authenticated encryption. And I told you that really in practice, the only form of symmetric encryption that you're allowed to use is authenticated encryption. Basically, encryption that's only secure against eavesdropping attacks is not generally secure. You must always also guard against tampering, and as a result, you should only be using authenticated encryption modes to do symmetric encryption. So that was the end of week 4. And then for weeks 5 and 6, we switched topics and talked about key exchange and public key encryption. In particular, in week 5, we talked about trapdoor functions and the Diffie-Hellman Protocol. We did the mathematics that are necessary to explain how those things work. And then in week 6, we talked about how public key encryption can be built from trapdoor functions and the Diffie-Hellman Protocol. I want to emphasize that the key exchange protocols that we saw in week 5 are only secure against eavesdropping and should never be used in practice. In fact, in week 8, we're going to see authenticated key exchange protocols, and those are the ones that are actually used in the wild, for example, in SSL and other protocols like that. But the ones that we saw in week 5 should never actually be deployed in the real world. The only reason we looked at those simple key exchange mechanisms was as motivation for trapdoor functions and Diffie-Hellman groups. Now, as you know, there are 4 more weeks to the full crypto course, which we're going to do at a later time. In week 7, we're going to talk about digital signatures and how to authenticate data in a way that anyone can verify that the data is authentic. Then we're going to talk about authenticated key exchange, as I said. Then we're going to talk about user authentication, how to manage passwords, one-time passwords, challenge response protocols. Then we'll talk about various privacy mechanisms, how to authenticate yourself without revealing where you are, how to sign in a way that doesn't reveal who you are, and so on and so forth. And then as part of the building blocks for some of these mechanisms, actually we'll talk about zero-knowledge protocols, which is kind of a general-purpose tool that's used very widely in cryptography. But I should say that crypto goes way beyond these core topics. And in fact, there are many, many more topics that I would love to tell you about if there was enough time. So I made a kind of a short list here, and this isn't even an exhaustive list. There are many other things that I would like to tell you about. And so if there's enough demand, I might even run an advanced crypto class, which is usually what I do for our graduate students, which would cover these more advanced topics, but that would actually take place sometimes next year. So stay tuned, and I will send announcements on when that's coming. So my final words, of course, remember my main message from this class, in that crypto is a tremendous tool, but you should always be careful when you use it. If you implement crypto incorrectly, the system will work perfectly fine. There will be no way to tell that anything is wrong, except when an attacker tries to attack the system, it might be easily breakable. And so crypto is one of these things where a little bit of knowledge is quite dangerous. It's quite important to make sure you get the implementation correctly. And one way to do that is to make sure that always other people review your code and your designs to find any bugs in the crypto implementation, or maybe even more general bugs in the system design. And finally, I'll leave you with this parting words that you should never ever invent your own ciphers or your own modes, and you should never even implement your own ciphers or your own modes. Try to stick to the standards as much as possible. Try to stick to standard implementations of those algorithms as much as possible. And if you have to deviate from that, then just make sure there's sufficient third-party review of what you've done. Okay, so I will say my farewell here. And let me say that the final exam will be made available on week 7, basically a week after the week 6 lectures become public. The final exam will cover material from all 6 weeks, and it'll pretty much be the same format as the problem sets. I hope everybody will do well on the exam, and we will send certificates once all the coursework is complete. And I hope to see you in the next iteration of this course, whenever that's made available. So farewell, and as always, please submit your comments and suggestions on the forum. I read all of your posts, and they're very, very helpful in improving the course. Hope to see you in the fall.